Imagine the history of our planet stretching over billions of years. In this vast record, there's a gigantic blind spot, a gaping void millions of years long. What if we humans, with all our technology and cities, weren't the first to reach this level of development on Earth? This mind-boggling thought underlies the so-called Silurian Hypothesis, a scientific question NASA researchers dared to ask. The essence of this hypothesis is simple and yet terrifying. If another highly advanced civilization existed on this planet long before us, would we be able to find any traces of it today? Let's fast forward millions of years into the future. Our gigantic skyscrapers, once piercing the clouds, will have turned to dust. Even the most durable plastics and polymers, which we consider eternal, will be eaten away by time and microbes. Fossil remains of intelligent beings will become incredibly rare, isolated finds in the rock strata. However, some clues, invisible to the naked eye, may be preserved in the planet's rocky record itself. Imagine geological layers where scientists find inexplicable anomalies, sharp spikes in atmospheric carbon levels, or sudden, unprovoked periods of global warming. Today, we see such strange imprints in Earth's distant past, carbon spikes, layers indicating abrupt climate change, events that seem to occur spontaneously without any apparent geological or astronomical cause. Perhaps this is just a fluke, a quirk of nature, or perhaps these are the last fading echoes of an industrial civilization that time has wiped from the face of the earth. And if something like this happened once, who can guarantee it won't happen again? The Silurian Hypothesis is more than just science fiction. It challenges our traditional understanding of history, forcing us to question our understanding of the past. This idea, advanced by astrophysicist Adam Frank and planetary scientist Gavin Schmidt, invites us to look at things from a completely different perspective. What if intelligent life forms already existed on Earth, whose technological advances were completely destroyed and buried under the weight of natural geological processes? This is a radical departure from classical archaeology, which focuses exclusively on the evolution of our species. This hypothesis forces scientists to consider, what if civilization is not a unique phenomenon, but a repeating cycle that played out in our planet's deep past? It challenges our presumptuous idea that humanity is the pinnacle of creation, the first and only intelligent species on Earth. The hypothesis suggests that any traces of ancient technologically advanced societies could have been irrevocably erased or hidden by powerful forces of nature. Imagine the fiery breath of volcanoes drenching entire continents with lava, the slow but inexorable movement of tectonic plates crushing and submerging land into a boiling mantle. Or simply millions of years of erosion turning mountains into sand. This concept compels future archaeologists to become geological detectives, searching for subtle, ghostly traces, anomalous chemical signatures in ancient rocks, strange submerged structures on the ocean floor, or unusual sedimentary layers that could hint at industrial activity in the distant past. However, there's a huge problem with this approach. The Earth's geological record itself is a book from which entire chapters have been torn out, the remaining pages washed away by water and scorched by fire. It's incomplete and often open to two interpretations. Traditional archaeology is accustomed to relying on specific finds, artifacts, building ruins, cultural remains. But all these things disintegrate over millions of years. Therefore, the Silurian hypothesis requires a completely different approach, combining the efforts of specialists from various fields. Here, geology must work hand in hand with climatology, and the search for hidden clues in the Earth's interior will require harnessing the full power of modern technologies, such as isotopic analysis and sophisticated computer modeling. By asking questions about ancient civilizations in this way, this hypothesis doesn't just expand the horizons of science, it opens up entirely new avenues for understanding the history of our own planet. It forces us to consider, what are we missing if we view the past solely through the prism of our own human experience? At the very core of this idea lie profound questions about the durability of technological societies. Perhaps every civilization is destined to undergo cycles of prosperity and inevitable decline. And as we delve deeper into this topic, it becomes clear that even admitting the existence of pre-human civilizations could completely change our understanding of the stability of life, the history of intelligence, and whether the path of human development is unique or universal. This brings us to a broader discussion of why the search for traces of ancient civilizations that vanished before us is of such colossal scientific importance. We will explore this topic in detail below. The idea of the existence of civilizations that predated humankind is at the very center of contemporary scientific debate. It forces us to completely re-examine not only human history, but also the entire context of the development of life on our planet. Traditionally, archaeology has painted a picture of a consistent linear progression from primitive societies to complex civilizations, culminating in our modern era. However, this entire coherent picture rests on a single, shaky assumption that only humans are capable of creating complex technology and culture. Any evidence of other intelligent activity either simply doesn't exist or can easily be dismissed as freaks of nature. But what if we abandon this arrogant assumption? It instantly expands the horizons of scientific research to incredible limits. If civilizations existed before the advent of humans, their traces could have been safely hidden by time, buried under kilometers of geological strata, or even deliberately destroyed by those who created them. This, of course, complicates the search for evidence. But it also makes it far more exciting, forcing researchers to invent entirely new methods to detect subtle signs of past activity. These include searching for anomalous chemical signatures, strange geological formations, or artifacts whose origins cannot be explained by natural processes. The emergence of such evidence will not simply rewrite history books. It will raise a host of new questions about the viability and longevity of technological societies. We will be able to study their interactions with the environment and perhaps understand the reasons for their rise and tragic fall. Moreover, this idea has profound philosophical and existential implications. It deals a crushing blow to our notion of human exceptionalism, to the idea that humanity has some unique purpose in the universe. Recognizing the possibility of precursors forces us to be more modest and to take a much broader view of the potential of intelligent life. This also opens the door to incredible collaborations across disciplines. Geology, astronomy, biology, and archaeology must join forces to create a more complete and comprehensive picture of our planet's history. Ultimately, the study of ancient pre-human civilizations underscores the importance of being open to the boldest ideas in science. Paying attention to anomalies and questioning established dogmas is what drives knowledge forward. This allows us to continually refine our methods and theories, maintaining a thirst for knowledge and a willingness to embrace new, revolutionary discoveries. Such research not only deepens our understanding of Earth's history, but also fosters a deeper understanding of nature, intelligence, and civilization itself throughout the vast universe. The idea of human uniqueness has deep roots in both science and our cultural code. Historically, this idea gained strength during the Renaissance and the Enlightenment, when scientific methods based on experience and logic began to rapidly develop. As scientific knowledge grew, humans increasingly began to perceive themselves as the center of the universe. This concept was initially supported by the geocentric model of the universe, and then by anthropocentric views, which placed humanity at the very pinnacle of biological and cultural evolution. Our anthropocentrism was fueled by the apparent complexity of human society, our language, and technological advances, which we believed made us completely different from other species. Moreover, humans began to be perceived as a species superior to any other potential civilization, be it extraterrestrial or pre-human. These ideas were based on several key beliefs. The first was that complexity and technological progress were inherent and unique features of the human condition. Our achievements seemed to us evidence of superior intelligence, leading to the belief that we represented a unique pinnacle of evolution. On the other hand, religious or philosophical notions of something special about humans placed us at the center of creation and artificially separated us from the rest of nature. These ideas shaped the belief that other civilizations, even if they existed, would be either completely different or inherently inferior, and their path of development would be incomparable to our own. Moreover, the very lack of clear evidence of advanced, non-human societies only reinforced this sense of exceptionalism. Our limited understanding of ancient history and the fact that we have yet to receive signals from extraterrestrial intelligence created the illusion of our loneliness and uniqueness. We were accustomed to believing that humanity was the only, or at least the first, intelligent species to have appeared on this planet. This belief was reinforced by the enormous difficulties in detecting traces of alien activity across vast cosmic and temporal distances, which led to a preconceived notion of human uniqueness. However, today, advances in astrobiology, archaeology, and the philosophy of science have seriously challenged this view. We have begun to recognize that technologically advanced civilizations may well have existed on Earth long before the emergence of humans. This has forced us to rethink the very concepts of intelligence and progress. We have begun to wonder, are our criteria for judging the presence of civilization too narrow? Perhaps the universe is filled with a multitude of intelligent life forms, each with its own unique characteristics, pursuing its own path of development, completely independent of human standards. This reassessment opens new exciting horizons for a deeper exploration of the scientific and philosophical implications of the existence of civilizations that came before us and were unlike us. The speculation about the existence of such worlds provokes profound reflection and scientific debate, challenging the most common notions about our place in the universe. Imagine that these incredible features indicate not just mastery, but profound symbolism, a connection to the cosmos and the universe. These traits may be evidence of a social organization and technological level that completely overturn our understanding of ancient history. The discovery of such artifacts inevitably raises the question, what if other, far more advanced civilizations existed before us? Their construction methods, the enormous size of their structures, and their incomprehensible purpose may hint at the existence of a collective intelligence, a knowledge base that existed long before the emergence of cultures known to us. It's entirely possible that this knowledge belonged to a single planetary civilization that once flourished and then vanished into oblivion, leaving behind only these silent, mysterious traces. This makes one wonder where exactly these incredible structures were found and how they managed to survive millions of years, especially in places that are virtually inaccessible to study today. Such reflections inevitably lead us to the idea of entire archaeological worlds hidden underground or at the bottom of the oceans. It is there, in the depths, that the remains of these mysterious civilizations may lie, holding the keys to the greatest mysteries of the past. This is where the bold hypothesis of the so-called Silurians, the idea of the existence of precursor civilizations, comes into play. A key role in this theory is played by archaeological finds hidden deep underground and on the ocean floor. After all, it is there that evidence of highly developed societies that predate our known human history by millions of years may be preserved. These sites, buried under tons of silt, hidden in the water, or littered with the debris of bygone eras, present researchers with unique challenges, but also offer incredible opportunities. They offer the chance to uncover an alternative history of life on Earth. The importance of these hidden worlds is difficult to overstate. Like time capsules, they have preserved structures, artifacts, and even environmental samples, remaining virtually untouched by either the destructive forces of nature or modern human activity. This offers us an invaluable opportunity to gain clues about civilizations that may have existed long before the first humans appeared on the planet. Subterranean spaces, whether submerged cities or extensive tunnel networks, can conceal the remains of complex infrastructure. Imagine meticulously designed foundations, incredibly precise tools, or even organic materials, safely entombed beneath centuries-old layers of the planet. These locations, protected from the outside world, are ideal repositories for evidence of technological or cultural breakthroughs that could have been forever wiped from the face of the Earth by rising sea levels or other global catastrophes. Likewise, submerged archaeological sites, entire cities submerged beneath the waves, shipwrecks, or entire underwater landscapes, offer astonishing opportunities to search for traces of civilizations lost to the depths. For example, submerged coastal settlements may contain artifacts and architectural features that shatter established notions about their time of creation, pointing to a much earlier period of intelligent life activity on Earth. However, the very attempt to discover these hidden worlds is a task of colossal difficulty, a true confrontation with the forces of nature, given the scale of our planet. The Earth itself, it seems, does everything to preserve its secrets. Sedimentation processes, the movement of tectonic plates, and inexorable water flows all work against researchers, erasing traces of the past. Often, no clues remain on the surface, rendering traditional excavation methods simply pointless. That's why peering through this veil of time requires entirely new revolutionary methods that combine classical archaeology with future technologies. It is precisely this union of diverse fields of science that holds the key to success. Combining geological and environmental data with advanced scanning techniques allows us to piece together fragments of ancient civilizations hidden from our eyes for centuries, like a mosaic. Understanding the role of underground and underwater features in the ancient civilization hypothesis underscores the importance of using cutting-edge technology today. As we delve deeper into how tools like ground-penetrating radar can revolutionize archaeology, it becomes clear that these innovations hold the key to unlocking the mysteries hidden deep beneath our feet or in the silent darkness of the ocean depths. There, underwater, unique artifacts may be found that could forever change our understanding of our planet's past. Modern technologies such as ground-penetrating radar are literally opening up new horizons in archaeology and historical research. These amazing devices allow us to detect and analyze hidden objects, vastly expanding the capabilities of scientists. They offer gentle methods for studying the Earth's interior, enabling the discovery of entire structures and landscapes that remain completely invisible from the surface. Their unique ability to detect subsurface anomalies without the need for excavation minimizes the risk of damaging potential finds, preserving them in their pristine condition and significantly increasing the chances of great discoveries. Its operating principle resembles a kind of echo sounder for the Earth's interior. The device sends high-frequency radio waves deep into the Earth. When these waves encounter underground objects, voids, or changes in rock layers, they are reflected back. These signals are recorded and converted into detailed images of what lies beneath the surface. Ground-penetrating radar is particularly effective at deciphering complex geological structures or identifying hidden walls, foundations, or artifacts in rugged terrain. Its ability to produce real-time images allows researchers to pinpoint future excavation sites with incredible precision, making the entire process vastly more productive. Another technological breakthrough is LiDAR, or laser scanning. Imagine an aircraft or drone bombarding the Earth's surface with laser pulses, creating highly detailed topographic maps. This technology is indispensable in dense forests, where traditional survey methods are rendered ineffective by the dense vegetation. LiDAR can literally see through the tree canopy, penetrating the dense jungle canopy and revealing hidden archaeological features, ancient city plans, road networks, or earthworks that have remained invisible for millennia. High-resolution LiDAR data allows the creation of digital terrain models, revealing the slightest changes that indicate the activity of ancient civilizations. Both ground-penetrating radar and LiDAR greatly simplify large-scale surveys that would previously have been unthinkable due to the labor-intensive nature of the work. They help identify promising sites, direct excavations precisely to their targets, and reconstruct ancient landscapes with astonishing accuracy. These technologies also make it possible to compare data from different parts of the planet, identifying patterns or anomalies that could indicate the existence of long-forgotten worlds. However, while these tools expand the horizons of science, they also pose new challenges. Interpreting the vast arrays of data they produce requires in-depth knowledge and specialized skills. Distinguishing genuine finds from false alarms requires careful verification and cross-checking. Distinguishing man-made objects from the chaos of natural formations remains an incredibly difficult task. And as technology advances, the question becomes increasingly pressing. How can we verify the authenticity and determine the age of anomalous finds? Verifying the authenticity and accurately dating such artifacts is one of the most challenging puzzles in modern science. This is primarily due to the limitations of existing methods and the unique nature of the finds themselves. One of the main challenges is distinguishing a genuine artifact created by a skilled hand from a skillful forgery, or even more difficult, from the whimsical play of nature itself, which can create objects strikingly similar to man-made ones. Yes, we have powerful tools such as radiocarbon dating, thermoluminescence, and stratigraphic analysis. They are effective, but not omnipotent. These approaches rely on the assumption that certain isotopic characteristics or the geological context of the find have remained unchanged. However, these assumptions can be undermined by environmental influences, external contamination, or processes that occurred after the object was buried. Moreover, unusual artifacts often don't fit into the established picture of the world, which raises skepticism in the scientific community and requires particularly thorough verification. For example, an object made of an unusual material or manufactured using an unknown technology may initially be mistaken for a natural formation or modern debris. Without corroborating data from various sources, such as a clear occurrence in a specific geological layer, consistent results from different dating methods, or the presence of accompanying artifacts, any conclusions remain mere hypotheses. The problem is compounded when finds reach us in fragments, severely damaged or altered by natural forces over millennia. This makes it virtually impossible to understand their original form and purpose. And another pitfall: nature itself can be the greatest deceiver. Some mineral deposits, crystalline structures, or rock formations can precisely mimic man-made objects in shape or texture, which can easily lead to deception. Distinguishing intentional modifications made by an intelligent being from natural geological processes requires a profound understanding of geology, mineralogy, and the dynamics of rock formation. Experts often have to resort to microscopic analysis to find the truth. To peer into the very heart of a stone, scientists analyze its chemical composition, creating a detailed 3D model. On this digital twin, they search for the smallest, barely perceptible traces of tools or imprints of ancient technologies, things never found in natural creations. The complexity of this verification only underscores the importance of a comprehensive approach. Here, at the intersection of sciences, archaeology, geology, and chemistry meet, and modern visualization technologies allow them all to speak the same language to create a unified, comprehensive picture of the origin of a mysterious object. With each new study, the criteria for authenticity become increasingly stringent, enabling us to more confidently separate genuine relics from natural curiosities. A thorough analysis of the environment in which a find was made is becoming absolutely essential to avoid fatal errors in interpretation and to gain a closer understanding of civilizations that may have existed long before us. There's always the possibility that some of these enigmatic finds could be mistaken for natural creations. That's why careful scientific analysis is the ultimate judge, separating genuine artifacts from geological illusions. After all, nature itself is both a master sculptor and a deceiver. Mineral layers, rocks intricately sculpted by wind and water, crystalline lattices, they sometimes take on forms so perfect that they can deceive even the most experienced eye, especially after millennia of erosion and geological transformations. To distinguish between a genuine artifact and a work of nature, it's necessary to understand how they formed, look for clues in the surrounding rock layers, and detect traces of a consistent, purposeful design. One of the key methods is a meticulous examination of the shape and material of suspicious objects. Genuine artifacts almost always bear signs that indicate their man-made origin. These may include tool marks, unnaturally regular geometry, or obvious evidence that the object was intentionally shaped. Such characteristics simply cannot be the result of random natural processes. Imagine perfectly symmetrical or patterned surfaces, smooth edges, or features that clearly indicate the object was part of something larger. All of these scream artificiality. Meanwhile, natural formations most often exhibit chaotic fractal patterns created by mineral crystallization, erosion, or other geological activity. Furthermore, contextual examination of a find plays a crucial role in determining its authenticity. If a suspected artifact is discovered in clearly defined geological layers, alongside other evidence of ancient life, whether tools, pottery fragments, or organic remains, then the likelihood of its authenticity skyrockets. Conversely, a solitary object removed from any context always raises legitimate doubts. To definitively distinguish between natural artifacts and handicrafts, it's necessary to dig even deeper. A geographic and geological assessment of the area can provide crucial clues. Understanding the local mineralogy and topography allows us to determine whether such forms could have arisen naturally. For example, through volcanic activity, sedimentary processes, or mineral deposition. Modern analytical methods also make an invaluable contribution to this investigation. Spectroscopic analysis can accurately determine the composition of a material and identify elements characteristic of human production rather than natural minerals. And technologies such as 3D scanning and electron microscopy make it possible to discern microscopic traces of processing invisible to the human eye. All these methods, combined with the expertise of geologists, archaeologists, and material scientists, create a powerful tool for evaluating potential artifacts. Understanding these subtleties helps us lift the veil of mystery on the past and opens entirely new horizons for future research. Understanding how diverse the traces of ancient cultures can be becomes critically important, especially when we accept the bold hypothesis of the existence of civilizations distinct from our own. This forces us to think more deeply about the diverse historical paths that could have shaped our planet over millions of years. The ability to distinguish natural phenomena from man-made ones not only protects us from drawing false conclusions, but also allows us to focus our attention on truly anomalous finds. These rare clues can unlock long-forgotten chapters in Earth's history. And as we hone our skill in distinguishing natural formations from ancient artifacts, we prepare ourselves for the next, even more exciting stage, the search for undeniable traces of ancient technologies and infrastructure. Finding the remains of ancient civilizations' mechanisms or structures requires a unique perspective, one capable of discerning subtle yet telling technological imprints hidden within the planet's very core. Unlike surface artifacts, which time and the elements may have obliterated or buried for millennia, telltale signs of past engineering often appear as anomalies in Earth's electromagnetic, gravitational, or seismic maps. This data could be the key to unlocking secrets buried deep beneath our feet. If discovered and correctly interpreted, these traces will provide powerful indirect evidence of long-extinct technological activity. One of the most promising areas of exploration is electromagnetic anomalies. Imagine a civilization that engaged in large-scale industrial activity. It would inevitably generate powerful and specific electromagnetic fields. For example, the remains of underground power grids, buried equipment, or communication systems can create localized magnetic disturbances or areas of anomalous electrical conductivity. These anomalies can be detected using geophysical scanners, magnetometers, and electromagnetic induction devices. Such anomalies are typically stable and have clear boundaries, which makes them strikingly different from natural fluctuations caused by ore deposits or other geological processes. Gravitational signatures also open up entirely new horizons for researchers. Massive artificial structures, whether vast underground cities or gigantic machines, can create subtle yet measurable changes in Earth's gravitational field. High-precision gravimetric instruments can detect density anomalies that don't fit into the pattern of known natural formations. For example, an entire complex of equipment or infrastructure buried underground will lead to a localized increase in density. Sharply contrasting with the surrounding geological structures, such anomalies clearly indicate their artificial origin. Seismic data, in turn, opens another window into the world of hidden ancient structures. Artificial structures, especially those constructed from materials atypical for the local geology, can reflect seismic waves in a unique way. When these waves, sent deep into the Earth, encounter the boundary between natural rock and an artificial structure, a tunnel wall, chamber, or foundation, they are reflected, returning with a unique, characteristic signature. Modern seismic imaging technologies are capable of detecting these features at depths and on scales that until recently seemed impossible. This could provide irrefutable evidence of ancient engineering. And here's where things get interesting. When we combine data from all these sources, electromagnetic, gravitational, and seismic, we can see what would be invisible individually. We can discover subtle traces of technologically advanced civilizations of the past. Careful study of these anomalies allows scientists to gather indirect yet compelling evidence. Even if not a single material artifact remains on the surface, such discoveries have the potential to completely upend our understanding of history and our place in the universe. Anomalies found in these data can serve as reliable markers of artificial origin, especially if they contradict all known natural geophysical laws. For example, electromagnetic anomalies can appear as strange, unnatural magnetic fields. Scientists are now encountering persistent electrical signals from the Earth's interior whose origins cannot be explained by known natural processes. These signals may resemble those generated by massive electrical infrastructure, especially if they exhibit regularity, a precise frequency, or coherence that are unlikely to arise naturally. Localized magnetic spikes may indicate the presence of buried energy sources or ancient devices that once powered complex systems. On the other hand, gravity anomalies often indicate an uneven distribution of mass beneath the surface. Amazing things can lurk beneath the Earth's crust, and when a gravity anomaly has clear boundaries and remains stable, it can indicate the presence of artificial voids, structures, or accumulations of materials completely alien to the local geology. Imagine that in some corners of our planet, gravity itself behaves strangely. These gravitational distortions could be the key to solving an incredible mystery. They could point to the existence of gigantic, man-made objects deep within the Earth. We're talking about colossal underground chambers, energy storage facilities, the scale of which is unimaginable, or even long-dead power reactors that, over millions of years of operation, have forever altered the gravitational field around them. But there's another path that leads us to traces of this hypothetical civilization, the tremors of the Earth itself. Seismic data opens another window into the mysterious past. Imagine anomalous seismic activity, inexplicable vibrations, strange resonances, or ordered tremors that don't fit at all with the natural movement of tectonic plates. All of this could be a direct indication of the presence of underground engineering structures. For example, if instruments record rhythmic seismic signals, repeating with mathematical precision, this could indicate the operation of ancient mechanisms, perhaps powered by crystal energy. These anomalies resemble not an earthquake, but rather the hum of pulsating energy sources or the vibrations of gigantic mechanical devices that once hummed within the depths of ancient structures. And unusual seismic reflections, like echoes bouncing off something solid and orderly, may hint at the existence of hidden tunnels, chambers, or multi-level complexes built to store or generate energy. When all this puzzling data comes together, it begins to form a unified, striking picture. A picture that clearly points to the presence of both ancient and possibly still active artificial systems. This evidence forces us to question the origin of these anomalies and pushes us to search for clues that could shed light on the nature of these forgotten energy sources. And this, in turn, raises the central question: what signs, exactly, could reveal the existence of these mysterious energy systems? What could these enigmatic remnants of the technologies that powered long-vanished civilizations be? If ancient energy sources and entire energy systems truly existed, they should have left behind subtle yet distinct traces, forever imprinted in the geological and archaeological record of our planet. Unlike our modern energy infrastructure, which is easily recognizable by standard materials and technologies, these ancient systems may have utilized natural resources in entirely different ways, employing methods that are not immediately obvious. For example, evidence of large-scale geothermal energy use or artificially created thermal anomalies may directly indicate ancient technologies for extracting heat from the Earth's interior. Such signatures may manifest as unusual heat flow patterns or mineral assemblages that could only have formed under conditions that cannot be explained by natural geological processes. Furthermore, altered mineral compositions or strange, unnatural isotopic proportions in certain rocks may be a direct consequence of ancient technological activity associated with the conversion or storage of colossal amounts of energy. Simply put, if ancient civilizations truly harnessed the planet's energy, they would inevitably leave behind fingerprints that will help us understand their technologies and unlock the greatest mysteries of our past. For example, anomalously high concentrations of rare isotopes or unusual electromagnetic properties of rocks may indicate the use of early electromagnetic or even radiation technologies. In some cases, the discovery of gigantic, precisely aligned stone structures may serve as evidence of energy collection or transmission systems, especially if their placement perfectly aligns with the positions of celestial bodies or the Earth's magnetic field lines. Furthermore, the discovery of artifacts made of unknown alloys or synthetic materials, impossible to create using known ancient technologies, may indicate incredibly advanced metallurgical processes. These materials could have served as components for the production of highly complex devices necessary for the operation of such systems. Just imagine, energy devices such as batteries or power regulators may have existed long before the emergence of the first known civilizations. If the authenticity of even one such artifact is proven, it will completely revolutionize our understanding of ancient technological development. In some cases, the remnants of electromagnetic or acoustic energy systems may have left faint but still detectable traces in the Earth's crust or the planet's magnetic field. For example, localized magnetic storms or persistent electromagnetic interference may be linked to buried ancient energy infrastructure. Over thousands or millions of years, these signals may, of course, have weakened or been obscured by natural processes. However, thanks to our modern ultra-sensitive technologies, their ghostly traces can still be detected and deciphered. All these potential clues provide us with incredible hints that ancient civilizations could harness energy on a scale and with a level of sophistication that only yesterday seemed pure science fiction. Discovering such signatures could open the way to a profound understanding of our planet's hidden technological legacy and pave new avenues for discovering ancient innovations long buried beneath the layers of time. But what if it's not just energy, but information as well? Remnants of ancient communication systems or data archives, if they ever existed, could be found today through the analysis of subtle geological and chemical markers. While familiar archaeological finds like pottery or metal tools provide obvious evidence of past technologies, traces of advanced information storage methods, especially those using complex materials, can be much more subtle. Finding them would require entirely different, specialized methods. Consider this. If an ancient civilization used storage media based on nanotechnology or other exotic materials to encode data, they could have left behind unique mineralogical or chemical anomalies in the Earth's geological layers. One way to detect these is by analyzing isotopic or mineral anomalies associated with the production of such materials. Some nanomaterials, such as engineered nanoparticles or multilayer composites, may contain elements or isotopic ratios that differ dramatically from naturally occurring values. Over time, these materials could have altered the local geochemistry, creating a unique chemical fingerprint detectable using high-precision spectrometry. Similarly, the presence of synthetic polymers or complex carbon nanostructures, such as graphene sheets, can leave their own unique signatures in sedimentary rocks, especially if they have survived for many millennia. Modern materials often possess unique physical properties that can actively influence their surrounding geological environment. For example, some nanostructures can accelerate mineral formation processes or act as crystallization centers, resulting in the appearance of microscopic defects in the rock, visible only under a powerful electron microscope. These microstructural features can serve as indirect evidence that high-tech materials once existed there and interacted with their environment. Ancient traces of technological activity, such as the use of electromagnetic or acoustic communication methods, could be preserved in mineral matrices as subtle electromagnetic or vibrational anomalies. Finding such traces is incredibly challenging due to potential degradation, contamination, and signal weakness. However, the constant advancement of our analytical methods opens up new exciting possibilities for searching for evidence of ancient communication systems or data storage hidden deep within the planet's geological record. As our knowledge expands, the prospect of discovering traces of highly advanced, possibly nanotechnological civilizations ceases to be science fiction and becomes an increasingly realistic scientific goal. Nanotechnology and other advanced materials possess unique physical and chemical properties that allow them to persist in geological deposits for vast periods of time. Unlike traditional materials, these innovative creations often contain elements or have molecular structures that are either extremely rare in nature on Earth or require unique artificial conditions to create. When such materials are produced or used in large quantities, they can leave subtle but detectable traces that can be found in sedimentary rocks, mineral formations, or even ice cores, recovered from depths of many kilometers. One key aspect is that nanomaterials often have unique isotopic ratios or crystal structures that differ dramatically from their natural counterparts. For example, artificial nanoparticles created with specific isotopic compositions or coated with special protective shells can resist natural degradation and persist in rocks for millennia. Over time, these particles can become embedded in sedimentary layers, mineral veins, or even fossils, forming a unique geological fingerprint that provides irrefutable evidence of technological activity in the distant past. Similarly, modern materials, such as ultra-high-strength composites or exotic alloys, can undergo mineralization over time, forming unique mineral assemblages that are easily distinguished from natural ones through geochemical analysis. Success in finding such traces directly depends on our ability to detect anomalies in Earth's geological history. Imagine the most complex detective problem in history. We're looking for clues not at crime scenes, but in the very fabric of the planet, in the geological record millions, perhaps even hundreds of millions of years old. We're looking for anomalous concentrations of chemical elements, strange isotopic shifts, or unique mineral structures, anything that can't be explained by nature. These traces of the past can be so subtle and elusive that detecting them requires the most advanced analytical tools available to humanity. Mass spectrometers capable of weighing atoms, powerful electron microscopes, and even synchrotron imaging that can penetrate matter. The key challenge facing researchers is distinguishing potential traces of an ancient, time-lost civilization from the pollution left behind by our own industrial era. It's like trying to hear a whisper from the depths of time amid the deafening roar of modernity. To accomplish this, we must thoroughly study the natural chemical background of our planet, understanding all its fluctuations and variations. And as our methods become increasingly precise, so does the hope of finding these ghostly signals in pristine layers of geological archives. The ultimate goal of this grand search is to identify persistent, repeating anomalies that could provide irrefutable evidence of the existence of high-tech materials created by someone long before us. And this search inevitably leads us to the question, can our eyes in the sky, modern satellites, help us in this endeavor? Satellite imagery and remote sensing technologies have revolutionized the search for traces of ancient or even extraterrestrial technological activity. They offer us a view of our planet from a height and with a scope undreamed of by terrestrial archaeology. These orbital sentinels allow scientists to peer into the most hidden and inaccessible corners of the Earth. The impenetrable Amazon jungle, the bottomless ocean canyons, and the sun-baked deserts, where any anomalies could lie hidden for centuries, invisible to the human eye. High-quality multispectral and hyperspectral cameras see the world differently than we do. They capture hundreds of shades and parts of the spectrum invisible to us, allowing them to discern the subtlest nuances in the mineral composition of soil and rocks. These nuances can reveal artificial structures or traces of large-scale landscape changes. Thermal imaging, in turn, searches for residual heat signatures, the ghostly echoes of long-extinguished energy sources that may indicate technological activity millennia ago. These technologies are capable of detecting traces left by both modern and ancient energy systems, opening up incredible prospects for discovering the remains of ancient technologies. Moreover, our orbital instruments help identify strange geometric anomalies that don't fit into natural geological landscapes. Nature favors chaos, smooth lines, and fractals. When perfectly straight lines, perfect rectangles, or concentric circles appear in images, they always raise questions and are seen as a potential sign of intelligent intervention. By analyzing these strange patterns in a broad spatial context, researchers can identify the most promising sites for ground expeditions. This prevents the waste of precious resources and dramatically reduces the likelihood of following a false trail. Furthermore, spectral analysis helps identify materials that are extremely rare in nature but directly related to high technology, such as unusual metal alloys or synthetic polymers. However, despite the power of satellite technology, its effectiveness depends entirely on our ability to correctly interpret the data it receives. Changes in the planet's geology, wind and water erosion, and volcanic activity, all these natural forces can create landscapes on the surface that may appear artificial from above, greatly complicating the search process. Camera resolution, although constantly improving, may still be insufficient to discern the fine details necessary for definitive and irrefutable conclusions. Finally, the colossal volume of information transmitted daily by satellites to Earth requires the development of sophisticated algorithms and artificial intelligence systems capable of sifting through these terabytes of data in search of genuine anomalies amidst the endless stream of information noise. With each new development in remote sensing technology, we face increasingly complex challenges in distinguishing natural mineral formations from possible traces of ancient technology. This dilemma remains a focus of attention and once again demonstrates that success requires a comprehensive approach, combining data from multiple satellites, cross-validation on the ground, and engaging experts from a wide range of scientific fields to avoid catastrophic misinterpretations. Understanding these subtleties is absolutely essential to continuing the search for evidence of civilizations that preceded our own, especially when nature itself acts as the great mystifier, creating objects that are strikingly similar to man-made structures. One of the most serious obstacles in this search is the ability to distinguish potential techno-artifacts from complex natural mineral formations. Numerous geological processes can create structures that, at first glance, appear to be sculpted by an intelligent hand. This turns the task into a true art, akin to trying to distinguish a sculpture by a brilliant master from a rock shaped by millions of years of wind and water. For example, geological formations such as banded iron formations, stromatolites, or certain mineral veins can have regular shapes and layered patterns, eerily reminiscent of the remains of tools or fragments of equipment. These structures formed over millions of years through the slow deposition of minerals, sedimentation, or even the activity of ancient microorganisms. They can possess striking regularity, symmetry, or unusual chemical composition, which can easily mislead and lead one to believe they are artificial objects. The main difficulty is that natural mineral formations are subject to endless changes under the influence of the environment. This gives rise to an incredible diversity of forms and textures, many of which can be mistaken for man-made. This variability of nature makes it difficult to develop clear and universal criteria that would allow us to distinguish natural structures from artificial ones with absolute certainty. Moreover, many mineral characteristics, such as unique isotopic ratios or chemical composition, can exactly match those we expect to find in technologically processed materials. This is especially plausible if we imagine that an ancient civilization could have used minerals with rare properties or employed processing methods unknown to us. The situation is further exacerbated by the fact that natural processes sometimes create completely anomalous structures, such as giant crystalline caves or spherical mineral nodules, which can easily be mistaken for evidence of past technological activity. Another serious barrier is the limited resolution and penetration depth of our current technologies. Remote sensing methods, whether satellite imagery, ground-penetrating radar, or spectroscopic analysis, are not always accurate and sensitive enough to detect subtle artificial changes buried beneath layers of rock in complex geological conditions. To distinguish a natural pattern from an artificial one, it's necessary to understand the entire formation history of a given landscape. However, this information is often either incomplete or extremely confusing. As a result, we face a fundamental problem of ambiguity. Features indicating natural and artificial origins can be virtually identical, and our detection methods still have their limitations. Solving these conundrums requires not only the development of more sophisticated analytical tools, but also a profound understanding of geological processes. Only this will help us develop reliable criteria for identifying true technological markers in a natural mineral landscape. Looking to the future, it's safe to say that technological advances will radically transform our capabilities in this field. Scientific advances are opening up truly fantastic horizons for detecting ancient technosignatures, allowing us to learn more about the possible existence of civilizations that predate humanity. One of the most promising areas is the development of more sensitive and versatile remote sensing instruments. Imagine next-generation satellites capable of detecting the slightest anomalies on the Earth's surface that could indicate past technological activity, unexplained geophysical changes, or even entire structures buried beneath layers of sedimentary rock. High-precision spectroscopy, enhanced by the power of self-learning algorithms, will be able to process enormous data sets to detect anomalous phenomena with incredible accuracy. This opens a new era for researchers and allows us to gain a deeper understanding of our own planet and its hidden history. Mineral compositions and unusual energy signatures that cannot be explained by natural causes are already attracting enormous interest from scientists. Modern advances in geophysical research, ground-penetrating radar, seismic tomography, and magnetic resonance imaging open new perspectives in studying the Earth's interior, allowing us to peer deep without destructive excavations. These tools are capable of uncovering hidden artifacts and entire infrastructure structures that may have been either deliberately concealed or simply lost to the merciless passage of time. As these methods become more accurate and accessible, their use will expand beyond localized searches and potentially lead to systematic global scanning of the planet for signs of ancient engineering marvels. Finally, another crucial aspect is the development of dating and isotopic analysis methods, which will allow us not only to find strange objects, but also to accurately determine their age, linking them to specific eras in Earth's history. Modern science is opening up entirely new horizons in the study of the deep past. Imagine having tools in our hands that can peer into the most hidden corners of Earth's history. Radiometric methods essentially allow us to date both ancient fossils and the rocks themselves with incredible, previously unheard of accuracy. This gives us the ability to construct a clear timeline onto which we can map any strange and anomalous events. But what if we combine this data with geochemical analysis? Then we have a powerful tool for searching for traces of technological activity. We can detect periods when unexplained bursts of energy occurred in the atmosphere or geological deposits, or processed materials appeared, even if not a single stone remains of the structures and machinery themselves. It's like searching for the ghost of a long-burnt fire by barely noticeable chemical changes in the soil. But that's not all. Entirely new forces are bursting into our arsenal as ancient researchers. Artificial intelligence and the analysis of colossal amounts of data. Just imagine, we can train powerful computer algorithms to distinguish natural processes from the traces of artificial intervention. These digital detectives can sift through mountains of information from diverse fields, geology, chemistry, physics, and piece together disparate, subtle signals into a coherent picture. With each new technological breakthrough, our ability to peer into Earth's past and find traces of long-vanished civilizations there becomes ever more astonishing. We're not just increasing our chances of spotting what was previously hidden. We're beginning to better understand how the activities of intelligent beings can leave their mark on the planet's geological record. And all this progress brings us to one fundamental question that has been troubling us for generations. Are we humans something absolutely unique in the multi-billion-year history of our planet? Or is our civilization merely the latest chapter in a much older and longer saga of intelligent life on Earth? There are many compelling theories that seriously consider the possibility of civilizations that predate humanity. These ideas challenge our long-held belief that humanity emerged very recently and was the only intelligent species on this planet. These hypotheses emerge from the intersection of multiple disciplines, combining data from geology, archaeology, astrophysics, and evolutionary biology. Together, they attempt to paint plausible scenarios for the existence of ancient and perhaps even extraterrestrial intelligent life. One of the most intriguing ideas is known as the Silurian Hypothesis. It suggests that a highly advanced technological civilization may have emerged on Earth millions, even tens of millions of years ago, but left behind only tiny, barely noticeable, and very ambiguous traces in the planet's rock record. This theory takes into account the vast time scales of geological processes. It explains how a society, perhaps superior to our own, could have vanished almost without a trace, leaving behind only strange chemical anomalies, unusual mineral deposits, or fossilized objects that are virtually indistinguishable today from natural creations. This hypothesis forces us to completely rethink our search methods and learn to look for subtle, hidden, and disguised evidence. Another, equally compelling model paints a picture of a cascade of successive civilizations. Imagine Earth's history not as a single, straight line, but as an endless cycle. Over millions of years, the planet could have seen countless rises and falls of great civilizations, each reaching incredible technological heights and then succumbing to catastrophe or slow decline. According to this view, civilizations could have existed in entirely different geological eras, their traces either completely obliterated by time or buried under kilometers of new sediment. Such models often rely on the idea of planetary resilience, the Earth's own ability to heal its own scars. Powerful forces such as tectonic plate movements, volcanic eruptions, and global climate change could erase or disperse virtually any evidence of entire empires, making their discovery nearly impossible. Some theories extend beyond our planet entirely. They suggest that intelligent civilizations may have existed on other planets or their moons long before the first humans appeared on Earth. These scenarios are based on astrophysical data, which tells us that habitable conditions existed in our Milky Way galaxy for billions of years. This opens up virtually limitless possibilities for the independent development of life, and consequently, technologies capable of reaching levels unimaginable today. Such hypotheses dramatically expand the time frame in which we search for intelligence. They force us to consider the complex interaction of planetary, biological, and technological forces on the scale of not just a planet, but the entire cosmos. Researchers are faced with new, incredibly complex challenges, requiring the development of even more sophisticated detection methods and the expansion of our search into the most unexpected areas. But a key question arises: how exactly do these grandiose models take into account all factors, planetary, biological, and technological? They don't simply consider them separately, but rather weave them into a single, complex system. These models represent intricate structures that reflect the subtle interactions between the environment, life itself, and the products of that life, advanced civilizations. At the core of everything are key parameters of the planet itself. How stable is its climate, its geological activity, and the composition of its atmosphere? These fundamental characteristics determine whether a planet is capable of supporting life over geologically significant timescales. For example, the planet's mass, the stability of its orbit, and, crucially, the strength of its magnetic field, which protects the surface from harmful cosmic radiation, are all taken into account. All these factors together shape the conditions on the surface and determine whether a world can become a cradle for long-term biological evolution, culminating in the emergence of intelligence. Next, the models consider biological aspects. How productive is the biosphere? What is its diversity and, most importantly, its resilience to shocks? How these factors influence the evolution and development of civilizations in a wide range of conditions is explored. How does life adapt to extreme environments? Will any traces of it survive global geological or even technological catastrophes? But that's not all. Biological factors themselves influence the planet through so-called biogeochemical cycles. Life can alter the composition of the atmosphere and climate, creating feedback loops that can either promote the development of even more complex life forms or, conversely, destroy them. Taking this aspect into account allows the models to assess the likelihood that life and intelligence could have arisen on a single planet not just once, but several times. And finally, technological factors. These help estimate how long a civilization can survive and how easily it will be detected. Everything depends on its energy consumption, environmental impact, and level of technological advancement. Models consider scenarios in which civilizations can either thrive or decline. Depending on the reliability of their infrastructure, they calculate the chances that their activities will leave long-lasting traces in the atmosphere or on the planet's surface. How do technological advances affect the environment? Do they create scars that will be visible millions of years from now? Models that integrate all three aspects, planetary, biological, and technological, give us a unique opportunity to gain a deeper understanding of how various forces influence the evolution of life and intelligence in the vast expanses of space. They don't simply show under what conditions civilizations might arise. They demonstrate how the environment and biological stability influence their development, survival, or ultimately, their inevitable extinction. This integrated approach highlights how interconnected everything in this world is and opens entirely new horizons for studying the potential diversity and longevity of extraterrestrial civilizations. All of these hypotheses have enormous implications for our understanding of planetary habitability and the evolution of life. They completely change our understanding of how diverse and resilient life can be in the universe. When we begin to seriously consider scenarios in which advanced civilizations could have emerged, flourished, and disappeared long before us, we come to a startling conclusion. Habitability is not some constant fixed characteristic of a planet. It is a complex, ever-changing dynamic process influenced by countless factors. These models suggest that several distinct eras of life could have succeeded each other on a single planet. Each had its own unique conditions, its own biosphere, and each could have ended as a result of catastrophic events. Thus, habitability appears to us not as something static, but as a pulsating process, with windows of opportunity that open and close on the scale of geological time. One of the key conclusions we can draw is that planetary environments may be far more resilient and capable of supporting life than previously thought, especially if life can adapt to the most extreme conditions or recover from global catastrophes. The very hypothesis of the existence of ancient, long-vanished civilizations suggests that planets can support complex life forms for vast periods of time, even if their conditions today seem completely unsuitable. This opens up new, exciting opportunities for searching for traces of past life and encourages us to further research, developing new methods that will allow us to find biological remains or technological artifacts in the most ancient geological layers of Earth and other worlds. We must question the very idea that evolution is a straight and predictable path. Let's imagine the history of life on Earth not as a smooth road leading to the summit, but as a series of random, often violent events. The fate of entire eras was decided not by gradual changes, but by the blind will of the cosmos. The impact of a giant asteroid, a sudden climate change, or the eruption of a supervolcano capable of plunging the world into darkness for millennia. These hypotheses paint a picture in which entire ecosystems, entire dynasties of living beings, could flourish rapidly in favorable conditions, achieve incredible power, and then vanish just as quickly due to a single catastrophe. What remained in their wake? Sometimes only a handful of fossilized bones buried under layers of ash, and sometimes only a ringing silence in the geological record. These ideas compel us to understand that survival on the planet depends not only on initial conditions, but also on the ability to withstand cosmic impacts. These concepts deepen our understanding of the complex connections between the environment and biological evolution. They suggest that our planet may have harbored life in the most unimaginable forms at various times. Some of these ancient worlds have vanished forever, erased by time, while others gave rise to new thriving species. As we explore these new horizons in the past, we must abandon the idea that the evolutionary path that led to the emergence of humanity was the only possible or unique one. This broader understanding of the history of life inspires paleontologists to search even more thoroughly. We are beginning to realize that the longevity of any dominant group of animals and their evolutionary paths are completely unpredictable, inextricably linked to the turbulent and violent history of their home planet. Models that explore these ancient, lost worlds help us better understand the great mysteries of paleontology. For example, the paradox that, despite hundreds of millions of years for life to evolve, we have yet to find traces of many hypothetical creatures that should have existed. These models suggest that truly successful and long-lived animal dynasties may have been incredibly rare or doomed to rapid extinction, which explains these alarming gaps in the fossil record. One of the key elements considered in these models is the concept of evolutionary longevity. It questions how long a dominant species can survive. This problem applies to Mesozoic dinosaurs, as well as to any other creatures that ever ruled the earth. They could have faced complete collapse or regression due to internal factors, depleted food resources, global epidemics, or climate change, to which their bodies were not adapted. If entire ecosystems were prone to self-destruction or gradual decline, even before they had time to leave behind massive fossil layers, this could explain the rarity of such finds. This approach forces us to rethink gaps in the fossil record, viewing them not as evidence of emptiness, but as a consequence of the transience and fragility of life itself. These models often employ the concept of great filters, nearly insurmountable obstacles that prevent living organisms from achieving long-term prosperity. Catastrophic events, whether natural disasters or biological crises, play a central role in this idea. Imagine supervolcanic eruptions blanketing entire continents in ash, asteroid impact causing planet-wide firestorms, or abrupt climate shifts turning lush jungles into icy deserts. All of these could periodically interrupt the evolutionary chain. On the scale of geological time, entire animal dynasties could experience ups and downs, significantly reducing their chances of being discovered millions of years later. This endless cycle of rise and fall implies that many species could have existed for only a short period of time, perhaps just a few million years. This makes their discovery in the rock record virtually impossible. Some theories suggest that certain species may have intentionally or accidentally occupied ecological niches unfavorable for the preservation of their remains. For example, inhabiting high-altitude forests, where acidic soil quickly dissolves bones. This further exacerbates the apparent silence in the geological record. A combination of natural disasters and conditions unfavorable for fossilization could have significantly reduced the likelihood of us ever learning about these lost worlds. These models form a complex and dramatic narrative in which the fragility of life in the face of catastrophic events is the primary explanation for its extinction. The possibility of these worlds raises questions about the factors that influence the rise and fall of species, and prompts us to explore the key role of disruptive events in the history of life, both on Earth and perhaps beyond. Numerous theoretical models analyzing the rise and fall of ancient ecosystems emphasize catastrophic events, which often serve as turning points, dramatically altering evolutionary paths. In these models, natural disasters such as massive volcanic eruptions, asteroid impacts, or abrupt climate changes can act both as destructive forces and as catalysts for the emergence of something new. When the ancient world experiences such a catastrophe, its immediate consequences often include widespread destruction, mass mortality, and the collapse of established food chains. These events can lead to the loss of unique species, threatening the continued existence of entire ecosystems. Catastrophic events can plunge the world into chaos and set evolution back millions of years. However, beyond their destructive impact, they can also act as a kind of reset button, creating conditions for the emergence of new life forms. For example, a powerful volcanic eruption can destroy an existing forest, but leave behind fertile volcanic soils that can give rise to a new, entirely different world. Climate change, following disasters, can alter the distribution of resources, forcing survivors to adapt or migrate. This sometimes leads to the emergence of new species and their expansion into the vacated territories. The timing and frequency of such catastrophic events play a crucial role in understanding the patterns of the rise and fall of ancient worlds. Frequent and severe catastrophes can disrupt long-term stability, leading to cycles of growth and collapse. Meanwhile, rare but highly destructive events, such as the Chicxulub asteroid impact, can explain the sudden disappearance of entire dynasties, especially when combined with other factors such as resource depletion or the emergence of more successful competitors. These models also emphasize that the remains of past eras are often fragmented or obscured by subsequent geological processes. Over millions of years, sedimentation, erosion, and plate tectonic movement could have destroyed or obscured the traces of entire worlds, complicating paleontological research. Thus, the interplay between natural disasters and fossil preservation becomes key to understanding why some eras leave behind only minor traces. This emphasis on the destructive power of natural phenomena raises an intriguing question. Could these models also explain the puzzling lack of convincing evidence for some hypothetical ancient creatures? One of the main mysteries these models attempt to solve is the lack of convincing evidence for the existence of some advanced life forms before the age of dinosaurs. Several hypotheses exist that such creatures may have existed, but their traces have proven minimal or so ambiguous as to make their detection and identification difficult. For example, some theories suggest that ancient creatures could have created complex and resilient structures, such as deep underground burrows or underwater reef colonies, which today are virtually indistinguishable from natural geological formations. Furthermore, these communities could have engaged in rapid, cyclical processes of destruction and restoration, effectively erasing their archaeological traces over geological timescales. Another explanation centers on the idea of natural or biological catastrophes that periodically reset the planet's surface. Such events could include massive volcanic eruptions, meteorite impacts, or global warming, which could obscure or destroy previous traces of life. These catastrophic events could make the discovery of remnants of past worlds virtually impossible. Conditions similar to pressing the reset button could arise on the planet, making the preservation of definitive artifacts or fossils unlikely. Theories suggest that pre-dinosaur ecosystems may have been temporary, interrupted by environmental catastrophes, preventing their legacy from being preserved or detectable today. Some hypotheses include the idea that early organisms may have employed a form of bioengineering, methods of environmental modification that leave subtle, barely noticeable traces in the geological record. For example, significant changes in the chemical composition of sedimentary rocks or subtle isotopic anomalies could have been misinterpreted or overlooked amid the diversity and complexity of the Earth's strata. These subtle changes may have been overlooked by natural geological processes, contributing to their apparent silence over entire eons. But despite these exciting proposals, testing such theories faces significant challenges. The main challenge is finding that irrefutable evidence. Attempts to find evidence that would confirm the existence of civilizations lost in the mists of time face a monumental challenge. The fact is that even the most advanced technologies we have today have their limits, as if we were trying to see something important through a glass, darkly. Imagine the geological record of our planet, not a flawless archive, but rather a book whose pages have been torn, washed away by water, and scorched by fire. Time mercilessly erases traces, erosion wears away mountains, tectonic plates crush and submerge entire continents, and chemical processes transform everything beyond recognition. Under such conditions, searching for the legacy of ancient civilizations becomes a task comparable to searching for a single grain of sand on a boundless beach. When there are no direct, indisputable artifacts, any indirect evidence raises a storm of doubt. A perfectly reasonable fear arises. Are we mistaking a bizarre play of nature for the work of intelligent hands? Where is the guarantee that an unusual geological formation is not just a rock, but the ruins of an ancient city? Reconciling such bold hypotheses with rigorous scientific facts requires not only breakthrough technologies, but also a willingness to think beyond the conventional. It's a delicate balance between flights of fancy and cold scientific calculation. Testing any model that allows for the existence of pre-human or even non-human civilizations runs into a wall of fundamental scientific and philosophical obstacles. Chief among these is the almost complete lack of direct material evidence. Consider the work of a classical archaeologist. They have potsherds, tools, and bones that can be placed under a microscope, analyzed for composition, and accurately dated using radiocarbon dating. But when it comes to hypothetical traces of technologically advanced predecessors, we enter a realm of shadows. These supposed traces are either impossible to find or extremely difficult to distinguish from natural geological formations. For example, a structure that might be considered artificial could just as easily be the result of volcanic activity or erosion. This greatly complicates any attempt to reach a definitive conclusion. From a scientific perspective, such research requires the combined efforts of specialists from completely different fields. Imagine this scientific symposium. Geologists, climatologists, archaeologists, and even astrophysicists working together to separate the wheat from the chaff, anomalous signals from the natural background. They often have to rely on subtle clues, strange isotope ratios in rocks, hidden microscopic structures, or unusual layers in sedimentary deposits. However, the line between a real signal and our imagination remains unclear. These theories still wander in a fog of hypotheses, and the risk of wishful thinking is high. Moreover, a veritable abyss of time yawns before us. We're not talking thousands, but hundreds of thousands, perhaps even millions of years. Existing dating methods are simply incapable of working with such precision over such vast time spans. Philosophically, the very idea of anyone existing before us deals a crushing blow to our notion of humanity's uniqueness and the linear path of progress. This forces us to ask, what do we even consider evidence? Are our scientific models flexible enough to accommodate such a radically different picture of the past? The possibility that all evidence has been destroyed by nature, hidden from our sight, or simply unrecognized forces us to reconsider the very boundaries of our knowledge. Moreover, our deeply ingrained bias, our anthropocentrism, our tendency to regard humans as the pinnacle of creation may become a veritable veil before our eyes, preventing us from looking at the facts objectively. Furthermore, such hypotheses teeter on the brink of scientific validity. After all, for a theory to be considered scientific, it must be not only provable, but also falsifiable. And how can one refute something for which evidence is sparse, vague, and uncertain? All these problems only highlight the rigor of methods and the openness of scientific debate required when evaluating such extraordinary claims. Looking to the future, we understand that upcoming discoveries could become both the foundation for these theories and their tombstone. Each new discovery has the potential to either confirm or completely refute these bold assumptions. We will either find something that will strengthen the idea of the existence of advanced civilizations long before us, or we will completely bury it. New technologies are already opening up incredible prospects. Deep-sea vehicles, high-resolution satellite imagery, and ultra-precise dating methods are all our new eyes and ears in the search for evidence that could revolutionize our understanding of Earth's history. Just imagine, using high-precision sonar, we can map the seafloor and discover previously completely inaccessible submerged cities. These underwater ruins may contain the remains of ancient structures or artifacts of civilizations that existed long before those we know. Advanced dating methods, in turn, can reveal anomalies in geological layers, whether traces of unseen materials or biological remains indicating a sudden surge of cultural or technological activity. Such discoveries would provide compelling support for the hypothesis of precursor civilizations. However, these same technologies could also work in reverse. They could become a tool for definitive disproof if, despite all our efforts and the most powerful instruments, we still find nothing. That would also be a result. The complete absence of artifacts, structures, or biological markers would only strengthen the belief that human civilization is unique in its complexity and the time of its emergence. Any new discoveries will require the most careful analysis. They could point to natural processes, erosion, sedimentation, or tectonic activity that could have simply erased or buried all ancient evidence. This gives skeptics the right to argue that the lack of evidence is a consequence of the planet's turbulent geological history, not the absence of ancient civilizations. Future discoveries will further advance our understanding of the dynamic nature of Earth's environmental history. For example, abrupt changes in atmospheric composition or the appearance of strange sedimentary rocks could be linked to global catastrophes, greatly complicating the interpretation of any findings. These cataclysms could either conceal traces of former civilizations by destroying and distorting their remains, or, conversely, preserve them in unique conditions, making them accessible to us millions of years later. Future research will continue to test our current scientific models. They will either provide irrefutable evidence or provide compelling reasons to abandon these hypotheses forever. Each new discovery will deepen our understanding of the planet's complex history, highlighting the importance of combining technological breakthroughs with an interdisciplinary approach in exploring the possibility of ancient, pre-human worlds. Climate change and global environmental disturbances play a decisive role in how we view archaeological and geological archives. These processes shape the very history of humanity and perhaps even other, more ancient civilizations. And they can act in two ways, as the greatest preservers and as merciless destroyers. On the one hand, certain environmental conditions create ideal time capsules. Imagine a rapid flood burying an entire settlement under a thick layer of silt, or the formation of an anoxic environment, as in peat bogs or flooded caves. Burial in ice or under a layer of volcanic ash can protect any artifacts, buildings, and even organic matter from decay. A striking example of this is Otzi, the Iceman, discovered in the Alps. His remarkable preservation demonstrates how a cold and stable environment can preserve organic remains for millennia. Similarly, volcanic ash can cover entire cities, giving us a snapshot of ancient life, frozen in time. It seems as if nature itself carefully guards its deepest secrets. More often, however, abrupt environmental changes act like a giant eraser, wiping away traces of ancient civilizations from the face of the earth. Consider the ice ages, when monstrous glaciers, kilometers thick, covered vast territories. They pulverized landscapes, destroyed artifacts, and fluctuating sea levels inundated coastal settlements. The movement of these ice sheets could erase any superficial evidence, leaving behind only barely noticeable geological scars. Volcanic eruptions, which sometimes preserve history in ash, in other cases devastate entire regions, burying archaeological sites under impenetrable lava flows. And global changes in the oceans, when sea levels rise and fall, radically reshape coastlines, inundating what was once dry land or exposing what was hidden underwater. This dynamic of nature has two sides. On the one hand, it can act as a natural repository, preserving echoes of the past for us deep within the planet's depths. On the other, it can erase these traces completely, leaving only ghostly hints of civilizations that once existed. Natural forces can be both careful guardians of ancient relics for millennia and merciless executioners, destroying any trace of history through erosion, sedimentation, and other processes. Understanding these global phenomena is key to the correct interpretation of archaeological and geological data. They influence not only what has survived the centuries, but also how we today discover and study the legacy of ancient civilizations. This complex interplay opens entirely new horizons for studying how natural forces influence the preservation or irrevocable loss of evidence of the past. It forces us to rethink everything we know about the impact of ice ages, volcanic activity, and ocean changes on our understanding of history. Our planet holds a turbulent, brutal history. Let's travel back millions of years to see Earth as it was then, a world constantly changing under the influence of colossal forces, ice ages, ferocious volcanic activity, and the merciless whims of the world's oceans have left deep scars on the planet's face. These scars, imprinted in the geological record, today pose a real puzzle for paleontologists who are trying to find evidence of ancient life forms that flourished long before the advent of humans. Imagine that throughout its long history, Earth has been the arena for countless global events. These forces of nature acted like a two-faced deity. On the one hand, they created, and on the other, they brought total destruction. As a result of these transformations, geological strata have become a complex pie, with some layers reliably concealing the secrets of the past, while others mercilessly erase any hint that life once teemed here. During the Great Glaciations, vast territories were buried beneath kilometers of ice. These glaciers were a force to be reckoned with, capable of both preserving and destroying everything in their path. As the ice sheets slowly but inexorably advanced, they literally engulfed entire landscapes, concealing the remains of ancient creatures beneath their icy shroud. However, when the climate warmed and the glaciers began to retreat, chaos ensued. Meltwater caused massive erosion, displacing tons of rock and scattering fossil evidence over vast areas. The incredible mass and movement of the ice crushed and deformed geological layers, distorting the original context of ancient ecosystems and making attempts to reconstruct the chronology of events a near impossible task. In the same regions that escaped the ice captivity, other dramas unfolded. Falling sea levels, caused by the freezing of water in glaciers, exposed gigantic land bridges like the one connecting Asia and America. This facilitated great migrations of ancient animals, but at the same time, it radically altered coastal landscapes, influencing which fossils would be preserved for future generations and which would be lost forever. Volcanic activity is another key player in this grand drama of Earth's history. Volcanic eruptions have been both a boon to science and a death knell for entire eras. Their activity leaves behind indelible traces that simultaneously aid and hinder researchers. Powerful eruptions spew millions of tons of ash into the atmosphere, which then settles, covering vast areas with a dense, suffocating blanket. Sometimes, this ash could instantly bury entire ecosystems, including plants and animals. Such sudden burial can preserve organic remains in minute detail, creating a kind of natural time machine. However, subsequent eruptions or tectonic shifts could just as easily destroy or displace these precious deposits. The volcanic landscape is constantly changing under the onslaught of molten lava flows and new layers of ash, which greatly complicates the analysis of the layers and distorts the picture of the past. Ocean changes, such as constant fluctuations in sea level and the movement of tectonic plates, also had a profound impact on the preservation of paleontological records. As sea levels rose, coastal plains sank beneath the waves, taking with them traces of ancient life that once thrived at the water's edge. Meanwhile, as sea levels fell, vast tracts of continental shelf were exposed, revealing submerged worlds that could hold pristine evidence of the past. Tectonic processes, such as the uplift and subsidence of the Earth's crust, can shift entire continents, disrupting the integrity of geological layers. Older sediments can become buried many kilometers beneath newer ones, or conversely, suddenly rise from the sea depths to become mountain peaks. These global processes create a dynamic and often incredibly turbulent geological record. They can both preserve and destroy any evidence of ancient life, making the search for fossils difficult, if not downright hopeless. Understanding these natural forces is essential for correctly interpreting the signals the planet sends us from its distant past. Let's ask ourselves, could global environmental catastrophes have caused the sudden and complete disappearance of entire prehistoric worlds? Such catastrophes have long been considered key factors capable of triggering abrupt crises in the biosphere, and their role in the disappearance of ancient ecosystems deserves the closest attention. Unlike gradual decline caused by slow changes, abrupt environmental shocks, such as monstrous supervolcanic eruptions, giant asteroid impacts, or rapid climate shifts, can lead to lightning-fast destabilization. They leave species no time to adapt, dooming them to extinction. The Earth's geological record contains evidence that similar events have occurred repeatedly, and each time, their consequences were catastrophic. For example, the Younger Dryas event, which occurred approximately 12,900 years ago, resulted in a sharp and sudden cold snap that had a profound impact on existing animal populations. Similarly, the eruption of the Toba supervolcano approximately 74,000 years ago may have triggered a global volcanic winter, leading to a dramatic decline in the populations of many species. Such environmental shocks could have instantly wiped out vital food sources, destroyed entire habitats, and caused such environmental degradation that no trace remained of once thriving ecosystems. Now imagine an event of a completely different scale, an asteroid impact. It's not just a catastrophe, it's instant and total devastation. The Chicxulub asteroid impact, which ended the age of dinosaurs 66 million years ago, is a striking example of how a collision with a cosmic object can trigger a planet-wide ecological crisis, devastating entire ecosystems and, consequently, all the living creatures that depended on them. Although such events are rare, their destructive power defies imagination. They can instantly wipe out complex biological communities that took millions of years to develop. It's important to understand that environmental disasters can not only destroy life, but also weaken it to the point of becoming vulnerable to other threats. For example, a sudden climate shift could disrupt food chains, leading to resource shortages, a struggle for survival, and ultimately the complete devastation of entire regions. These shocks could have been the primary cause of the sudden extinction of many prehistoric species, leaving behind only pitiful scattered traces that modern scientists are struggling to piece together. Two major geological processes, natural sedimentation and erosion, play a key role in whether we ever see the remains of ancient creatures. Sedimentation is the slow accumulation of mineral and organic particles, layer after layer, covering and isolating fossils. In quiet environments, such as deep lake beds or river deltas, this process can create ideal conditions for preservation, protecting remains from physical deterioration, chemical decay, and microbial activity. Rapid burial of bones or skeletons in fine-grained sediments can slow their decay for thousands or even millions of years. However, in dynamic environments, where the elements' rage and erosion is particularly severe, the chances of preservation plummet. Erosion is a force that simultaneously destroys and creates for science. It slowly but surely wears away layers of soil and sediment, revealing what was previously deeply buried. While erosion can damage and destroy fossils, it also opens new windows into the past, allowing us to see what was previously inaccessible. Coastal cliffs, river bluffs, and mountain slopes are essentially natural excavations, where nature itself does the hard work for us, revealing artifacts of prehistoric life. The interaction between sediment accumulation and erosion also directly influences the chemical environment surrounding fossils. Minerals deposited with rocks can create unique conditions. For example, acidic soils accelerate the decay of bones, turning them into dust, while alkaline environments, conversely, promote their fossilization and excellent preservation. Understanding these subtleties is key to the correct interpretation of paleontological finds. These processes determine whether we find a well-preserved dinosaur skeleton or just a handful of fragments. They help paleontologists select the most promising excavation sites and understand the conditions in which a particular artifact was discovered. Now consider how natural resource deposits such as vast coal seams or ore veins might further influence this picture. What role do they play in concealing or conversely revealing traces of ancient life? These deposits, including mineral veins and coal seams, are themselves part of the geological record and can both conceal and reveal evidence of the past. Let's travel back in time to an era when the Earth itself was a chronicle and its strata and aquifers were the pages of that great book. The history of each region, its geological past, and its ecological landscape directly influence the secrets it reveals. When ancient monsters roamed these lands, they left behind invisible traces that today, millions of years later, we are learning to decipher using cutting-edge scientific methods. Imagine an ancient riverbed. Water currents, changing their path, created unique mineral deposits. Every layer, every grain of sand is a witness to a bygone era. And it is here, in these layers, that we can find traces of a bygone life. Geological activity, like an invisible archivist, carefully or conversely ruthlessly managed the legacy of the past. Traces of ancient life can manifest themselves in the form of altered rocks and unusual concentrations of certain elements, which can be identified through geochemical analysis. In some cases, these deposits, like sarcophagi, preserve fossilized bones or entire skeletons, turning them into veritable time capsules. However, the very nature that preserved these treasures can also reliably hide them. Over millions of years, processes such as sedimentation, the accumulation of sediment, erosion, or mineralization can mask or even distort the layers containing fossils. This turns the paleontologist's work into a true investigation, where they must separate natural geological formations from the priceless remains of ancient creatures. Moreover, places that once teemed with life, dense forests, full-flowing rivers, attracted entire ecosystems. Predators and their prey left their traces here, but the same natural forces that made these lands a dinosaur paradise can now become a curse for researchers. For example, intense geological activity near fossil-rich deposits can completely destroy this priceless evidence. Ancient skeletons buried in mineral-rich sediments can be shifted by tectonic plates or buried to inaccessible depth, making their discovery virtually impossible. On the other hand, nature sometimes creates ideal repositories. Consider, for example, ancient swamps or mineral-rich lakes. They are renowned for their incredible ability to preserve organic materials, providing us with astonishingly complete pictures of life millions of years ago. Understanding this complex relationship between the planet's natural resources and paleontological finds highlights the importance of an integrated approach. Here, geology, geochemistry, and paleontology must work together to identify the most promising excavation sites. To reconstruct our hidden past, it is crucial to understand how natural strata can preserve or, conversely, conceal traces of ancient life. This is especially relevant given that the most incredible discoveries may await us beneath as yet unexplored layers of the Earth. And this line of research naturally leads us to how climate models can predict where exactly to look for these lost worlds. Climate models are more than just a tool for meteorologists. For paleontologists, they're a veritable time machine, allowing us to peer into the past and understand where ancient animal civilizations might have lived. These models help us go beyond traditional fossil hunting methods. They reflect long-term ecological processes, giving us a profound understanding of the evolution of life on our planet. Climate conditions have played a colossal role in the distribution of life. They help researchers discover areas that might have been oases millions of years ago, but are now hidden beneath layers of sand or ice. By reconstructing past climate patterns, scientists can pinpoint with high accuracy the locations of ancient water sources, fertile valleys, or giant forests, the habitats of the Mesozoic titans. This allows them to focus their searches on areas that would otherwise be overlooked. One of the key tools here is the analysis of sedimentary rocks and paleoclimatic data. This analysis helps understand how climate change, for example, periods of extreme drought or conversely global floods, affected the preservation of the surface over millennia. Climate models can reveal zones where natural processes, such as sedimentation or wind erosion, either cocooned remains or mercilessly destroyed them. This understanding allows paleontologists to pinpoint the most likely locations for remarkably preserved skeletons, especially in regions that have experienced dramatic environmental changes. Moreover, climate modeling helps better interpret data obtained using modern remote sensing techniques. Imagine, specialized algorithms can predict where traces of ancient ecosystems, dry riverbeds where herds of sauropods drank to drink, or the remains of prehistoric forests, are hidden beneath modern landscapes. This close connection between climate science and cutting-edge technology allows for the efficient allocation of resources for field expeditions. It's worth noting that these models are constantly being refined, integrating geological, biological, and climatic information. As a result, we are obtaining increasingly accurate reconstructions of past environmental conditions. These reconstructions can reveal entire eras of time when specific climatic conditions supported the flourishing of particular dinosaur species. As we gain a better understanding of how climate influenced the dispersal and survival of ancient creatures, these models will become even more important for predicting where their traces may be preserved. They open up new horizons for us in exploring the hidden pages of life's history on Earth, especially in areas where the vagaries of nature have either preserved or obliterated the legacy of our distant ancestors. And here we come to the most dramatic point. Future climate change, unfolding before our eyes, creates both serious challenges and exciting yet terrifying opportunities for discovering traces of the ancient world. As global temperatures rise, glaciers melt, and sea levels fluctuate, the landscape that has concealed the planet's history for millennia is beginning to change. It could reveal new paleontological treasures or forever destroy existing ones. These changes could accelerate the erosion of surface sediments, making some fossils more accessible. However, these same processes could threaten fragile remains through increased weathering and biological activity. Imagine rapid melting of ice in the polar regions could expose previously frozen layers, opening up incredible research opportunities. Permafrost could yield not just bones, but entire mummies of prehistoric creatures, flesh and skin preserved. But the moment we discover them, they become vulnerable to further destruction. Changes in precipitation patterns and increased storm intensity could wash away or, conversely, bury entire paleontological layers that held invaluable chronological context. In some cases, floods and landslides could wipe out entire dinosaur graveyards, forever depriving us of any knowledge of their history. On the other hand, in arid regions, increasing dryness may actually promote the preservation of organic materials that would have long since decayed in wetter conditions. This potentially increases our chances of finding unique finds. The consequences of climate change extend far beyond physical preservation. Areas previously considered inaccessible to paleontological expeditions, such as deserts or tundra, may become more hospitable. However, these same changes may also create new challenges. For example, increased soil salinity or thawing permafrost could damage fossils during excavation. This ongoing transformation of landscapes highlights the importance of the race against time. Scientists must adapt their approaches to finding, documenting, and preserving ancient artifacts before they disappear in a constantly changing world. This dynamic interplay between climate and paleontology demonstrates how the future can both reveal and forever bury our understanding of the history of life on Earth. Studying past environmental changes opens the door to a profound understanding of how ancient ecosystems remained resilient or, conversely, became vulnerable over the centuries. From the swamps to the Great Plains of Mesopotamia, the ancient world constantly faced climate fluctuations, and its history holds lessons for us all. Here, in the depths of prehistory, not just societies, but entire biological empires collapsed. Dynasties of giants that ruled the planet for millions of years faced the same merciless challenges: the depletion of vital resources and monstrous natural disasters. These events, frozen in stone, became the death knell for some species and a source of growth for others. They are the greatest lessons of Earth's history, whispering to us from the depths of time one simple truth: no life form, no matter how powerful, is completely immune to the wrath of the environment. The key lesson the fossil record teaches us is the relentless need for adaptation. Species that thrived and conquered entire continents demonstrated an incredible capacity for change. They exploited new food sources, adapted to changing climates, or developed new survival strategies. Their biological and social structures, whether herding behavior or new hunting methods, evolved in direct response to the challenges the planet presented them. Conversely, those creatures that failed to recognize nature's threatening signals, whether a great drought turning jungles into deserts or the slow but sure extinction of food plants, were doomed. Their path led inexorably to decline and oblivion. Consider the great Permian extinction, which wiped out almost all life on Earth. It became a striking example of how global environmental stresses, like a hammer, strike the most vulnerable points of entire ecosystems, leading them to complete collapse. Another crucial lesson is the price of a lack of biological foresight. Many prehistoric ecosystems were perfectly tuned but fragile mechanisms. They lacked the resilience to mitigate the impending ecological crisis. This led to cascading extinctions. Plants disappeared, herbivores perished, and when herbivores perished, the great predators starved. A painfully familiar picture, isn't it? Today, we see the same patterns in our own problems, where the reckless depletion of resources and pollution of the planet threaten the stability of our own world. Understanding these ancient cycles forces us to seriously consider sustainability and the steps we can take to avoid the fate of the titans of the past. Archaeological and paleontological data reveal another side of the coin. Environmental upheavals often became the catalyst for incredible evolutionary breakthroughs. Having survived the crisis, life didn't simply recover. It gave birth to new, sometimes bizarre forms. New survival technologies emerged, new species occupied empty niches, and evolution itself seemed to be exploring new paths of development. These bursts of adaptation demonstrate nature's astonishing ingenuity and its ability to renew itself even after the most devastating blows. The history of ancient worlds demonstrates that the longevity of any dominance, whether the reign of dinosaurs or the age of giant mammals, was directly dependent on the ability to adapt, use resources wisely, and exist within ecological constraints. This perspective not only deepens our understanding of the laws of life, but also serves as a stern warning for us. It reminds us that caring for our world is not a whim, but a fundamental requirement for our survival, highlighting the delicate balance between civilization and nature, which is so easily upset. Reflecting on these lessons, we inevitably come to the question: how do we learn about these ancient dramas in the first place? How does paleontology, the science of the past, allow us to peer back millions of years? Searching for traces of ancient life is more than just digging up bones. It's the thrilling possibility that right beneath our feet, buried deep within geological strata, lies evidence of entire eras that predate the emergence of humans. This idea resonates with our theme. We're not simply searching for remains. We're searching for the history of natural civilizations that existed long before us and perhaps left far deeper traces than we can imagine. Thus, the work of a paleontologist is more than just collecting fossils. It's a true detective investigation, searching for physical evidence or anomalies that point to the turbulent activity of life in the past. Traditionally, we imagine a scientist with a brush cleaning a dinosaur bone. But what if traces were left behind by more than just bones? What if entire ecosystems, having risen and fallen, altered the very geology of the planet long before our ancestors descended from the trees? Recently, researchers have increasingly discussed searching for so-called biosignatures, relics of ancient life that can be found in the form of unusual chemical deposits, geological structures, or anomalous phenomena in the Earth's crust. One area of research is analyzing ancient sedimentary rocks for signs of large-scale biological intervention. Unusual mineral layers, strange geological formations, or anomalous isotopic ratios may indicate past microbial activity that altered the composition of the atmosphere and oceans. Large-scale life activity could also have left its traces. The discovery of gigantic ancient reef systems built by billions of tiny organisms or traces of massive mineral mining by bacteria, all of this could indicate ancient industrial activity at the microbiological level. These traces could be preserved in the geological record, revealing the secrets of biological civilizations that existed millions or even billions of years ago. In addition to studying rocks, researchers are also focusing on indirect evidence hidden in the planet's structure itself. Such signals could include unusual patterns in the distribution of chemical elements, anomalous deposits, or even changes in ancient climate records that cannot be explained by purely geological processes. For example, hypothetical megastructures created by life, such as stromatolites, which once dominated the planet by producing oxygen, forever changed the world. If they had existed billions of years ago, they would still leave noticeable chemical and geological imprints. The search also includes the analysis of microscopic artifacts, such as spores, pollen, or even organic molecules that may have been preserved in amber or permafrost. If ancient ecosystems were complex and diverse, traces of their activity may be scattered across the planet. They may await discovery, remaining silent witnesses to bygone eras. In our search for these ancient worlds, we employ a wide range of methods, from traditional excavations to innovative chemical analysis and rock scanning. This expands the horizons of paleontology from simple bone collection to in-depth geological and chemical research spanning the entire history of our planet. To detect these signals or artifacts, which could indicate the existence of entire ancient ecosystems, requires a deep understanding of geological processes and the potential traces life may have left behind. Unlike the well-preserved skeletons we find relatively often, these ancient biosignatures are likely to be subtle, as they have been preserved for millions of years in the constantly changing Earth's crust. Scientists suggest that anomalous chemical signals could be one of the key indicators. The study of ancient rocks is aimed at analyzing chemical elements that could have been processed by living organisms. Currently, efforts are focused on finding obvious traces, such as graphite of biological origin. However, ancient life forms could have left more subtle imprints. One possible indicator is unusual isotopic ratios that are inconsistent with natural geological sources. These signals may be weak, blurred by time, or mixed with more recent deposits, making them difficult to distinguish from purely natural phenomena. Another potential clue is the discovery of unusual physical structures in the rock, such as large, geometrically regular mineral deposits or rhythmic layers that could not have formed without the participation of living organisms. These structures could have been created by bacterial colonies for resource extraction or defense, and could be silent witnesses to ancient activity awaiting discovery. Their detection requires modern scanning and analysis technologies capable of detecting the smallest chemical and structural anomalies deep within rock strata. Spectral analysis of ancient minerals and meteorites opens up new horizons. The presence of exotic organic compounds or unusual isotopic ratios in rocks may indicate a possible biological origin. These artifacts could have been formed by the metabolic processes of ancient organisms and then preserved in the rock for billions of years. Despite all the difficulties, advances in geochemistry, data processing, and interdisciplinary approaches offer hope. Our ability to detect and interpret evidence of ancient life is constantly improving. Yet, the central question remains: are the most astonishing evidences hidden right beneath our feet in the geological record of our own planet? After all, artifacts of ancient life found in the Earth's strata have the potential to radically alter our perception of not only human history, but the entire history of life on Earth, transforming what we thought were ordinary stones into pages of a great prehistoric chronicle. From a scientific perspective, such reflections present a real challenge. They force scientists to completely rethink their methods and seek entirely new ways to peer into our planet's past. Let's step into a geologist's laboratory. If intelligence existed on Earth millions of years before us, then all our time-tested tools, analysis of rock layers, radiometric dating, may prove simply blind. They need to be recalibrated, rethought from scratch. Perhaps they are simply unable to detect those subtle signals or anomalies that scream of past technological activity, but we miss them, attributing them to the quirks of nature. This forces us to return to the very basics. We must once again delve into the paleontological record, into sedimentary layers millions of years old, and study the isotopic composition of ancient minerals. The goal of this ambitious investigation is to find traces of artificial structures or materials that may be barely visible today, almost erased by time, and mistaken for ordinary geological formations. And then another, no less complex question arises. What can possibly survive millions of years? How durable and long-lasting must the artifacts of an ancient civilization be? Could the remains of their cities and machines be buried under kilometers of rock, ground down by the movement of tectonic plates, and forever hidden from our sight? Now let's move away from geology and touch on something deeper: our place in the universe. The very idea that something intelligent, capable of building and creating, could have existed on this planet before humanity. This idea strikes at the very heart of our pride. It completely undermines the anthropocentric view of the world, according to which humans are the pinnacle of creation, the pinnacle of the evolutionary tree. Instead, we are presented with a completely different picture. Perhaps intelligence and technology are not a unique phenomenon, but a kind of repeating cycle in the long history of Earth. This perspective forces us to be humble. It opens up incredible possibilities for imagination about the paths life could have taken. Civilizations could have been born, flourished, and perished countless times, leaving behind only the faintest, ghostly traces. This thought also forces us to ask fundamental questions about the nature of consciousness and civilization itself. Was the emergence of technological society an inevitable evolutionary step? Or does it require unique planetary conditions, making civilization a rare and fragile phenomenon in the universe? Moreover, delving into hypotheses about pre-human civilizations, we encounter even more complex mysteries. How long could they have existed? What impact did their activities have on the planet? Imagine for a moment that they interacted with the environment so intensely that they permanently altered the climate or atmospheric composition. Could we, today, millions of years later, detect these global scars on the planet's surface? Such studies challenge our understanding of Earth's stability and hint that the ups and downs of technological progress may be cyclical. And as we ponder these scientific and philosophical questions, the foundation for a fascinating dialogue about extraterrestrial life and ancient super-civilizations is being laid. And here, the mystery of civilizations lost in the depths of time bridges the gap to another great question. Are we alone in the universe? The search for traces of intelligence on our own planet is inextricably linked to the search for intelligence among the distant stars. This connection underscores the importance of the so-called Silurian Hypothesis. It becomes a kind of missing link between Earth's deep past and cosmic exploration, forcing us to completely rethink what we even consider evidence of intelligence. This bold idea, suggesting that advanced civilizations existed here before us, is closely intertwined with contemporary debates about life on other planets. It challenges the established chronology of human development and forces us to acknowledge that the history of our home planet may be far more complex and multifaceted than we've traditionally believed. This opens up entirely new horizons for research. We can conceive of the possibility that alien civilizations may have influenced the emergence of life on Earth or even brought it here. It's also worth considering, how could ancient societies have achieved incredible technologies long before the first written records appeared? The hypothesis of extraterrestrial life makes it clear. Earth is hardly the only oasis of intelligence in the vast cosmos. And in this context, the search for evidence of ancient contact with aliens, anomalous artifacts, inexplicable gigantic structures takes on a completely new, far deeper meaning. If we accept that civilizations flourished on Earth long before humans, then their sudden appearance or rapid technological advancement can be explained precisely by contact with extraterrestrial intelligence. Perhaps their legacy was misunderstood by descendants and transformed into myths of gods and monsters, and we mistakenly regard their structures as natural formations. This theory is providing a powerful impetus for scientists and independent researchers, forcing them to reconsider the origins of many archaeological mysteries. They ask, what if some artifacts or geological anomalies are nothing more than traces of those who came before us, or evidence of alien intervention? Moreover, the so-called Silurian Hypothesis forces us to take a completely new look at the ancient myths that have captivated human imagination for centuries. Legends of Atlantis, tales of the mysterious Lemuria, and other lost lands. These mythical continents, which mainstream science has traditionally dismissed as beautiful fiction, can now be viewed from a different perspective. What if these are more than just fairy tales? What if they encode a collective memory of real events, of civilizations that existed long before the advent of writing and have sunk into oblivion? This hypothesis forces us to pause and consider, should these myths be taken literally or as symbols? Could they be the key to forgotten or deliberately hidden chapters of not only human, but also non-human history? This understanding also prompts us to rethink the very boundary between history and myth. While academic scholarship often treats such narratives with distrust, this hypothesis calls for an open-minded study of archaeological and geological data. It demands that we seek evidence of earlier, possibly non-human, civilizations. With the advancement of sciences such as archaeology, astrobiology, and planetology, the rigid boundaries between myth, history, and scientific fact are beginning to melt and blur. This is giving rise to a fascinating dialogue about the true age and origins of civilization, not only on Earth, but perhaps far beyond. Throughout human history, we have seen how numerous myths and legends have simultaneously supported and challenged the idea that advanced civilizations could have existed here before us. For example, some ancient cultures tell of lost worlds and powerful primordial beings. These stories seem to hint at a distant and far more advanced past. Take the Sumerians, often considered one of the first civilizations. Their texts explicitly state that all knowledge and society itself were bestowed upon them by divine beings descending from the heavens. This may be a veiled reference to an origin story that extends back much further into prehistory. Human history is full of such mysteries and enigmas. The ancient Egyptians, for example, believed that their land was once a realm of primordial chaos, subsequently brought into order by powerful gods. This also suggests that true history began long before the rise of the pharaonic civilization we know today. However, many traditional narratives assert the opposite, that it was with the emergence of humans that the true path of progress from primitive origins began. These narratives essentially deny the existence of predecessors, presenting human development as a single, straight, unbroken line, stretching back into an unknown past. Such ideas find strong support in religious texts, which often describe divine creation as the single starting point for all creation. Conventional science views Earth as the cradle of humanity, without categorically rejecting the very possibility of the existence of earlier intelligent beings. However, some legends and archaeological finds have already been interpreted as possible evidence of the existence of ancient advanced societies that predate our known history. For example, the stories of Atlantis, detailed by Plato, describe a highly advanced civilization that vanished overnight into the depths of the sea. These stories still spark heated debate. Do they have a real historical basis, or are they simply beautiful allegories? Some megalithic structures, such as the Great Pyramids of Giza or Stonehenge, also challenge the official version of history. They evoke shock and awe at the technological capabilities of ancient builders, fueling speculation about lost knowledge or entire civilizations. Despite these facts and narratives, mainstream science remains extremely cautious. It typically views myths as symbolic or allegorical narratives, rather than literal accounts of events. The primary challenge for researchers is to determine whether these ancient stories contain hidden meanings that can be deciphered by modern scholars. Are they echoes of a collective memory of real events, or merely figments of a wild imagination? Thus, we hear time and again about civilizations that existed long before the advent of humans. However, to move beyond assumptions and hypotheses, scientific research must be based on solid physical evidence, and this requires the most thorough verification and meticulous analysis. This is what opens the way to understanding how scientific methods such as geology, paleontology, and archaeology can provide a critical assessment of the very possibility of the existence of civilizations in ancient times. Each of these disciplines offers its own unique perspective on Earth's past. Geology, for example, provides the fundamental foundation. It analyzes rocks and creates maps of layers that help us understand how our planet's surface formed over billions of years. Then comes paleontology, a science that uses fossilized bones and the smallest imprints in stone to reconstruct the history of life on Earth in its primordial form. And finally, archaeology. It searches not for bones, but for handprints, for traces of intelligence. It studies the material remains left behind by ancient cultures, giving us insight into their lives and worldviews. Geologists, using highly precise dating methods such as analyzing radioactive isotopes in volcanic ash, can establish time frames that extend far beyond the entire written history of humanity. And if anomalies or unexpected features are suddenly discovered in these ancient layers, for example, unusual accumulations of rare minerals, imagine an artifact that at first glance appears to be human-made, but upon closer inspection defies everything we know. Such objects may bear technological imprints or be composed of materials that directly point to their extraterrestrial cosmic origin. Consider some archaeological finds that baffle even the most seasoned scientists. They simply don't fit into the picture of the development of known ancient civilizations and could be evidence of a visitation from another world. We're talking about anomalies that force us to rethink history. For example, incredibly complex metallurgy that developed thousands of years before its time. Or materials with an isotopic composition that isn't found in any geological process on Earth. And what about gigantic structures, the construction of which seems impossible without technologies that ancient people simply didn't have? These incredible artifacts may be buried deep within geological strata, sealed there millions of years ago by ancient cataclysms. Or, even more intriguingly, they may be ingeniously embedded within objects we've considered for decades to be ordinary creations of our ancestors. Uncovering such anomalies is a titanic undertaking, requiring not just attention, but the collaboration of specialists from a wide variety of cloud keys. Geochemists, like detectives, study the chemical composition of finds, searching for unusual isotope ratios that serve as a kind of cosmic passport, proving their extraterrestrial origin. Meanwhile, materials scientists in their laboratories are trying to unravel the secrets of alloys and composite materials that simply have no analogs on Earth. Of course, there is a risk of error. Sometimes meteorite fragments or rare mineral formations found in ancient layers can be mistaken for something man-made. Without the most thorough analysis, these natural wonders can easily be dismissed as geological anomalies or even traces of modern industrial pollution. And yet, archaeologists must keep an open mind. They must be willing to entertain the idea that some of the most enigmatic objects, be they inexplicable carvings, mysterious symbols, or artifacts with no cultural affiliation, may actually be messages from the depths of space. Each such find requires incredibly meticulous research to rule out all possible misinterpretations. The greatest challenge for a scientist here is to distinguish between a genuine extraterrestrial artifact and a rare natural phenomenon, or simply our misunderstanding of what ancient craftsmen were capable of. The presence of strange finds at excavation sites is too easily explained away by a freak of nature or accidental contamination, especially when there's no ironclad scientific basis. Moreover, such artifacts are extremely rare, and accurately determining their age is incredibly difficult. All this makes it difficult to settle the debate and definitively prove their extraterrestrial origin. The very idea that alien objects might not simply be hidden, but woven into the fabric of Earth's ancient history, forces us to completely rethink the past. Archaeological finds that have sparked heated debate for decades are now attracting the keen attention of a new generation of scientists and researchers. This interest is pushing them beyond their usual methods, forcing them to explore fields such as astrobiology and planetology. This holistic approach opens up entirely new horizons. It allows us to speculate that the history of our planet may be far more closely connected to space aliens than we ever dared to imagine. And this, in turn, is sparking heated debate about how we should now interpret these inexplicable relics of our distant past. When considering such possibilities, the question inevitably arises: how might theories about ancient aliens change our understanding of the most enigmatic archaeological discoveries? These hypotheses often directly contradict classical scientific interpretations. They suggest that extraterrestrial beings may not only have influenced early human civilizations, but may even have been their creators. This bold viewpoint forces scientists to take a fresh look at mysterious discoveries, unusual artifacts, unexplained megalithic structures, and anomalous traces, acknowledging the possibility of their extraterrestrial origin. Instead of dismissing these anomalies as natural accidents or cultural coincidences, proponents of this theory claim that we may be witnessing direct evidence of contact or even intervention by extraterrestrial civilizations. Imagine strange carvings or symbols that are completely out of keeping with the level of development of the culture in which they were found. Perhaps these are not primitive art, but artifacts created by highly advanced extraterrestrial beings. Perhaps they were messages or symbols whose true meaning has been irretrievably lost over the centuries. This reassessment of the archaeological context forces scientists to critically examine the dogma that absolutely all ancient artifacts were created by human hands. This opens the door to alternative explanations that allow for an alien influence. The influence of this theory becomes especially significant when research findings contradict everything we know about the technological or cultural capabilities of ancient societies. This approach encourages interdisciplinary collaboration, combining knowledge from fields as diverse as astronomy, geology, and material science to jointly analyze anomalies. The idea that some artifacts or materials may be of extraterrestrial origin encourages researchers to seek evidence in the most unconventional sources. This fosters open-mindedness and encourages creative research methods. Ancient alien hypotheses are having a profound impact on the search for extraterrestrial artifacts, expanding the boundaries of research far beyond traditional archaeological excavations. Researchers can now study cosmic phenomena and even space debris, which may harbor invaluable clues or even the physical remains of ancient civilizations. This, in turn, leads us to consider extraterrestrial materials such as meteorites and cosmic dust as potential carriers of evidence. These cosmic wanderers, which constantly fall to Earth, may contain hidden information, biological traces, or even microscopic artifacts from distant worlds or ancient civilizations that once interacted with our planet. In their search for traces of extraterrestrial presence, researchers are increasingly turning their attention to space debris, which may contain crucial information about ancient civilizations beyond our own world. Meteorites and cosmic dust are more than just random debris from cosmic cataclysms. They may be true messengers, carrying information about civilizations that existed long before us. Their value in the search for extraterrestrial artifacts lies in their ability to travel unimaginable distances, carrying material and perhaps even biological or technological traces across the void. As they traverse the vastness of space, these celestial particles can capture fragments of the surfaces of other planets, technological debris, or other anomalous materials left behind by civilizations long gone or hiding in distant star systems. Meteorites, in particular, are an invaluable source of information as they arrive from across the solar system and even beyond. Formed in distant regions of the universe, these celestial rocks still retain unique chemical and isotopic signatures reflecting their birth environment. When a meteorite falls to Earth, it may contain isotopic anomalies, or embedded microstructures that suggest its artificial origin or connection to past technological activity. For example, certain isotopic ratios of elements, such as nitrogen or noble gases, may indicate processes not found in the natural geology of planets, dramatically increasing the likelihood of artificial intervention. Furthermore, some meteorites, when examined microscopically, exhibit structures strikingly resembling microchips or machine parts, raising the most daring speculation about their artificial origin. Cosmic dust, composed of microscopic particles from comets, asteroids, and interstellar clouds, offers a more subtle but no less intriguing avenue for research. These tiny particles may contain complex organic molecules, unusual mineral phases, or other chemical markers that could be linked to biological or technological activity. Because cosmic dust continually settles in planetary atmospheres, it can be collected and analyzed, providing a continuous record of matter from a wide variety of regions of space. If anomalies or unusual compounds are found in this dust, it could provide indirect evidence of extraterrestrial activity, especially if these findings don't fit the natural patterns of matter formation. Thanks to modern analytical techniques such as high-precision mass spectrometry, electron microscopy, and spectroscopy, scientists can detect the smallest anomalies in meteorites and cosmic dust. These technologies can detect chemical, isotopic, and structural markers that would otherwise remain forever undetected. They open exciting horizons for searching for traces of ancient civilizations, or their remains transported across the cosmos. As research progresses, this cosmic cargo may reveal hidden chapters of cosmic history, shedding light on possible interactions between ancient civilizations and the universe as a whole. Astronomical observations play a key role in the search for sites where ancient extraterrestrial artifacts may be hiding. These observations involve more than simply staring at the starry sky. They involve a deep analysis of celestial phenomena, the stellar environment, and cosmic anomalies that could indicate the activity of extraterrestrial intelligence in the distant past. One of the main approaches involves studying the regions around ancient stars and planetary systems. Scientists look for unusual characteristics or deviations that cannot be explained by natural astrophysical processes, such as anomalies in a star's luminosity or oddities in the motion of its planets. Imagine a star that flickers completely irregularly, violating all known cosmic laws. Its light fades and then flares up again, as if something colossal were periodically passing in front of it, obscuring it from our view. Anomalies, like the mysterious behavior of Tabby's star, make scientists wonder, are we observing traces of ancient intelligence? Are these shadows a sign of the existence of gigantic artificial structures, so-called megastructures? To peer into the darkest and most distant corners of the universe, we use our infrared eyes, telescopes like WISE. Their job is to scan the cosmos for evidence of the past activity of civilizations long since vanished. Astronomers, like cosmic archaeologists, play a key role here. They search for excess thermal radiation, the very traces that might have been left by a civilization that learned to harvest energy on an industrial scale. These are hypothetical structures like Dyson spheres. Imagine a colossal shell built around an entire star to capture every last drop of its energy. Such a structure would inevitably heat up and emit infrared radiation. This thermal signature would be unique, unmistakable from any known natural phenomenon. That's why researchers meticulously sift through enormous data sets, trying to find these anomalies, patterns that don't fit into the conventional picture of the world. But we don't just look, we also listen. The enormous ears of our planet, radio telescopes like the gigantic Allen Array, are constantly listening to the cosmic silence. They search for anomalous signals, highly focused transmissions that could originate from advanced civilizations or their automated systems that have outlived their creators. We also closely study worlds around other stars. Using spectroscopy, a method that allows us to determine chemical composition from a distance, we analyze the atmospheres and surfaces of planets. We look for things that shouldn't be there, traces of artificial alteration or artifact deposits. The discovery, for example, of materials or structures that could not have formed naturally under known geological or atmospheric conditions would be powerful indirect evidence. Imagine peering into the icy outskirts of an alien star system, their equivalent of our own Kuiper Belt, and seeing not a chaotic accumulation of rocks and ice, but anomalously ordered debris fields, structures that look like the ruins of something grand. All these astronomical methods create a unified system that helps narrow the endless expanses of space to specific, most promising points for further, more in-depth study. Yet, despite the power of our technology, this search remains an incredibly challenging task. Separating the artificial signal from natural cosmic noise is particularly challenging. This requires not only the most advanced instruments, but also the highest level of skill in interpreting complex data. Distinguishing between natural processes occurring in space and man-made signals is one of the most fundamental problems in modern science. The universe is filled with a wide variety of radiation and short but powerful events that can easily mimic signs of intelligent activity. The main difficulty is that many signals from space are inherently ambiguous. Take fast radio bursts, FRBs, for example. These are incredibly powerful bursts of radio waves lasting only thousandths of a second, originating from intergalactic space. Their characteristics may resemble communication signals. However, most scientists believe they are the result of colossal natural cataclysms. For example, the collision of neutron stars or the violent activity of magnetars, stars with monstrous magnetic fields. To distinguish such natural sources from artificial ones, a detailed analysis is necessary, studying their spectrum, timing characteristics, polarization, and how often they repeat. The main obstacle to this is the incredible diversity and complete unpredictability of natural phenomena. Many signals from space are chaotic, fleeting, and never repeat, which does not suggest intentional transmission of information. For example, pulsars are the rapidly rotating remnants of exploded stars. They emit strictly periodic radio pulses and could initially even be mistaken for extraterrestrial beacons. However, their remarkably stable radiation is now perfectly explained by the known laws of physics. At the same time, signals with irregular or non-repeating characteristics raise suspicion, but they too could simply be the result of complex natural processes that we do not yet fully understand. This forces scientists to constantly develop new analytical methods to learn how to accurately distinguish potential artificial signals from the natural cosmic background. This uncertainty makes it difficult to classify signals with complete confidence, especially when data is sparse or corrupted by interference. Another problem is the technological limitations of our own instruments. Although radio telescopes and data processing algorithms are constantly improving, they may still lack the sensitivity and resolution to detect subtle signs of artificial origin. Add to this interference from our own sources, satellites, terrestrial radio transmissions, and even space debris. All this further complicates the process and often leads to false positives that could mimic signals from extraterrestrial civilizations. Moreover, it's possible that other civilizations use communication methods radically different from our own. What if they communicate not by radio, but via modulated laser beams, neutrino streams, or other exotic methods that we can't yet detect. This makes finding them even more difficult, almost impossible. Our instruments may simply be blind to the signals sent by other civilizations, which only highlights the limitations of our technology. The problem isn't just technology, but also our own perception of what we consider signs of intelligence in this vast cosmic void. But as our observational methods and theoretical models evolve, scientists are gradually improving their ability to distinguish natural cosmic phenomena from possible traces of alien technology. This remains one of the most challenging tasks in astrophysics. Future space missions offer truly exciting prospects. They may discover traces of ancient civilizations beyond Earth, forever changing our understanding of the history of life in the universe. Technological advances, more sensitive spectrometers, autonomous robotic explorers, and sophisticated remote sensing systems are opening up entirely new horizons. We stand on the threshold of a new era in the search for extraterrestrial intelligence, both modern and ancient. Missions to icy moons like Europa or Enceladus, where massive subglacial oceans are suspected to lurk beneath thick layers of ice, could yield real breakthroughs. Who knows what biosignatures or even artifacts might be frozen in this permafrost, waiting for millions of years? Our missions to Mars continue to methodically explore the planet, searching for evidence of past life, with a particular focus on searching for fossilized microorganisms in ancient sedimentary rocks. The discovery of complex organic molecules on other planets would be irrefutable proof that life, and perhaps civilization, arose independently in the universe. Beyond our solar system, powerful telescopes already allow us to peer into the atmospheres of exoplanets. We search for chemical anomalies there, for example, traces of industrial pollutants or even the artificial glow of cities at night. The discovery of such signals would be a landmark event in human history, proof that somewhere out there in the depths of space, other intelligent civilizations existed, leaving behind tangible traces. The search for extraterrestrial artifacts, whether gigantic megastructures or anomalous radio signals, is becoming one of the most important goals for future research programs. As our technologies advance, the possibility of discovering the remains of ancient civilizations, whether they're structures or energy signatures, is becoming increasingly realistic. These searches could lead us to titanic civilizations that flourished millions or even billions of years ago, whose traces have been preserved across cosmic timescales. However, the primary challenge remains the ability to distinguish genuine evidence from natural phenomena or false alarms. To ensure our conclusions are reliable, we must develop the most stringent verification criteria and utilize the full arsenal of modern science. The prospect of discovering ancient extraterrestrial civilizations will not only answer the eternal question of whether we are alone in the universe, but will also forever change our perception of our place in this vast space. It will force us to consider whether humanity is unique or whether we are merely one of countless chapters in the endless book of cosmic life. And this research inevitably returns us to the question of our own origins. If we find evidence of civilizations that predate humankind, It will upend our understanding of our own roots and lead to a complete revision of scientific, philosophical, and social theories. We traditionally perceive human evolution as a linear process that reached its peak with the emergence of modern humans, Homo sapiens. This concept is supported by decades of paleontological finds, genetic studies, and archaeological discoveries, which have allowed us to construct a clear chronology of our past. However, if traces of civilizations that existed before the emergence of humans were discovered, this entire linear model would collapse overnight. Such discoveries could point to an entirely different, far more complex and mysterious history of our planet. Imagine for a moment that traces of something utterly unthinkable were discovered in the geological record of our planet. Evidence that long before the first humans appeared, intelligent beings already existed on Earth, building complex societies. Such evidence would be a true shock, capable of turning everything we knew about ourselves upside down. The idea that only humans are capable of building civilizations would collapse overnight. It would force humanity to look in the mirror and ask a painful question. How unique is our intelligence? How exceptional is our technological development? What exact conditions in the universe must converge for a highly organized society to emerge and flourish? We can only speculate about what these ancient civilizations were like. Did they possess technologies comparable to our own? Or perhaps their forms of knowledge and social organization were so different that they surpass our wildest imagination? The very idea that entire civilizations could have arisen and vanished without a trace on this planet before us, leaving behind only ghostly, long-forgotten imprints in stone, could shatter our notions of the stability and vulnerability of society. This discovery would boldly challenge our view of the human-centered world. It would force us to radically rethink humanity's role in Earth's incredibly long and dramatic history. It could push us to a stunning realization. What if our species is not the pinnacle of evolution? What if, in the grand theater of life and intelligence, we are merely one of many, and far from the first or the most brilliant? This realization would fundamentally alter our understanding of our own evolutionary path. The implications of such a discovery would reach far beyond science, touching the deepest chords of our souls, questions about our purpose and destiny. After all, if great civilizations can arise, reach unprecedented heights, and then vanish without a trace, erased from the memory of time, then what is the fate of our own society? How strong is the foundation on which we stand? Such knowledge would resonate profoundly in philosophy and influence our cultural identity. It could force us to reflect on our own fragility and inspire a complete rethinking of our views on progress and the very meaning of consciousness in the universe. The possibility of the existence of ancient pre-human civilizations forces us to perceive our history not as a unique and singular path, but as a chapter in a much larger, perhaps cyclical, saga of cosmic and terrestrial evolution. And this grand saga constantly challenges us, pushing the boundaries of our understanding of life. The realization that humans were neither the first nor perhaps the only intelligent masters of Earth challenges our deepest, most ingrained philosophical and cultural beliefs. It forces us to ask fundamental questions about our role in the universe, the uniqueness of human consciousness, and the very nature of progress. Historically, many cultures and schools of thought have viewed humanity as the pinnacle of creation, a species with a special, almost divine mission in the cosmic order. Recognizing that we are not alone in this regard could be a powerful impetus for rethinking our true place in the world. The discovery of civilizations that existed before us, or even concurrently, would shatter our anthropocentric worldview. We would see a universe brimming with consciousness and creativity across countless eons. This cultural shift could lead to a new understanding of our uniqueness. Myths, religious dogmas, and philosophical treatises that have emphasized our exceptionalism for centuries would be questioned or reconsidered on a broader cosmic scale. The idea that humanity represents a singular and unrepeatable path to enlightenment could give way to a concept of continuity, cyclicality, and perhaps a common cosmic heritage shared by multiple intelligent species. Such a perspective could teach us humility and develop a deep sense of kinship with other potential intelligent beings, both past and future. Philosophically, this touches on the very foundations of our existence, questions of origin, purpose, and morality. If previous civilizations had achieved the same level of technological and social development as us, their rise and fall would provide invaluable lessons. Their history would become a dire warning about how we should move forward. The realization that intelligent life on Earth could have arisen, flourished, and declined countless times would force us to reconsider our views on stability and progress. We might ask ourselves, is technological progress an inevitable and linear process, or is it cyclical and subject to harsh ecological or cosmic laws that operate independently of the will of individual civilizations? This uncertainty could exacerbate existential debates. Are we truly the first in a cosmic sense, or merely the latest in a long line of intelligent life? This nebula could provide new impetus to philosophical inquiry, prompting us to seek new paths to understanding consciousness and to comprehend the legacy and potential of future civilizations. Ultimately, discovering evidence of the existence of other intelligent species would not simply shift our scientific paradigm. It would have a profound impact on our sense of self and cultural understanding of our place in the universe. The discovery of traces of ancient pre-human civilizations could fundamentally change our views on technological progress and social development. We've become accustomed to thinking of human history as a gradual ascent from primitive stone tools to complex technological societies. However, if we were to find evidence of earlier civilizations, this coherent concept would be challenged. It would force us to consider that technological evolution is not an exclusive achievement of humanity, but perhaps part of a broader recurring cycle of social rise and decline throughout the long history of our planet. If we were to discover the remains of highly developed ancient societies buried beneath the centuries, we would have to reconsider our understanding of the speed and nature of progress. Imagine the presence of highly sophisticated infrastructure or evidence of artificially altered geological landscapes could indicate that these societies once achieved an incredible level of development, perhaps comparable to our own today, perhaps even surpassing it. Such discoveries would force us to consider whether technological innovation is an inherent feature of all intelligent life, or whether it depends on a unique confluence of environmental and social circumstances. This hypothesis may indicate that civilizations can experience periods of rapid, explosive growth, inevitably followed by catastrophic declines, a pattern that may repeat itself over geological timescales. Understanding that multiple civilizations may have existed at different epochs in Earth's history would also change our understanding of social development. It could mean that technological progress does not always move in a straight line, from simple to complex, but depends on a variety of factors, including random historical events and powerful environmental influences. Drastic changes in the ecosystem, the depletion of vital resources, or internal societal collapse could cause a civilization's developmental path to be abruptly altered or even halted altogether. This realization may teach us to be more humble in our assessment of our own path and to focus on resilience and adaptability in the course of social evolution. Moreover, such discoveries may influence our understanding of how to ensure long-term and sustainable technological growth. Knowing that advanced civilizations before us may have encountered their own intractable problems and collapsed may serve as a stark warning and prompt us to consider the long-term sustainability of our current path. It may also inspire us to rethink the very concept of progress, shifting the emphasis from purely technological achievements to societal stability and harmony with nature. By changing our perception of progress, these discoveries inevitably compel us to consider the ethical implications of discovering and interpreting evidence of ancient civilizations. Our attitude toward this knowledge, whether respect, curiosity, or extreme caution, becomes vital, paving the way for a deeper understanding of our place in the complex and multi-layered history of the Earth. The quest to find evidence of ancient civilizations that existed long before human history raises serious ethical questions that go far beyond mere scientific curiosity. As researchers delve deeper into the planet's geological and biological archives, they confront crucial dilemmas related to responsible information management, respect for the past, and the potential consequences of new discoveries. One of the most significant concerns is the cultural and societal impact. The discovery of evidence of a pre-human civilization could challenge deeply held beliefs, religious teachings, and entire cultural identities, potentially causing genuine shock and stress in societies around the world. To disseminate such stunning results responsibly, careful and thoughtful public communication is essential, emphasizing scientific rigor and honestly acknowledging all existing uncertainties. This will help avoid a wave of misinformation or unfounded wild speculation. It is also crucial to consider preservation and potential destruction. Excavation or probing of ancient geological strata can inadvertently damage fragile environments or destroy priceless evidence of the past. Scientists and policymakers must carefully weigh the potential benefits of discoveries against the risks of irreversible consequences. The surviving geological record is an invaluable archive of Earth's history. Ethical research requires the use of minimally invasive methods to preserve the integrity of the very evidence we so desperately seek to discover. Another complication is the potential geopolitical implications. Discoveries indicating the existence of highly advanced ancient civilizations could. Such discoveries have the potential to challenge the established histories of entire nations and their claims to some kind of cultural primacy in the ancient world. This raises legitimate concerns, as such stunning evidence could be used for political purposes or to advance certain ideologies. And here, more than ever, the importance of an international scientific community, transparent work, and research that undergoes the rigorous scrutiny of colleagues around the world becomes clear. The creation of uniform rules and deep respect for the sovereignty of the sites where unique archaeological treasures are found can help smooth over rough edges and guide research in a responsible direction. The very possibility of discovering traces of long-vanished worlds compels us to delve deeper into history and treat the planet's past with greater reverence. We must not forget our moral responsibility to those who come after us. Decisions about which finds to preserve, how to interpret controversial and incomplete data, and whether to publish potentially game-changing information all require a balanced and ethical approach. Paleontologists and archaeologists must constantly walk a fine line between an insatiable thirst for knowledge and a clear understanding of how their discoveries may impact society and nature. Our desire to peer into the deep past must be based not only on scientific integrity, but also on unwavering ethical principles. And the further our technology advances, the more pressing these questions of responsible study of the Earth's ancient record will become. Future scientific breakthroughs could dramatically change our ability to discover and interpret evidence of ancient life, particularly those forms that vanished, leaving behind few physical traces. With every advance in technology and scientific methods, we delve deeper into the mysteries locked within the geological strata and environmental archives of our planet. For example, incredible advances in high-resolution isotope analysis are opening up entirely new horizons for scientists. They are now able to detect subtle chemical anomalies that may indicate major past events, such as global climate change or mass extinctions, the traces of which would otherwise be indistinguishable from natural geological processes. Thanks to cutting-edge microscopic analysis techniques, such as high-powered electron microscopes and synchrotron radiation technology, we have the ability to peer into the very heart of fossil remains. We can examine the microstructure of bones, the nanomaterials found in ancient organic matter, and study fossilized tissues that clearly indicate a biological rather than geological origin. Entirely new scientific fields, such as astrochronology, which links geological strata with astronomical cycles, and geophysical visualization, are expanding our arsenal of tools and helping us gain a deeper understanding of our planet's history. These technologies promise to one day unlock the deepest mysteries of Earth's distant past. Imagine advanced seismic exploration enhanced by self-learning computer algorithms can uncover entire burial grounds of ancient animals or fossilized ecosystems that could force us to completely rethink our understanding of the chronology and very nature of life in prehistoric eras. These technologies help us distinguish natural geological formations from possible traces of ancient life, even in regions of the planet previously considered inaccessible or unpromising. These scientific breakthroughs are opening the way to a new understanding of Earth's history and its place in the universe. This compels us to continue our search with even greater persistence and responsibility. Moreover, the rapid advancement of computing power and analytical software is dramatically simplifying the processing of massive data sets. This allows us to uncover hidden patterns on a scale previously unimaginable. As a result, we have the potential to detect subtle signs of ancient biological activity, such as the global distribution of specific isotopic signatures or anomalous concentrations of certain minerals that may be associated with ancient ecosystems. The integration of complex climate modeling and paleoecological data also greatly enhances our understanding of how ancient animal communities interacted with their environments. This allows us to find indirect evidence of their existence and their impact on nature. As we expand the boundaries of our research, these innovations not only increase the precision and sensitivity of our work, but also open up entirely new horizons for data interpretation. The ability to more accurately date finds and assess their place in Earth history will be key to understanding and comprehending our planet's past. Distinguishing signals of ancient life from natural geological processes is a task that becomes increasingly difficult. However, thanks to advances in this field, we are gradually transforming speculative hypotheses into scientifically sound theories. This brings us closer to understanding the true scale and complexity of Earth's ancient history. Interdisciplinary research plays a crucial role in the search for traces of ancient life, especially when it comes to hypotheses that challenge conventional scientific views. This approach combines knowledge from a wide range of fields: geology, paleontology, archaeology, climatology, astrophysics, and genetics. This allows us to create a unified, comprehensive picture of Earth's distant past. Geologists and paleontologists provide invaluable information on ancient sedimentary rocks, isotopic markers, and fossil remains, which may contain traces of ancient biological activity or colossal environmental changes. These data open new avenues of discovery and help us better understand the evolution of life on the planet. Scientists are studying traces of ecosystems that existed millions of years before the advent of humans. Archaeologists, meanwhile, are developing innovative methods to search for hidden artifacts and structural anomalies that may lie deep within geological strata. These techniques often involve the use of advanced imaging technologies, such as ground-penetrating radar and remote sensing of the Earth from space. Climatologists are helping us reconstruct ancient climate conditions. Climate patterns and environmental shifts that influence the rise and fall of entire prehistoric worlds represent a fascinating area of research. Astrophysicists study cosmic events, such as giant asteroid impacts or solar flares, that may have left a permanent scar on the planet's geological record. Geneticists, meanwhile, are studying ancient DNA samples to reconstruct biological history and perhaps find evidence of certain plant and animal species associated with ancient ecosystems. Collaboration between different disciplines plays a key role in developing new methods, such as combining geochemical analysis with modern computer modeling. This allows scientists to distinguish natural phenomena from possible traces of biological influences in the geological record, giving us a more complete understanding of our planet's past. Dialogue between disciplines forces us to reconsider established assumptions, encouraging researchers to consider alternative explanations and refine hypotheses from different perspectives. Such mutually beneficial collaboration not only opens new horizons for research, but also makes its results more reliable, reducing the likelihood of errors and misinterpretations. The search for evidence of ancient worlds is intensifying day by day, and integrating diverse scientific fields is becoming essential for understanding new data in a broader context. Interdisciplinary research plays a key role here, linking disparate fields of science to solve the complex mystery of Earth's ancient history. This integrated approach greatly increases our chances of detecting the subtlest signals of long-extinct life forms, which in turn allows us to better understand the true history of our planet and the incredible potential of life that existed long before us. If the existence of complex prehistoric ecosystems in unexpected places and times is confirmed, it will fundamentally impact our views on the protection and conservation of the planet. By rethinking our perception of the Earth's resilience and vulnerability, we begin to understand that complex life forms and perhaps entire highly organized ecosystems existed long before the emergence of humans. This realization underscores the crucial importance of preserving the planet's deep history, not just its current state. This understanding has the potential to shift our very paradigm, shifting our focus from short-term environmental protection to longer-term integrated management that takes into account the Earth's entire geological and ecological record. One of the major consequences of this shift will be a more sensitive approach to preserving geological archives, rocks, fossil records, and sedimentary layers that contain traces of ancient life. Protecting these layers from contamination or destruction will become a priority, as they may provide crucial clues to understanding past planetary catastrophes, climate change, and the resilience of the biosphere. This discovery will spur the development of advanced monitoring technologies aimed at detecting the slightest changes or disturbances that threaten these ancient records. Moreover, the realization that ancient ecosystems may have significantly altered Earth's environment will force us to rethink the resilience of our own planet. This discovery may reveal that Earth systems are far more adaptive than previously thought, or conversely, more vulnerable to long-term impacts, whether from natural disasters or human activity. Therefore, future planetary conservation strategies will need to incorporate the lessons learned from these ancient events. Let's travel back in time and imagine the lessons our planet's stone record holds. Let's focus on how understanding ancient catastrophes helps us prevent irreversible damage today and build a wiser interaction with Earth's global systems. After all, the assumption that entire eras existed before us, where other forms of life reigned, forces us to look at our world in a completely new way. This idea could push humanity to create global rules for protecting planetary heritage, similar to the treaties that govern activities in outer space. A deep dive into Earth's history and its geological archives could unite the efforts of scientists from around the world. Their shared goal is to stop the environmental destruction that is irrevocably erasing valuable geological and paleontological evidence. This awareness can inspire unprecedented investment in interdisciplinary research, where geology, paleontology, and climatology work hand in hand. This will allow us to better understand how resilient and yet vulnerable our planet was over millions of years. Ultimately, recognizing that Earth was once home to incredible and complex ecosystems deepens our sense of responsibility. It reinforces our understanding that we must protect not only modern nature, but also the very historical fabric of our planet. We must ensure that future generations can learn from its deep past while preserving its life and all its splendor. Understanding the incredible depth of our planet's history opens up colossal opportunities that go far beyond mere scientific curiosity. By uncovering evidence of ancient worlds, we can learn from their experiences, from their rises and falls. By studying both extinct and modern biological communities, we gain invaluable insights into the resilience, adaptation, and incredible ingenuity of life itself. These lessons from the past can have a profound impact on how we address modern challenges, from species conservation to the development of new technologies. Firstly, studying ancient times significantly expands our understanding of long-term planetary processes. We're talking about climate change, continental movement, and atmospheric evolution. Understanding how the ancient biosphere responded to past natural disasters helps us create more accurate models predicting future climate change. This, in turn, allows us to develop far more effective survival strategies. For example, evidence of how ancient ecosystems recovered from asteroid impacts or massive volcanic eruptions can inspire us to create innovative engineering solutions that mimic natural adaptation mechanisms. Moreover, studying the biological technologies of past eras, so to speak, can unlock the secrets of the evolution of complex systems. Just imagine, if we discover that ancient ecosystems developed incredibly efficient ways of using energy or recycling resources, this could become a source of inspiration for solving our energy problems. This knowledge completely shatters the notion that complexity and efficiency are recent inventions. It opens our eyes to the potential longevity and genius of evolutionary solutions. Studying Earth's ancient history fosters a sense of humility and a deep appreciation of the interconnectedness of all life. Understanding that dominant species like dinosaurs may have existed long before us and ruled the planet for 150 million years highlights how fleeting any species' dominance can be. This perspective can influence our values, shifting our focus from immediate gain to long-term planning and sustainable development. In practice, the very methods developed to find and analyze ancient evidence, such as advanced geochronology, remote sensing, and sophisticated data modeling, drive technological progress that benefits many industries. These innovations are finding applications in resource exploration, environmental monitoring, and even space exploration. Overall, understanding Earth's deep past doesn't just enrich our scientific knowledge, it facilitates technological development and shapes thinking aimed at survival and prosperity in the future. By continuing to uncover the hidden pages of our planet's history, we not only uncover the secrets of ancient worlds, but also pave the way for a more informed and secure future for ourselves. Finding traces of ancient life is an incredibly challenging task, both from a geological perspective and given the limitations of our research instruments. Unlike archaeological excavations of the recent past, where artifacts and ruins are relatively close to the surface, discovering traces of life that existed hundreds of millions of years ago is immeasurably more difficult. One of the main obstacles on this path is time itself, the great destroyer. The Earth's crust is in constant flux. Tectonic activity, relentless erosion, and the accumulation of kilometers-thick layers of sedimentary rock, all this either reliably conceals or completely destroys any potential evidence. Imagine, what was once the surface could now lie several kilometers deep or be molten in the Earth's mantle. Moreover, paleontologists must look for highly specific signs: anomalous chemical markers in rocks, unusual mineral deposits that could only have formed with the participation of living organisms. These traces are often incredibly difficult to detect and even more difficult to distinguish from the results of ordinary geological processes. For example, some chemical compounds left over from the decomposition of ancient organisms can be very similar to substances of inorganic origin, making their identification incredibly difficult. Solving this puzzle requires cutting-edge methods, high-precision spectroscopy capable of detecting the smallest chemical anomalies, and deep drilling to peer into the planet's interior. However, such methods are limited by their colossal cost and scale. We cannot drill through the entire planet in search of remains. Another critical issue is the temporal resolution of our geological record. Earth's rock record resembles a book from which entire chapters, if not volumes, have been torn out. Many potential traces of ancient life have been erased or buried so deeply that we will never be able to retrieve them. Our planet's surface is a dynamic, constantly changing arena. Volcanic activity can bury entire ecosystems under a layer of ash and lava. Subduction, the process by which one tectonic plate subducts beneath another, literally pulls ancient rocks into the planet's molten core, destroying them forever. This makes discovering definitive evidence incredibly difficult. Moreover, the enormous time gap between the age of dinosaurs and the present day means that any evidence we are fortunate enough to find has likely undergone significant changes. Fossilization, deformation, and chemical substitution all complicate their accurate interpretation. Finally, our overall understanding of Earth's ancient history remains incomplete. The deeper we peer into the past, the more fuzzy and fragmentary our data becomes, and the more we must rely on circumstantial evidence and scientific hypotheses. This uncertainty only underscores the importance of developing new technologies and approaches that integrate geology, chemistry, and biology to improve our chances of peering into long-vanished worlds. The search for traces of ancient life, especially that which existed before the advent of humans, faces seemingly insurmountable obstacles. Chief among these are the vast time spans involved, spanning more than 4.5 billion years of Earth's history. During this time, any possible signs of ancient ecosystems were subjected to constant geological transformations, reliably concealing or completely obliterating their traces for entire eons. Unlike archaeological finds, which can be carefully excavated and studied, ancient fossils buried in the Earth's crust had to withstand the onslaught of incredible natural forces. Just imagine, crushing shifts of tectonic plates, centuries of erosion, the pressure of thousands of tons of sediment, and complex chemical transformations. These processes can alter or completely erase any evidence beyond recognition, making it virtually impossible to distinguish a fossil from ordinary rock with the naked eye. Moreover, the very duration of these processes creates a major problem. Our geological archives will always be incomplete. The Earth's crust is continually renewed. Old rocks are remelted in the mantle, and new ones are formed in their place. This can lead to entire layers of history containing dinosaur remains simply disappearing from the face of the Earth. As a result, physical evidence, such as skeletons, teeth, or skin impressions, is extremely rare and almost always in fragments. This lack of data makes it difficult to establish precise timelines or determine what a given species looked like, especially when the original forms of bones or shells can be reduced to obscure mineral formations. The situation is further complicated by the slow pace of geological processes, which not only destroy, but also transform traces of the past, literally fusing ancient remains into the Earth's geological system. For example, if dinosaur bones were buried in an environment rich in certain minerals, these minerals could completely replace the organic matter over millions of years, leaving only an exact stone replica. But their chemical composition has now become part of the surrounding rock. Traces of life become literally indistinguishable from inanimate matter. Even isotopic signatures that could indicate a biological origin can become obscured over time due to diffusion and mixing within the planet's interior. This vast time gap is a chasm separating us from the world of dinosaurs, and peering into it becomes increasingly difficult with each passing million years. Imagine trying to read a book with only a few faded, torn pages remaining. This is precisely the challenge scientists face when they attempt to peer into our planet's deep past. The abyss of time, measured in hundreds of millions of years, poses a nearly insurmountable barrier, limiting our ability to find and, more importantly, correctly understand traces of hypothetical ancient civilizations. This monumental problem is forcing paleontologists and geologists to develop increasingly sophisticated and sensitive search methods. Their goal is to detect subtle anomalies hidden within the strata of geological formations, like quiet whispers from a bygone era. Yet, the sheer length of Earth's history remains a major obstacle. We are forced to ask not only what might have survived in this stone record, but also what colossal portion of the ancient world was forever erased from the face of our planet as its surface constantly churns, shifts, and rewrites itself. Even the most advanced dating and analytical technologies we boast about today are stymied by this challenge. They face incredible challenges when it comes to detecting and confirming traces of technologies that may have existed long before the advent of humankind. Take, for example, radiometric methods, our magic clock for peering into the past. Approaches like uranium lead or potassium argon dating work flawlessly when it comes to dating rocks or fossils. They rely on precise measurements of isotope ratios in mineral crystals, but their effectiveness plummets when we try to find traces of technological activity buried in geological layers. Why is this? It's simple. Such traces, whether remnants of metal or synthetic materials, become unstable over time, change their chemical composition, and become virtually indistinguishable from natural formations. Trying to detect microscopic particles of an ancient alloy or composite within the rock mass becomes a real puzzle. These signals from the past may be too weak, chemically elusive, or so altered over millions of years that we simply don't see them. There are other sophisticated methods too. For example, thermoluminescence, which can tell us when a particular mineral was last exposed to heat or sunlight. But even this has its pitfalls. These methods have a sensitivity threshold, and any subsequent geological events associated with heating can completely reset their readings, erasing valuable information. Imagine an ancient artifact buried underground. Over millions of years, its original appearance will be distorted beyond recognition. Geological processes like a giant mixer mix, compress, and melt the layers of rock, erasing or so altering any artificial signals that they become indistinguishable from ordinary stone. Of course, scientists have powerful tools at their disposal: spectroscopy, microscopy, and isotope analysis. They can detect chemical anomalies or traces of synthetic substances, but even here, we hit a wall. Contamination of samples, the extremely low concentration of the elements being sought, or the incredible difficulty of separating the artificial signal from the natural background. All of this reduces the chances of success to a minimum. Consider this. Detecting barely noticeable traces of a metallic alloy in ancient sediments at depths of several kilometers requires measurements of exceptional precision. But how can these measurements be made if the material itself has undergone colossal destruction at the molecular level over tens of millions of years? Moreover, the resolving power of many of our instruments simply doesn't allow us to detect tiny, localized technological traces, especially if they are scattered over vast areas or chemically fused with the surrounding environment. Yes, cutting-edge methods like scanning electron microscopy offer incredible detail, but they are useless if we don't have the actual sample to study, or if that sample has been altered beyond recognition after burial. All these limitations lead us to one fundamental problem. Perhaps our current scientific tools are simply not sophisticated enough to reliably find evidence of technological civilizations that could have flourished long before the human era. The combination of subtle traces, the relentless decay of matter over time, and the imperfections of our technology creates a virtually insurmountable barrier to solving this greatest mystery. But that's not all. Nature itself, the geological and biological processes of our planet, seem to be actively covering their tracks. For millions of years, the face of the Earth has been constantly changing. Tectonic activity, like a giant sculptor, has reshaped the continents. Imagine these powerful forces, giant crustal plates colliding, forming mountain ranges, or, conversely, one plate sinking beneath another into the fiery bowels of the planet, carrying with it everything that stood on the surface. These processes are capable of burying or melting any remnants of ancient civilizations, erasing the slightest hint of their existence. What about volcanoes? A massive eruption can cover vast areas in meters of ash and lava in a matter of hours. And what about erosion? Tireless winds, like giant sandpaper, grind mountains into dust. Water and glaciers mercilessly scrape the surface, scattering and destroying any material evidence. And this is where biology comes into play. A whole army of invisible destroyers, microbes, tirelessly decompose organic matter. Plant roots, penetrating deep, disrupt the structure of fines. On the scale of geological time, materials such as wood, fabric, or even bone are doomed to decay. Their preservation is possible only under unique, ideal conditions, for example, the complete absence of oxygen or instant burial. But such conditions are extremely rare. In the overwhelming majority of cases, any organic artifacts either degrade beyond recognition or disappear without a trace. Chemical processes also play a role. Mineralization and leaching alter or simply dissolve potential markers of the past. Groundwater movement can leach organic molecules from rock or dissolve minerals that could preserve traces of ancient structures. Over millions of years, chemical weathering will transform any artificial object into something indistinguishable from ordinary stone. As a result, the Earth's sedimentary record, which could be our primary source of knowledge, is in fact a chaotic mosaic of incomplete and distorted fragments. Rock layers are constantly eroded, mixed, and deposited unevenly, making the discovery of clear and consistent evidence virtually impossible. If highly advanced civilizations existed, their traces should have remained in this chronology. However, the inexorable filter of natural geological and biological processes erases or obscures this evidence, presenting scientists with a nearly impossible task. Finally, there's another, perhaps the most powerful barrier: our own prejudices and assumptions. One of the main pitfalls is anthropocentrism, our tendency to regard human civilization as the pinnacle of creation and the only possible example of advanced life. This view through the keyhole of our own experience can lead researchers to simply overlook or ignore evidence that doesn't fit into their conventional picture of the world. This approach leads scientists to interpret any geological anomalies solely in terms of natural processes known to them without even considering alternative hypotheses. This human centrism is a powerful inhibitor, preventing the search for evidence that contradicts traditional beliefs. Many scientific models assume that the emergence of a technologically advanced civilization is an extremely unlikely and short-lived phenomenon. This mindset itself hinders the search for subtle or indirect signs of the existence of something before us. This skepticism even influences scientific funding, directing resources toward traditional research and leaving behind bold interdisciplinary projects that could lead to breakthroughs. Added to this is the so-called confirmation bias, an insidious mental trap. Researchers, sometimes unconsciously, favor data and interpretations that confirm existing scientific theories. As a result, anomalies that don't fit into the overall picture are often dismissed as measurement errors or statistical noise, even though they may be the key to a great discovery. Our perceptions are also distorted by misconceptions about the geological record itself. Many believe that the layers of the Earth's crust are a perfect archive, neatly arranged and well preserved. But they forget the dynamic nature of our planet: erosion, tectonics, sedimentation. All of this constantly destroys and scrambles the pages of this stone book. Another misconception is the belief that any technological traces can be easily detected with our modern instruments. But this assumption ignores the possibility that ancient technologies may have been based on entirely different principles or used materials that don't leave lasting traces. Finally, we are weighed down by cultural and social norms. The traditional view of Earth's history describes it as a series of gradual natural events. This reduces our willingness to embrace radical ideas, such as the existence of intelligent life before the emergence of humans. Taken together, all these biases and assumptions create a powerful mental barrier that prevents us from even beginning to search in the right direction. Imagine trying to solve history's greatest mystery, but our own minds are blocking us from seeing the clues. There are invisible mental barriers that can prevent even the most impartial researcher from developing the truly revolutionary methods needed to test bold hypotheses about the past. Recognizing and overcoming these mental traps, these methodological impasses, is the key to an objective and comprehensive scientific view of the most intriguing mysteries of the ancient world. Testing the boldest assumptions about prehistory requires the collaboration of the greatest minds from completely different fields of science. The task is so enormous that it cannot be accomplished alone. It spans numerous disciplines. Geology, which reads history from layers of rock. Paleontology, which resurrects ancient monsters from their bones. Archaeology, which searches for traces of activity. Climatology, which recreates the weather of bygone eras. And even astrophysics, which studies cosmic events that influenced life on Earth. Combining knowledge from all these fields allows us to take a much broader and deeper look at the problem in our search for evidence. Such collaboration generates unique methods, combines enormous data sets, and builds new theoretical bridges. Together, they help us hear the quiet signals that can be detected deep within the history of our planet. Let's imagine this team in action. Geologists and paleontologists can work together to study geological sections, refining stratigraphic analysis to identify anomalous layers, strange interlayers that may hint at unusual activity or past global environmental catastrophes. Archaeologists, with their invaluable experience in finding artifacts and conducting excavations, can apply their skills to a whole new level, helping to uncover the material evidence left behind by ancient life. With their help, we can better understand how to search for possible hidden or time-eroded remains, if such exist at all. Climatologists, for their part, can use supercomputers to model ancient environmental changes that could have either obscured or, conversely, preserved this invaluable evidence. And astrophysicists can study the traces of extraterrestrial impacts, such as giant asteroid impacts, which could have coincided with periods of flourishing or, conversely, the total extinction of ancient life forms. This approach takes us beyond purely terrestrial data and provides a much broader cosmic context for our understanding. This interdisciplinary approach to uncovering the mysteries of the past also facilitates the development of entirely new analytical methods. For example, breakthroughs in isotope analysis, remote sensing technologies, and ultra-high-resolution imaging are often the result of collaboration between various scientific institutions. These tools open new horizons for research and discovery. They can detect the faintest chemical signatures or structural anomalies in rocks, indicating vigorous biological activity, even hundreds of millions of years after it ceased. Moreover, dialogue between different disciplines forces scientists to critically rethink established dogmas, such as the timescales of geological processes or the stability of certain environmental markers. This helps us better understand the past world. To avoid biases that could lead our research down a dead end, we need to combine our efforts. This will give us a deeper insight into Earth's history and greatly increase our chances of discovering subtle or indirect evidence. Moreover, collaborative research will enable the development of comprehensive projects and large-scale expeditions that can encompass all aspects of the problem. Combining diverse scientific approaches will not only expand our research capabilities, but also enhance the reliability of our interpretations. This will bring us closer to uncovering the truth and perhaps forever change our understanding of the history of life on Earth. Such collaborative work prompts us to consider how technological breakthroughs can further expand the horizons of our research, allowing us to analyze and interpret colossal volumes of data. Technological advances are playing a key role today in discovering and interpreting evidence of ancient life, especially that which flourished long before the advent of humans. In recent decades, advances in analytical methods have revolutionized our capabilities. We have learned to study the Earth's geological and biological archives to a level that allows us to discover subtle traces that were previously completely invisible. For example, high-precision radiometric dating methods such as uranium-lead and argon-argon analysis have allowed us to calibrate the chronology of Earth's history with incredible precision. This allows us to identify anomalies, events that may indicate unusual bursts of activity or global disruptions caused by the rise or fall of ancient ecosystems. Studying ancient worlds with modern technology opens up entirely new horizons in understanding the past. Research into unusual patterns of activity or global disturbances is becoming increasingly fascinating. Advances in geochemical analysis, such as assessing isotopic ratios in ancient rocks, have opened up new possibilities for identifying traces of the ancient biosphere. Anomalous isotopic ratios, or the presence of rare elements in unusual concentrations, can act as indirect indicators of biological activity. This allows us to more accurately perceive the echoes of ancient processes that took place millions of years ago. Furthermore, advances in sedimentary rock analysis, including scanning for microscopic fossils and nanostructures, are helping us identify evidence of life's powerful impact on its environment. This evidence may include nanoscale organic remains or unusual mineral formations that previously remained undetected. Rapid advances in remote sensing technologies, including satellite imagery and deep geophysical surveys, have significantly increased our ability to search for traces of ancient worlds. These tools allow us to identify large-scale anomalies, hidden subsurface structures, unnatural geological formations, and disturbed layers that may indicate the presence of gigantic ancient ecosystems. With the increasing resolution of sensors and the introduction of machine learning algorithms capable of detecting subtle patterns in the landscape, our chances of discovering signs of ancient life have increased significantly. Interdisciplinary approaches combining paleontology, geology, and even astrobiology are dramatically expanding our horizons. For example, analyzing the flow of extraterrestrial material or isotopic changes in rocks caused by cosmic rays can provide valuable information about our planet's past. With modern technology, we are able to detect even the most indirect evidence. As technology advances and our ability to interpret complex signals advances, we are rethinking the entire history of life on Earth. Technological advances continually push the limits of what we can detect, interpret, and ultimately understand about our planet's distant past. However, this progress also forces us to consider the limitations and potential biases that may be built into our research methods. The quest to understand Earth's deep past faces not only scientific and technological challenges, but also serious philosophical barriers. Epistemology, the study of the nature of knowledge, raises crucial questions. What can we truly know about the past, and how reliably can we interpret ancient signals imprinted in the geological record? These limitations stem from the very nature of the fossil record. Think of it not as a complete book, but as a few torn, charred, and soggy pages. It is a fragmented, biased, and constantly changing document, exposed to the Earth's relentless geological processes over millions of years. One of the fundamental philosophical problems is the problem of inference. Much of our knowledge about ancient life is based on indirect, not direct evidence. For example, to identify traces of a hypothetical ecosystem that existed millions of years ago, we interpret geological anomalies, isotopic signatures, and microfossils. However, these signatures often prove ambiguous and can easily be explained by natural geological phenomena unrelated to life. This raises a fundamental question. Are our modern scientific methods capable of effectively distinguishing between genuine traces of ancient life and natural formations that merely masquerade as such? This is the limit of knowledge that underlies all our observations and interpretations. Furthermore, the distant past is shrouded in what some philosophers call a fundamental horizon of knowledge. The deeper we look into the past, the more rapidly our ability to obtain reliable knowledge declines. Erosion, tectonic processes, and sedimentation continually destroy or obscure potential evidence, creating a natural barrier similar to the event horizon of a black hole, but on a geological scale. This implies that some truths about the earliest epochs of Earth may forever remain beyond our comprehension. This is not only due to technological limitations, but also to the very nature of time and matter. Moreover, our scientific paradigms, our ways of thinking, are shaped by modern knowledge and technology. This forces us to assess our capabilities with a certain degree of humility. After all, with the development of new methods, such as advanced isotope analysis or deep Earth scanning, we may in the future reconsider or even completely overturn ideas that seem unshakable to us today. But let's be honest, are there limits to our knowledge? It's entirely possible that some pages of the great book of Earth's history have been torn out forever. They lie beyond the horizon of what we humans are capable of seeing or understanding. This philosophical limit shouldn't quench our curiosity. On the contrary, it serves as a constant reminder of humility. These very boundaries define our vision of what can possibly be known about our planet's hoary past. And they also drive us to a relentless search for new knowledge, new astonishing discoveries. And as we reflect on how we read the Stone Chronicle, it's important to remember we mustn't be overconfident in our final verdicts. When we search for the ghostly remains of civilizations lost in the abyss of time, we face not only scientific, but also profound ethical dilemmas. These include scientific integrity, respect for other cultures, and the impact our findings will have on the world. Researchers who delve into geological strata in search of these forgotten chapters in Earth's history must fully understand the weight of moral responsibility for their discoveries and their interpretation. Imagine the enormous responsibility this entails. One of the greatest dangers along this path is the trap of misinterpretation. What if vague, nebulous data is mistaken for irrefutable proof of intelligent life? Unless such conclusions are subjected to the rigors of scientific scrutiny and explained with utmost clarity, they could spark a wave of misinformation. This could distort public opinion and the scientific debate, ultimately undermining trust in science itself and its authority. This is why it is vital that any such research be conducted according to the strictest standards and methodologies, and that its results be completely transparent and supported by ironclad evidence. However, even the mere publication of preliminary unconfirmed evidence can cause a genuine sensation or trigger a flurry of unsubstantiated speculation. Moreover, the very idea of discovering traces of a civilization that flourished long before the first humans emerged has the potential to shake the very foundations of our cultural and religious beliefs. For some societies, such a discovery could be a true earthquake, challenging fundamental beliefs about humanity's uniqueness in the history of the universe, triggering intense resistance or outright denial. On the other hand, for others, such discoveries could serve as a source of inspiration, a stimulus to rethink our origins. It could teach us humility and give us a deeper sense of connection with Earth's incredibly distant past. Respect for the diversity of cultural views is of paramount importance here, especially when we are dealing with artifacts or symbols that may be interpreted very differently in different traditions. And here we come to another pressing ethical issue: how to preserve and manage ancient monuments and artifacts if they are found. Let's imagine for a moment that we have such evidence in our hands. We would immediately need to develop an entire system for their protection and conservation. And the key question immediately arises: who will have access to these finds? Who will study them? Who will be able to display them for public viewing? It will be necessary to find a delicate balance between the insatiable thirst for scientific discovery and respect for the cultural or spiritual significance these monuments may hold for certain peoples or communities. Furthermore, we are constantly threatened by activities that could cause irreparable harm to the environment or lead to simple exploitation. The tantalizing prospect of discovering ancient civilizations could lead to the plundering of their habitats, and priceless artifacts could end up on the black market. This would not only destroy their historical value, but also demonstrate extreme disrespect for the cultures with which they are associated. To prevent such barbarity, it is vital to establish clear ethical rules and foster international cooperation. In some situations, our quest to discover ancient, possibly pre-human civilizations is inextricably linked to ethical challenges that require the most careful and thoughtful analysis. Responsible research must rest on three pillars: scientific integrity, respect for culture, and the preservation of our shared heritage. Only in this way can we enrich our shared understanding of Earth's ancient history, rather than irreparably damage it. Just imagine how the potential discovery of a civilization that existed millions of years before the first humans could upend our entire understanding of ourselves and our culture. It would force us to completely rethink our place in the grand story of our planet. For centuries, humanity has seen itself as the pinnacle of creation, the pinnacle of the evolutionary tree, or a unique product of life's development. But what if irrefutable evidence suddenly emerged that intelligent life, or even technologically advanced societies, existed long before us? This discovery could shatter the idea of human exceptionalism and deepen our understanding of the resilience and continuity of life itself. Such a transformation could teach us humility, showing us that humanity is just one chapter in a much larger, perhaps cyclical and multi-layered evolutionary saga. Culturally, recognizing the ancient civilizations that preceded our own could trigger tectonic shifts in mythology, religion, and philosophy. Ancient myths could be revived, filled with echoes of long-forgotten worlds. Religious doctrines that emphasize divine creation could be enriched by stories of great cosmic or planetary cycles of destruction and rebirth. This broader perspective could highlight the importance of responsibly managing our world, recognizing that human civilization is merely a link in the endless chain of life on the planet, not its absolute beginning. Moreover, the very idea of ancient, possibly technologically advanced societies that existed long before humans could inspire us to reassess our own scientific and technological paths. It raises perennial questions about the rise and fall of civilizations and the fragility and sustainability of technological progress. Such reflections could influence future development strategies for our society, emphasizing the importance of restraint and caution in our technological ambitions. On a psychological level, the discovery of ancient civilizations has the potential to greatly enrich our understanding of the diversity of intelligence and its cultural manifestations. This could deepen our understanding of what civilization and progress truly are. Moreover, such a discovery could help us shed egocentric views and embrace a more comprehensive view of the world, recognizing the full complexity of the universe at different times and under different conditions. However, faced with these dizzying conclusions, we are faced with a crucial question. What is our priority? Should we focus on preserving potential excavation sites and artifacts from these ancient civilizations, protecting their secrets for future generations? Or should we continue active searches to uncover their secrets and better understand their history as quickly as possible? This dilemma highlights the importance of finding a balance between respect for the past and the indefatigable curiosity that drives all scientific discovery. For our pursuit of knowledge to remain ethical, we must consider the profound implications for human identity and cultural narratives when we intrude upon ancient sites and handle their artifacts. This raises a serious conversation about how to balance curiosity and responsibility in science. So, which should we choose, preservation or research? Both paths are of enormous importance, especially when we consider potential discoveries that could rewrite our understanding of history and the very concept of civilization. The thirst for discovery drives us to search for ever new clues, expanding the horizons of our scientific understanding. Modern technologies are our arsenal in this hunt for knowledge. Remote sensing, which allows us to peer beneath the Earth's surface, high-precision visualization, and geochemical analysis, help us discern subtle signs that would previously have gone completely unnoticed. These efforts have the potential to dramatically enrich our knowledge of the planet's past, revealing the complex relationships between natural processes and possible traces of ancient technologies. However, this pursuit of knowledge is fraught with enormous risks. During archaeological excavations in the heat of the moment, there's a real risk of damaging fragile objects, forever destroying their original context. Without context, any find is just a beautiful trinket, devoid of its history. Uncontrolled excavations can lead to ordinary natural formations, be they mineral deposits or geological anomalies, being mistaken for artifacts of ancient civilizations. The pursuit of sensationalism can undermine scientific objectivity, especially if preliminary, incompletely verified results are distorted or exaggerated. This can lead to false understandings of the history of our world. On the other hand, the priority of preservation underscores our ethical obligation to protect objects from deterioration and maintain scientific integrity. Conservation of artifacts allows future technologies and methods to conduct more accurate data analysis. At the same time, the context of the find remains intact, allowing for its accurate interpretation. This also helps preserve priceless evidence of the past for future generations. Avoiding hasty conclusions that could mislead the public or become the basis for pseudoscientific theories is the foundation of a balanced approach. While research is absolutely essential to advancing our knowledge, it must be conducted in strict accordance with scientific protocols and with the utmost respect for the subject matter. Maintaining context, essential for adequate interpretation, helps avoid gross errors in conclusions and sensational claims that can arise from hasty and ill-considered actions. Maintaining this delicate balance is the only guarantee that our pursuit of knowledge will remain responsible and scientifically sound. And herein lies its particular significance. Imagine how fragile and precious the record of our planet, written in stone, is. When we speak of millions of years, of long-vanished worlds, preserving the integrity of our understanding of this profound history becomes paramount. Any misinterpretation, any distortion of data related to ancient life can entail risks that go far beyond mere scientific inaccuracies. They can trigger a cascade of social and cultural consequences. Often, incorrect conclusions arise from what's known as confirmation bias. This is a mental trap whereby a researcher, without realizing it, begins to selectively select ambiguous facts to fit their own preconceived theories. The result is a distorted picture of the past, capable of profoundly misleading not only the general public, but the entire scientific community. Overestimating the significance of a tiny bone fragment or an obscure geological imprint can give rise to entire false paradigms, undermining the very foundations of the scientific method. This diverts precious resources, time, and effort from truly promising and sound research areas, and the pursuit of sensationalism only exacerbates this danger. Imagine this. Preliminary, unverified excavation results are presented as irrefutable proof of the existence of a previously unseen superpredator, changing our entire understanding of the ecosystem. Unfounded media hype immediately erupts. This approach not only sows misconceptions among millions of people, but also deals a crushing blow to public trust in science itself. After all, when subsequent, more thorough studies fail to confirm the initial claims, all that remains is disappointment and skepticism. Moreover, misinterpretations of past events can have unexpected cultural repercussions. When the discovery of a new dinosaur species or an entire prehistoric ecosystem is linked to a specific geographic region, it can paradoxically become a tool for strengthening nationalist sentiments or fueling ingrained stereotypes. On the other hand, complete denial or deliberate disregard of irrefutable facts due to cultural or religious biases can hinder genuine scientific progress for decades. This creates impenetrable intellectual dogmas that stifle critical thinking and prevent new, revolutionary ideas from gaining ground. For example, some religious doctrines may perceive the very idea of life existing on Earth millions of years before humans as a direct contradiction to sacred texts on creation. This leads to the categorical denial or disregard of any paleontological evidence that would seem to undermine deeply held beliefs. The penchant for sensationalism leads to another problem. Genuine, fundamental discoveries are perceived with less seriousness. Complex paleontological and geological phenomena are reduced to simplified, flashy stories that lose all important details and nuances. This only undermines public understanding of the scientific process itself, fostering unhealthy skepticism instead of deserved recognition of the titanic work of scientists. When evidence is distorted, the line between credible science and Hollywood blockbuster entertainment becomes dangerously blurred. This makes it incredibly difficult to convey the importance of rigorous methods, data verification, and careful, balanced interpretation. Ultimately, the threat of misinterpretations and cheap sensationalism only underscores the vital need for rigorous analysis, independent expert review, and the utmost responsibility in approaching any scientific discovery. Understanding the cultural and social dynamics surrounding these discoveries is the foundation for open and honest dialogue. A dialogue that respects diverse perspectives but does not allow for the distortion of objective scientific data. Cultural and religious beliefs have a profound impact on how society perceives scientific hypotheses, including the very possibility of worlds that predate humanity. When new evidence emerges, whether unusual geological formations, fossilized footprints, or fossil remains that point to a history beyond our species, it is society's ingrained views that determine whether these ideas are enthusiastically embraced or dismissed outright. In many cultures, religious doctrines have for centuries emphasized the uniqueness of humans and the divine nature of creation. This naturally generates skepticism toward any hypotheses that challenge these fundamental concepts. For example, within the traditional Abrahamic religions, geological anomalies or the bones of giant lizards could, for centuries, be perceived as signs of divine providence, traces of the biblical flood, or the bones of fallen giants, but in no way as proof of the existence of ancient ecosystems. However, there are other, much more ancient worldviews that view such discoveries entirely differently. They view strange stone impressions or gigantic bones as traces of ancestral spirits or evidence of the ancient wisdom of the earth. This perspective opens the door to the idea that our planet may have been home to other incredible life forms that dominated it long before the advent of humans. Cultural narratives also shape both scientific discourse and public opinion. Imagine a society dominated by strict scientific skepticism or authoritarian control of knowledge. In such an environment, any unconventional hypotheses that go beyond the pale would be immediately rejected simply to maintain ideological purity. On the other hand, cultures with a rich mythological tradition, rich in tales of dragons, sea serpents, or vanished worlds, may be much more receptive to new paleontological discoveries. New scientific data then seamlessly integrates into an already familiar spiritual or philosophical context. Religious and cultural traditions can influence even such pragmatic matters as research funding, the setting of scientific priorities, and how scientists communicate their work. When discoveries conflict with society's core beliefs, this inevitably leads to social and cultural resistance. Institutional pressures can seriously hinder open research and even lead to the suppression or concealment of controversial evidence. Conversely, a community that views scientific research as a way to better understand the grandeur of the universe and complement its spiritual worldview can foster more open dialogue and encourage scientific curiosity. It's crucial for scientists to recognize the powerful influence cultural and religious perspectives have on their work. This underscores the crucial importance of sensitive, transparent, and respectful communication, one that respects people's worldviews while presenting the facts objectively and honestly. Engaging with cultural context can foster greater acceptance and understanding, especially when hypotheses about ancient worlds and their inhabitants challenge conventional wisdom. As science advances, acknowledging these diverse perspectives helps foster a more inclusive and respectful dialogue. This is essential for expanding our shared understanding of the history of life on Earth and our own place in this grand picture. Scientists bear a profound moral responsibility for how they present their discoveries about ancient worlds. This responsibility becomes especially acute when their findings contradict accepted theories or have the potential to fundamentally alter society's perception of history. Evidence of the existence of long-vanished ecosystems, obtained through the analysis of geological anomalies, the study of micro-remains, and the use of modern detection methods is becoming increasingly compelling. Here, researchers must walk a fine line, balancing scientific integrity with public outcry. Achieving this balance between the passion for research and the need to preserve the planet's heritage requires clear ethical principles and close collaboration between scientists from a wide range of fields. Any fieldwork should be conducted using minimally invasive methods, meaning those that cause the least harm. This could include non-destructive scanning or remote sensing, which reduce the risk of damaging unique fossils or entire rock layers. For example, technologies such as aerial LiDAR scanning or ground-penetrating radar make it possible to peer underground and study hidden structures without resorting to large-scale destructive excavations. This preserves the invaluable context of discoveries for future generations of researchers who may have even more sophisticated tools. Furthermore, any information obtained must undergo rigorous peer review and reproducibility testing to avoid hasty or sensational conclusions. Conservation, in turn, requires the implementation of uniform international standards for the protection of unique geological and paleontological sites, particularly those that may contain traces of entire prehistoric ecosystems. This includes the development of strict protocols that will govern access to such sites, prevent commercial exploitation and vandalism, and ensure their integrity for future research. For example, the creation of global inventories of potentially important sites, similar to those used for UNESCO World Heritage Sites, could help protect these fragile windows into the past from destruction. Cultural and religious sensitivity must also always remain a top priority. Scientists are obligated to engage with local communities on whose lands excavations are conducted and consider their worldviews when interpreting and presenting their findings. This may include organizing public hearings and educational programs to simply and clearly explain the significance of discoveries and their potential impact on people's cultural beliefs. Transparent communication, underpinned by scientific rigor, will help minimize the risk of misinformation and maintain the highest level of public trust. Ultimately, the choice between preservation and research should not be an either-or dilemma. An integrative approach that combines responsible research with careful preservation will allow us to expand the boundaries of knowledge without destroying the Earth's invaluable geological and cultural history. This requires global cooperation, ethical stewardship, and a deep understanding that our quest to understand the past must respect both scientific truth and the cultural diversity of all humanity. The importance of transparency in science cannot be overstated. Scientists must formulate their conclusions with crystal clarity, always honestly acknowledging potential inaccuracies, data gaps, and methodological limitations. This is the only way to avoid misinterpretations of their work. Presenting research results to the public without properly accounting for all uncertainties will inevitably lead to misconceptions, media sensationalism, and unfounded fears. At the same time, underestimating or ignoring truly intriguing anomalies can hinder scientific progress and weaken healthy public interest in understanding the world. Striking a balance between these two extremes requires thorough peer review, rigorous verification, and completely open discussion within the scientific community, even before the results are presented to the general public. Imagine how powerfully a single discovery can shake the entire scientific world. When paleontologists discover something that upends our understanding of ancient life, they must understand the weight of responsibility that falls on their shoulders. After all, we're talking about more than just bones buried in stone. A discovery proving, for example, complex social behavior in dinosaurs, which we've come to regard as primitive, can shatter decades of theories, It could cast a shadow on established scientific dogma, force textbooks to be rewritten, and even change how we view the evolution of life on our planet. Therefore, scientists working at the forefront of paleontology must be prepared for such upheavals. They must not only make discoveries, but also serve as communicators of this new knowledge for the entire society, fostering a well-informed and balanced dialogue. It is crucial to join forces with geologists, biologists, and other specialists. Only in this way can we be sure that interpretations of new, stunning discoveries will be complete and respectful of the Earth's grand history. When we discover traces of life that existed long before the advent of humans, the question arises: how to tell this story correctly? How to weave it into the existing picture of the world? Researchers must choose their words with the utmost care, lest their findings generate false sensations or unhealthy debates within the scientific community. The dissemination of such revolutionary knowledge should bring the light of enlightenment and spark curiosity, not sow panic or strife between scientific schools. A responsible approach requires crystal clarity and precision in presenting the facts. This should inspire further research, while at the same time deeply respecting the impact these discoveries will have on our understanding of the past. The discovery of unique fossils, entire ecosystems frozen in time, inevitably raises pressing questions related to the management, protection, and even ownership of this priceless heritage. Such finds can become a bone of contention as they involve the interests of various countries, scientific institutions, and even private collectors. This is especially true if unique fossils or entire bone strata are discovered on international borders or in territories considered the heritage of a particular people. The preservation and study of archaeological and paleontological sites is always closely intertwined with questions of sovereignty, national pride, and cultural identity. The discovery of evidence of even more ancient and complex life forms could only exacerbate these latent conflicts. It challenges conventional wisdom and could spark debates about whose scientific legacy is more significant. Consider the so-called Silurian Hypothesis, which suggests that traces of ancient activity could have been reliably hidden in the Earth's deepest geological strata. In such a scenario, the stakes skyrocket. The possibility of finding something that defies conventional paleontology will spark heated debates about how to classify and study it. Some countries or scientific groups may claim exclusive rights to such finds, considering them part of their national heritage. Others will insist that they belong to all humanity and should be open to the international scientific community. These disputes could flare up again if fossils are found in disputed territories or if the discovery itself is perceived as a threat to someone's scientific authority. Moreover, commercial interests can also interfere with this complex game. Extraction of minerals or the development of tourist infrastructure can completely confuse everything. Powerful economic forces emerge that can either promote the preservation of unique places or push them toward mindless exploitation. This creates a fierce conflict between the greed for profit and the desire to preserve the planet's heritage for future generations. And without clear international laws and regulations, these disputes could lead to disaster, the irreversible loss of priceless artifacts from the past. To prevent such conflicts, we need a system based on mutual respect, close cooperation, and absolute transparency. International agreements like those adopted by UNESCO to protect World Heritage Sites clearly demonstrate the importance of our planet's history. They call for shared responsibility for the stewardship and wise use of our greatest discoveries. Developing clear rules that involve local authorities, governments, and the global scientific community will help build trust and foster collaboration. The key is to ensure that our insatiable thirst for knowledge does not harm the very treasures we seek to discover. As we uncover the secrets of Earth's deep past, ethical and diplomatic issues come to the fore. Our research should deepen our shared understanding of life, not become a source of hostility. Ethical principles are the compass that must guide us in the responsible pursuit of knowledge about the history of our planet, especially when we consider the hypothetical possibility of life forms far more complex than we can imagine. Above all, transparency and scientific integrity must underpin any research. This is the only way to avoid false, sensational claims about discoveries and to contribute to a genuine, deep understanding of Earth's history. Any traces or remains discovered during excavations must undergo the utmost scrutiny, free from the pursuit of fame and sensational headlines. Only in this way can we maintain public trust in science and prevent the spread of misinformation, which could poison the entire scientific field. An interdisciplinary approach is crucial in such research. Ethical standards should encourage close collaboration between geologists, paleontologists, biologists, ethicists, and local authorities. This comprehensive approach allows for consideration of all possible aspects, from the cultural significance of a site to the environmental impact of excavations. For example, if certain geological formations are considered potential traces of ancient life, researchers must be aware of the impact their work will have on the environment and the historical heritage of the region. This comprehensive approach helps avoid potential appropriation of results and fosters a responsible attitude toward the history of our planet. Another critical element is the need to protect and preserve the sources of information themselves. This applies not only to fossil remains, but also to geological data, records, and the entire context of the find. Protecting these sources helps prevent their misuse and preserves the integrity of scientific data for future generations. This also includes a sober assessment of all the possible implications of discoveries from scientific, cultural, and societal perspectives. If evidence suddenly emerges indicating that complex life existed long before known eras, this could completely upend established theories and require a radical rethinking of the entire picture of evolution. Therefore, ethical research must consider the potential public impact of such discoveries. They must ensure responsible dissemination of information and exercise extreme caution in their statements, so as not to undermine trust in science or provoke a wave of unfounded speculation. Cultivating scientific humility and openness to new ideas is also vital. Recognizing the limitations of modern technologies and methods encourages scientists to avoid hasty conclusions and to be honest about existing uncertainties. This ethical stance fosters integrity and encourages collaborative efforts to improve research and interpretation methods. Essentially, Ethics is our guidebook, guiding us on our journey into Earth's deep history, demanding respect, responsibility, and scientific integrity. As we delve into the uncharted depths of prehistory, these principles help us find a balance between our natural curiosity and our moral duty to honor the incredible and complex stories our planet holds. This responsible approach not only advances science, but also maintains the purity of our collective pursuit of truth. To achieve harmony between the passion of exploration and the need for preservation, several fundamental principles must be followed. First, minimally invasive methods are essential. The use of technologies such as LIDAR, ground-penetrating radar, or computed tomography allows potential fossils to be studied without destroying them. These methods preserve the invaluable context of finds, which is critical for their accurate interpretation. Secondly, international standards and cooperation are essential. Global protocols, similar to UNESCO agreements, must be developed to regulate access to potentially important sites and protect them from unsustainable exploitation. This includes creating a unified registry of significant geological and paleontological sites to prevent their destruction or commercialization. Third, cultural and scientific sensitivity is essential. Researchers must work closely with local authorities and scientific communities, taking their views and values into account when interpreting findings. Conducting open consultations and educational programs will help explain the significance of discoveries to the world and minimize potential conflicts. Fourth, transparency and peer review. All results, without exception, must undergo rigorous peer review and be reproducible. Scientists are obligated to clearly and explicitly disclose any ambiguities and methodological limitations in their work. This will help avoid cheap sensationalism and misinformation. And fifth, long-term management. Conservation must always be a priority. This includes developing strategies to protect geological layers and paleontological sites for future research. This could include creating protected conservation areas or using digital technologies like 3D scanning to document finds without physically removing them from the rock. This integrated approach allows us to combine scientific inquiry with heritage preservation, ensuring progress without compromising the integrity of history. A deep respect for the complex records imprinted in stone and a responsible approach to discoveries will help us better understand our place in the universe while preserving the opportunity for future generations to continue this great quest. Imagine we're searching for the ghosts of bygone eras, not the ghosts of legend, but the tangible remains of entire civilizations wiped from the face of the earth. Evidence of their existence won't be carved in stone in the form of statues or temples. No, their traces are gigantic scars on the planet itself. Massive disturbances in geological strata, chemical echoes of events that generated incredible temperatures. These are the indirect clues that can whisper to us of past greatness. Paleontology is also joining this grand investigation. Like a detective, this science sifts through layers of ancient rock in search of fossils. And although paleontologists are usually fascinated by reconstructing the picture of biological evolution, their trained eye can spot things that stand out from the general picture. Anomalies, for example, sudden and unexplained changes in the composition of fossil communities, or even more intriguing, strange artifacts buried in sedimentary rocks millions of years old. Such finds could be direct evidence of technological activity in the distant past or environmental disasters that don't fit into any known natural scenario. Consider what if unusual microstructures or materials, eerily reminiscent of artificially created objects, were discovered in ancient stone. This could be the first real evidence of the existence of ancient industrial civilizations. Even archaeology, which we are accustomed to associating with human history, is now pushing the boundaries of what is possible, applying its methods to the study of anomalous finds and bioarchaeological evidence in strata that are hundreds of millions of years old. Modern science is armed with powerful tools. Methods like spectroscopy, electron microscopy, and sophisticated chemical residue analysis allow scientists to peer into the very heart of matter. They can distinguish natural mineral formations from materials that could only have been created by intelligent hands. Imagine suddenly discovering unusual metals, complex alloys, or synthetic compounds never created by nature in layers dating back to the dinosaur era. This would be irrefutable evidence of the existence of ancient industry, and such a discovery would demand immediate and meticulous study. All these scientific disciplines, geology, paleontology, chemistry, are united to critically analyze stratigraphic data, the very record of our planet, in search of signs of ancient worlds. By comparing geological and chronological data with the analysis of fossils and artifacts, scientists are trying to find inconsistencies and unexplained phenomena that could overturn our current understanding of Earth's history. And here, the most rigorous scientific methodology is applied, guaranteeing that any, even the most daring, claims about pre-human civilizations are supported by ironclad, irrefutable evidence. It's important to understand this rigorous scientific approach is designed to weed out fantasies and separate natural geological processes from seemingly improbable hypotheses. But what if these hypotheses are confirmed? What if evidence is found that supports the so-called Silurian theory? This will force us to completely rethink our views on the evolution of life, the nature of technological progress, and the fragility or resilience of our planet's ecosystem on geological timescales. If it turns out to be true that a highly advanced civilization existed on Earth long before humans appeared, it would completely revolutionize our understanding of planetary and biological history. Currently, most of us are accustomed to considering humans as the pinnacle of evolution and our technological development as a unique and very recent phenomenon. However, confirmation of the Silurian hypothesis would deal a crushing blow to this anthropocentric or human-centered view. Such a discovery would mean that intelligence and the ability to create complex technologies are not the exclusive privilege of our species, or a recent invention in Earth's history. Complex life forms with advanced societies could have arisen on our planet multiple times, perhaps driven by the same evolutionary forces, but each time following their own unique path. This discovery would also force us to rethink the resilience and vulnerability of our planetary environment. If we assume that a previous civilization left deep scars on Earth's geology, for example, through massive resource extraction, massive construction, or other powerful environmental impacts, We would have to rethink our understanding of the planet's ability to regenerate itself. This would raise deeply uncomfortable questions about the durability of technological societies. Perhaps planetary conditions foster their emergence, but then inevitably lead to their demise. This, in turn, could shed light on the resilience of our own civilization, highlighting the importance of understanding and mitigating the long-term consequences of our actions. Moreover, confirmation of this hypothesis would force scientists to rewrite the entire chronology of habitability on Earth. This could mean that conditions favorable for the emergence of life and even civilizations are much more common on planets than previously thought. Or, conversely, such windows of opportunity could be very brief and interrupted by catastrophic events, repeatedly setting back the evolutionary clock. This complex and multifaceted picture could alter our perception of climate change, the sustainability of the biosphere, and even the likelihood of life elsewhere in the universe. If we can prove the existence of an earlier civilization, it will profoundly deepen our understanding of our home planet's history. We will see that its development is not a simple linear progression from simple to complex, but rather a mosaic of rises and falls, of civilizations that emerged and disappeared, leaving behind invisible but everlasting traces. Unraveling these ancient mysteries will open entirely new horizons for research. We will be able to contemplate not only what life is, but also its boundless possibilities and the imprints it leaves on the fabric of time. This profound shift in our worldview could transform our understanding of planetary evolution and inspire us to redouble our search for signs of long-lost civilizations. To discover these traces, we must learn to read between the lines of the geological record, recognizing subtle yet telling signs hidden deep within the layers of Earth's history. Unlike the obvious clues at the site of a recent event, civilizations that existed in ancient times left behind much more subtle but far more significant evidence. And these can only be discovered by carefully analyzing the geological strata. These traces can take a variety of forms, and each is a window into the distant past, allowing us to see how ancient civilizations influenced their environment and the technological level they reached. One key indicator is anomalous patterns in sediment accumulation. The activities of an advanced civilization, such as the construction of megastructures, planetary scale resource extraction, or landscape modification, would inevitably have influenced the deposition of sedimentary rocks. For example, abnormally thick or compositionally distinct layers may indicate periods of intense material recycling or global environmental change. Such layers often contain unusually high concentrations of recycled minerals or even synthetic substances that are unlikely to have formed in such quantities naturally. The most important clues to unraveling this mystery may lie not only in specific metal alloys or industrial waste, but also in isotopic anomalies. Civilizations with advanced technology could have altered the natural isotopic ratios in nature through smelting, alloying, or complex chemical processing. For example, changes in the isotopic ratios of elements such as lead, copper, or iron, far beyond the limits of natural variation, could indicate large-scale industrial activity. Such anomalies, forever imprinted in mineral deposits, represent chemical fingerprints of human impact on the world. But mineral deposits themselves can also contain invaluable information. Certain mineralogical features, such as synthetic compounds that do not exist in nature, unusual crystal structures, or metal concentrations that cannot be explained by natural geological processes, may all indicate deliberate intervention. Technological influences inevitably left their mark on Earth's history. For example, the presence of mineral phases that form only at extremely high temperatures, or the remains of synthetic materials such as ancient ceramics or metallurgical slags in layers hundreds of millions of years old would provide compelling evidence of past technological activity. To understand these signs, we must recognize that any technological influence, whether human or otherwise, leaves behind a complex, multi-layered chemical and mineralogical legacy. If we carefully analyze these clues, we can find irrefutable evidence of the existence of an advanced civilization that preceded our own, whose history was intricately woven into the very geological structure of our planet. And a deeper study of these traces inevitably raises the question, how exactly can sedimentary layers, isotopic anomalies, and mineral deposits serve as keys to unraveling the mystery of ancient technological activity? The most important indicators in this search are sedimentary layers, which conceal subtle but compelling clues within their depths. Careful analysis of these geological archives can reveal patterns that differ markedly from normal natural processes. These patterns may indicate the intervention of intelligent beings in the distant past. Sedimentary layers typically form through the slow, gradual accumulation of particles over time. However, anomalies, such as unusually thick or intermixed layers, may indicate rapid sedimentation processes or even mechanical disruption. Consider layers that bear the imprint of thermal alterations, unusual compaction, or anomalous particle sorting. This could hint at activities such as large-scale mining, construction, or industrial waste disposal. In some cases, disturbances in sedimentary layers coincide with known technological processes, such as the presence of fragments of crushed rock or fossils in unnatural positions, further supporting the hypothesis of ancient intervention. Artificial conglomerates, that is, materials created artificially and fused with natural sediments, represent another key element that could shed light on the true history of our planet. Imagine holding a slice of ancient rock in your hands, a kind of stone chronicle. It contains chemical signatures that can tell us incredible stories. Distortions in the ratio of isotopes, the tiny particles that make up elements, act as alarm bells. Fluctuations in the distribution of carbon, nitrogen, or rare metals can indicate processes that go far beyond the usual natural cycles. For example, if we see a sudden and dramatic spike in the abundance of certain isotopes in a particular geological layer, it could be a cry from the past. It could be evidence of someone smelting ore at unimaginable temperatures or practicing ancient metallurgy. Such anomalies, like bright flashes, stand out against the calm flow of natural events, especially when they coexist with other geological oddities. This opens up a stunning possibility. We could be looking at the traces of intelligent intervention or even echoes of extraterrestrial technology, forcing science to re-examine our planet's past. Mineral deposits, in turn, become another source of clues when their composition or formation method baffles scientists. Imagine using powerful microscopes and chemical analysis to discover particles of synthetic minerals in ancient rock, for example, fragments of artificially created ceramics or unusual metal oxides not naturally produced. Moreover, geological strata millions of years old can conceal entire layers of industrial waste, such as slag or molten quartz. Such finds are no longer indirect hints, but direct physical evidence of ancient production. When we piece together all the geological clues, sedimentary anomalies, and unusual minerals, a compelling picture of an ancient technological civilization begins to emerge. However, to accurately interpret these signs requires painstaking analysis by a team of specialists from various fields. Only then can we separate natural geological vagaries from the genuine traces of civilizations that have sunk into oblivion. And this search forces us to delve ever deeper into the mysteries of the past. And here, researchers face one of the most complex and captivating mysteries. How can we distinguish a creation of nature from the ruins of an ancient engineering genius? Where does that fine, almost invisible line lie? This problem continues to excite scientists, posing ever new challenges. For paleontologists and geologists studying Earth's deep past, trying to separate natural phenomena from the handiwork of intelligent beings is an incredibly complex and multifaceted quest. Over millions of years, the face of our planet has been constantly changing under the influence of powerful forces, violent volcanic eruptions, shifting tectonic plates, relentless erosion, sedimentation, and mineralization processes. All of this could create structures that remarkably accurately mimic, or conversely, reliably conceal traces of someone's activity. Without the full context, such objects can easily be dismissed as freaks of nature. On the other hand, genuine artifacts created by someone in time immemorial could be virtually destroyed, altered by chemical processes, or buried under kilometers of rock, making their discovery nearly impossible. Even when researchers acquire the most sophisticated methods capable of distinguishing the artificial from the natural, the challenges remain. Modern scanning technologies allow us to peer underground and see genuine traces of ancient civilizations, distinguishing them from geological formations. However, this process requires meticulous analysis of layers, obtaining incredibly high-resolution images, and the collaboration of geologists, archaeologists, and geochemists. Let's travel back in time to an era when the planet itself was a battlefield of titanic forces. Its geological history is full of catastrophes. Imagine a supervolcano eruption spewing millions of tons of ash into the sky, or a giant meteorite impact whose shockwave wipes out entire ecosystems. These cataclysms could have either forever destroyed any evidence of ancient civilizations or, conversely, created unique geological time capsules. For example, a thick layer of volcanic ash can cover an entire area suspected of containing archaeological finds. This creates a colossal problem. How can we determine whether a discovered artifact was created before or after the eruption? Similarly, mineralization processes can create structures in rock that look human-made but are in fact entirely natural. Technological advances have given us a better understanding of these conundrums. But this only highlights the importance of a holistic approach to studying the past. The problem remains daunting. Modern techniques such as isotope dating, remote sensing of the planet from space, and geophysical research allow us to increasingly accurately distinguish natural processes from the traces of intelligent activity. However, deciphering the resulting data still requires incredibly careful and thoughtful analysis. As our knowledge grows, the boundary between natural geological features and potential signs of ancient civilizations is becoming ever clearer. This opens up new, exciting opportunities to explore how planetary scars like impact craters may hold clues to long-lost worlds. Impact craters and other traces of planetary catastrophes are essentially natural archives of Earth's turbulent history. They may provide clues to unraveling the mysteries of ancient societies. When a massive asteroid or comet slams into a planet, it leaves a gigantic scar on its surface, a crater that serves as a lasting reminder of the destructive power of space. These sites often contain layers of molten rock, minerals altered by colossal pressure, and sediment ejected over kilometers. All of this can be precisely dated to determine the moment of impact. Now imagine that such an event occurred during an era when an advanced civilization already existed on Earth. This cataclysm could have left subtle but completely unmistakable traces in the rock. These signs, such as anomalous chemical composition of materials or unusual mineral compounds, could directly indicate the existence of a technological culture on the planet at that time. Furthermore, other planetary events, such as supervolcanic eruptions or powerful earthquakes, could also have affected the preservation of ancient artifacts. Imagine gigantic layers of ash blanketing entire continents. They create clear markers in the geological record that can be traced worldwide. If an ancient civilization existed before or during these events, its remains, whether tools, building fragments, or even biological traces, could have been buried beneath these layers. Over millennia, such deposits would have been reliably preserved, effectively hiding evidence of early technological progress beneath a thick layer of geological strata. Impact events and planetary upheavals have a profound impact on climate and ecology, which in turn dramatically alters the preservation conditions of all materials, both organic and inorganic. Sudden climate shifts can either accelerate decay processes or, conversely, create unique conditions for ideal preservation. For example, the incredible heat and pressure of an asteroid impact leaves behind unique mineralogical fingerprints. These traces, when considered alongside other geological anomalies, can serve as indirect evidence of the existence of a civilization, especially if they coincide with other archaeological finds. As we learn to read the deep sea and geological records, the importance of these planetary events becomes ever clearer. They act as both destructive forces and guardians of history, capturing moments from Earth's past that may hold clues to civilizations beyond our current understanding. This brings us to a crucial question. What role did these events play in the history of our planet? And how can deep-sea sediments and ice cores help us search for evidence of ancient technological activity? These natural archives have the potential to unlock secrets hidden in the geological record and perhaps open doors to worlds lost in time. Deep-sea sediments and ice cores are invaluable repositories of our planet's ecological history. They offer a unique glimpse into eras that predate everything we know. Sediments, layer upon layer accumulated on the ocean floor over hundreds of thousands and even millions of years, represent unique archives of information about the ancient world and possible traces of technological activity. These natural reservoirs preserve multi-layered data on the atmosphere, ocean, and land conditions, making them invaluable tools in the search for evidence of earlier advanced societies. Deep-sea sediments are a complex mixture of mineral particles, organic remains, and microorganisms that slowly settle to the ocean floor. By analyzing these layers, researchers can detect anomalous chemical signatures, unusual mineral forms, or traces of rare elements. All of these may indicate ancient technological processes, such as metallurgy, the creation of complex alloys, or even chemical industry. For example, anomalously high concentrations of metals such as gold, platinum, or rare earth elements, which cannot be explained by natural cycles, may be direct evidence of mining or metallurgy that existed long before the advent of known civilizations. Ice cores, which scientists extract from the depths of polar ice caps, in turn preserve a chronological record of atmospheric composition, volcanic eruptions, and the tiniest dust particles. History is written in these ice pillars like a book. They contain layers of soot and chemical residues that can be analyzed for industrial pollutants or byproducts of technology. Imagine the shock of scientists finding traces of a synthetic compound, such as a chlorofluorocarbon, in a layer of ice hundreds of thousands of years old. Its presence there deep in time would be irrefutable evidence of ancient technological processes capable of producing such substances. Moreover, modern analytical techniques such as mass spectrometry, isotope ratio analysis, and spectroscopy allow scientists to detect and measure even the most minute traces of materials in these complex natural archives. These technologies are helping us increasingly distinguish natural mineral formations from those that could have been created by artificial means. Imagine we're searching not for the bones of giant lizards, but for something far more subtle, the chemical ghost left behind by technology. After all, any industrial process alters the environment, and these changes, these anomalies in isotopic composition, can be imprinted in the geological record. Consider deep-sea sediments or ice cores extracted from permafrost. It's there, in these pristine archives of the planet, that traces of unprecedented production or large-scale resource extraction may be hidden, which would otherwise remain a mystery. That's why researchers study these layers so closely. They are the cutting edge of science in the search for subtle but potentially sensational evidence of an ancient technological era. Every bit of information, whether detailed stratigraphy, that is, the sequence of layers, or chemical analysis, helps construct a precise chronology. And when this chronology is run through the powerful analytical tools of modern times, it can reveal the existence of civilizations long since wiped off the face of the earth. But here, a key question arises. How can modern methods of geochronology, the science of dating rocks, help us date these ghostly artifacts and traces? How do they deepen our understanding of our planet's mysterious past? Today's approaches to studying the age of the Earth play a crucial role in uncovering its deep history, providing us with invaluable information about bygone eras. Creating a precise timeline onto which to plot the possible traces of ancient civilizations remains a key challenge for scientists. Modern dating methods make it possible to determine with astonishing accuracy the age of geological formations, fossil deposits, and even the smallest shifts in the Earth's crust, all of which may serve as indirect evidence of past technological activity or environmental impacts. One of the most powerful tools in geologists' arsenal is radiometric dating. Its essence is simple. We measure the decay of unstable isotopes in rocks and minerals, which occurs at a constant, well-known rate, like a highly accurate natural clock. For example, the uranium-lead method allows scientists to accurately determine the age of zircon crystals found in ancient volcanic ash layers. Such ash layers serve as reliable chronological markers, like bookmarks in the book of Earth's history, against which other geological finds can be compared. And when anomalies are discovered in these precisely dated layers, for example, unusually high concentrations of certain elements or strange mineral structures, geochronology helps answer the fundamental question: is this the result of natural processes or artificial activity? Perhaps the work of a civilization that existed long before the advent of humans. Techniques such as argon dating allow us to accurately date volcanic eruptions and the ages of associated ash deposits, which often serve as time markers. This can be vital for understanding when and how potential artifacts or anomalies may have formed and for placing them in a clearly defined temporal context. Advances in thermochronology, methods for measuring the cooling age of rocks, provide information about tectonic events, massive processes that could have either brought ancient structures to the surface or buried them forever. This can provide clues about when and how such features may have been preserved or destroyed. In addition to radiometry, recent advances in isotope geochemistry, such as stable isotope ratio analysis, can aid in investigating past environmental conditions that may have been altered by human activity. For example, sharp changes in the isotopic composition of carbon or oxygen can indicate colossal changes in the ecosystem caused by, say, industrial emissions. However, despite the power of these tools, their use requires extreme caution. The ability to accurately date specific artifacts or traces depends entirely on the preservation of the material evidence and the context in which it was found. As we delve deeper into Earth's ancient history, understanding the strengths and limitations of geochronology becomes essential to separating hard facts from speculation. The question of how to distinguish traces of previous civilizations from the results of natural geological processes inevitably forces us to consider the limits of our methods. Are they even capable of capturing the most hidden, most concealed traces of an ancient, possibly highly advanced civilization? Although geological methods have represented a real breakthrough in our understanding of the Earth's distant past, they have serious limitations when it comes to searching for evidence of civilizations that preceded our own. These limitations stem from both the very nature of geological processes and their unimaginable scale, making the task of discovering ancient traces incredibly difficult. One of the main obstacles is the vastness of time itself. Many early civilizations, if they truly existed, would have left behind only subtle or fleeting traces that could easily vanish over millions of years. Geological processes such as erosion, sedimentation, plate tectonic movement, and volcanic activity constantly reshape our planet. These powerful forces can erase or obscure any traces of ancient activity, especially if they were not monumental or widespread. Imagine a civilization that used primarily biodegradable materials or created a limited number of durable artifacts. After millions of years of geological upheaval, absolutely nothing of it might remain. Moreover, modern geochronological methods often have resolution limitations. This makes it difficult to accurately determine events or structures hundreds of thousands or millions of years old. Radiometric dating, isotopic analysis, and stratigraphic methods, which work with pinpoint accuracy within specific time frames, can be much less effective or even inapplicable to very ancient deposits. This creates a kind of blind spot for the study of early civilizations that may have existed during periods when geological traces were too weak or unclear. Another crucial task is the search for indirect evidence. Many potential traces, such as artificial alterations in mineral deposits, anomalies in sediment composition, or unusual isotopic ratios, can be subtle or highly ambiguous. Distinguishing them from natural geological processes requires a high level of interpretation. Sometimes, such signals can simply be ignored as natural anomalies or even missed altogether. Ultimately, preservation is key. Some environments, such as dry caves or stable mineral deposits, are ideal for preserving artifacts, while others quickly erode or destroy them. These factors can greatly complicate the process of finding and studying ancient civilizations. The shifting geological layers makes it nearly impossible to detect cultures that may have existed in less favorable conditions. As a result, our modern geological tools, although incredibly powerful, cannot give us a complete picture of the Earth's distant past. And this opens up truly fascinating possibilities for reflection. Could some traces of ancient civilizations have been destroyed or hidden not simply by geological processes, but by something far more catastrophic? For example, collisions with celestial bodies or other cosmic phenomena. Space impacts and other astronomical events have long captivated scientists. Their potential to have a colossal impact on planetary history is undeniable. Catastrophic events such as asteroid and comet strikes or intense solar flares can cause planetary scale destruction. Destruction capable of obscuring or completely erasing evidence of even the most advanced and powerful ancient civilizations. When exploring Earth's deep past, these events act as powerful erasers, capable of destroying surface structures, contaminating archaeological layers, and completely reshaping the environmental conditions in which civilizations flourished. One of the most striking examples is the asteroid impact that caused the mass extinction at the Cretaceous-Paleogene boundary, approximately 66 million years ago. This event didn't just end the age of dinosaurs, it had a catastrophic impact on the surface and biosphere of our planet. Impacts of this magnitude leave behind unique geological scars, layers of iridium, impact quartz, and giant craters that can be detected even tens of millions of years after the catastrophe. If any ancient civilizations existed before these events, their remains could have been buried under kilometers of debris. Over time, these layers eroded or metamorphosed, making any finds beneath them virtually invisible. Moreover, cosmic events such as supernova explosions or gamma-ray bursts could have had a dramatic impact on Earth's atmosphere and climate, causing prolonged periods of severe environmental stress. These events could have significantly reduced or even completely destroyed any biological and technological artifacts that might have supported the existence of previous civilizations. Intense radiation and radical atmospheric changes could have made such finds even rarer and more elusive. These changes could also have accelerated erosion and sedimentation processes, effectively wiping out any surface evidence of ancient societies. It is important to understand that cosmic impacts can also cause secondary effects, such as massive volcanic eruptions or abrupt climate change, further complicating the discovery of traces of ancient civilizations or leading to their complete disappearance. These secondary effects could make the work of archaeologists and geologists seeking to uncover the secrets of our planet's distant history virtually impossible, turning the search into a veritable ghost hunt. In particular, the role of extraterrestrial collisions in the possible destruction of evidence of the past cannot be overestimated. Studying our planet's geological record is a fascinating journey into the past. It repeatedly demonstrates one simple truth: even the most powerful civilizations can be wiped off the face of the Earth. Imagine catastrophic events on a planetary scale, asteroid impacts, supervolcanic eruptions can literally reset history, leaving not a single stone standing of great societies. Yet, at the same time, these same cataclysms leave their own unique scars, their own distinctive signatures in the rocks. And if you learn to correctly read these signs, you can uncover incredible secrets of our planet's turbulent past. This understanding inevitably leads us to one of the most intriguing questions in paleontology. What if fossils can tell us not only about ancient animals, but also about ancient civilizations that have no connection whatsoever to humans? Fossils are priceless archives, veritable time capsules. They allow us to peer into the past millions, hundreds of millions of years, revealing a grand panorama of the evolution and diversity of life. We are accustomed to seeing them only as the remains of biological organisms, bones, shells, leaf impressions. But what if we look deeper? What if these stone records preserve traces not only of biological life, but also of technological life? Sometimes paleontologists stumble upon fossil anomalies, unique structures that baffle them. They force them to question accepted views and wonder, could these strange finds be traces of ancient non-human civilizations or their technologies? Let's step back into the lab and examine these mysteries under a microscope. Among the most intriguing finds are anomalous mineral formations that cannot be explained biologically. Imagine researchers discovering fossils with incredibly complex, almost perfect, geometric patterns, symmetrical forms that are extremely rare in the wild. We're talking about complex microstructures, similar to fractals, fused directly into the mineral matrix. They resemble not living tissue, but rather tiny parts of an unknown mechanism, some kind of engineering components frozen in stone for eternity. Equally intriguing are unusual inclusions in sedimentary rocks, carbonate or even metallic ones. They may be direct evidence of ancient technologies. In some geological layers, tens of millions of years old, scientists are finding what appear to be artificial devices or fragments thereof. These may be perfectly smooth surfaces that could not have formed naturally, or layered composite materials, seemingly created layer by layer using an unknown technology, or even microscopic assemblies of various elements. Such anomalies provide powerful evidence that technological activity may have occurred on Earth in the deep past, especially when the characteristics of these finds are inconsistent with known biological fossilization processes. For example, when paleontologists discover microstructures with precise machine-made geometry, fine grooves, perfectly smooth ridges, or microscopic, perfectly shaped holes, this raises a host of questions. Questions that conventional science has yet to answer, especially when these strange artifacts are found close to the most ordinary biological fossils. Another incredibly promising direction in these searches is the identification of isotopic or mineralogical anomalies. Simply put, scientists are looking for chemical fingerprints that cannot be explained by natural geological processes. What could these be? For example, an unusual chemical composition of a rock that is not found in nature, or metal alloys that simply should not be there, or materials subjected to strong thermal influences. Geometric engravings, complex patterns, traces of deliberate modification, all this suggests that some ancient creatures had not only intelligence, but also tools. If such markings demonstrate a high degree of regularity and uniqueness, their biological origin is seriously questioned. This opens the door to completely improbable hypotheses about the existence of intelligent design in the prehistoric era. While the vast majority of fossils directly point to biological evolution, certain anomalies and unusual structures force us to expand our horizons. They prompt us to consider that these finds may have a much broader range of origins, including technological or artificial ones. This, in turn, forces us to reconsider our entire understanding of Earth's ancient past and the possibility of the existence of long-vanished, yet advanced civilizations. Detecting such anomalies is only the first step. The most difficult part is proving their artificial origin. This requires a meticulous study of any deviations from standard biological processes. Ordinary fossils typically accurately reflect biological morphology. We see shells, bones, and plant imprints. But some finds clearly stand out from this pattern, hinting at the presence of intelligent design or technology. What are we looking for? Irregular mineral deposits resembling artificial elements? Symmetrical geometric patterns that could not have been created by nature? Micro cracks that mimic circuit structures, or repeating motifs that appear intentional. These structures may include microscopic fractures aligned according to precise geometry, as well as unusual alloys or traces of mineralization resembling microchips. None of this can be explained by natural geological or biological processes. One of the most exciting areas of research involves analyzing mineralized tissues for signs of nanostructured engineering. It sounds like science fiction, but imagine the presence of unusually uniform layered deposits within fossilized tissues. This could indicate processes strikingly similar to those used today in nanofabrication. Scientists are also paying attention to materials with characteristics that are inconsistent with typical biological mineralization, such as inclusions of pure metals or complex alloys within fossils. Such anomalies may be nothing more than embedded microelectronic components or fragments of synthetic composites preserved within ancient biological materials. Particularly intriguing are those that exhibit perfect alignment or symmetry, far beyond the natural growth of minerals. Another promising avenue is the careful study of fossilized biofilms or microbial mats. If signs of artificial intervention are found in their structure, this could be key to understanding ancient biotechnology. These structures may exhibit complex organization, symmetry, or layering that are unlikely to be explained solely by natural processes occurring in the microcosm. They may be evidence of genuine bioengineered structures. Furthermore, anomalous isotope ratios or chemical compositions of these finds may indicate the presence of non-biological materials, further supporting the hypothesis of technological intervention. However, researchers face a daunting task: distinguishing genuine technological anomalies from the bizarre effects of nature, from distortions arising during the fossilization process. Nevertheless, today they have powerful tools at their disposal. Modern imaging techniques such as electron microscopy, synchrotron radiation analysis, and spectroscopy allow them to peer into the stone's deepest secrets. They help reveal the smallest details, inaccessible to conventional observation. These tools enable researchers to detect features at the micro and nanoscale. If these features are convincingly confirmed, they could provide irrefutable evidence of technological intervention. Such findings could provide compelling evidence of ancient technological activity that cannot be explained by natural processes. This study also raises a broader question. Can the analysis of microfossils reveal the secrets of complex biological or technological processes that took place in the distant past? Delving into the world of microfossils opens a window into Earth's ancient biological history, providing invaluable insights into the origin and evolution of life on our planet. These tiny fossils, often smaller than a micrometer, that is, smaller than a grain of dust, can be found in rocks billions of years old. They provide evidence of the existence of primitive organisms long before the emergence of complex multicellular life. While microfossils are traditionally associated with the simplest microbial forms, recent scientific advances reveal something astonishing. They may contain subtle signs of biological complexity, which in turn may point to far more intricate processes that occurred in the ancient world. One of the most exciting areas is the study of microfossil morphology. Scientists look for signs of cellular differentiation, that is, the segregation of cells by function, or traces of specialized structures. For example, some filamentous or spherical microfossils exhibit complex organizational patterns. They resemble primitive biofilms or even early forms of intercellular interactions. These characteristics may indicate that the earliest microbes already possessed a certain structural and functional complexity. They may even have exhibited rudimentary forms of communication or signs of resource sharing, all of which could be considered the first steps toward the creation of complex biological systems. Moreover, chemical analysis of inclusions within microfossils can reveal isotopic signatures that indicate metabolic activity that goes far beyond simple survival. For example, certain carbon or sulfur isotope ratios may indicate complex metabolic pathways similar to those found in modern extremophiles, organisms living in the harshest environments, or even early forms of photosynthesis. Such finds shatter the notion that early life was exceptionally simple. They point to a whole spectrum of biological complexity, which may include processes characteristic of modern, far more advanced organisms. But beyond purely biological processes, some microfossil structures, scientists suggest, may contain signs of technological intervention. Let's step back into a paleontologist's laboratory. Imagine a thin slice of ancient rock under the lens of a powerful microscope. What are we looking for there? Not just traces of life, but something more. Perhaps echoes of ancient, incomprehensible technological interactions. These could be subtle patterns in how minerals formed or anomalous chemical compositions hinting at how living organisms once upon a time somehow influenced their environment. And while such interpretations spark heated debate in the scientific community, they make us think. Perhaps hidden within these microscopic fossils are clues to the possibility that biology and technology could have coexisted in our planet's unimaginably distant past. The mere study of these microfossils is already upending our understanding of evolution. It gives us compelling reason to believe that the earliest forms of life on Earth may have been far more complex than we've traditionally believed. And this raises fundamental questions. What was the nature of these earliest biological breakthroughs? Could those ancient microbes have possessed abilities or initiated processes that defy modern models of life's evolution? Such bold ideas force us to rethink everything. They suggest that ancient microbial life or other complex fossils could radically alter the very history of life's origins on Earth, and perhaps even open up entirely new avenues for the search for life in the vast reaches of space. Discovering traces of ancient microbial life forms or the remains of complex organisms undoubtedly expands our understanding of biological evolution. But with this new knowledge comes new, even more complex mysteries. Take microbial fossils, for example, often appearing as fine fossilized threads or layered structures in rock. They are among the earliest physical evidence of life on Earth. These microscopic artifacts take us on a journey back 3.5 billion years to a time when our planet was very young. However, it is precisely their tiny size and primitive form that pose a major challenge. How can we distinguish a genuine trace of a living organism from a non-living mineral formation that merely skillfully mimics a biological structure? Nature is a great deceiver. Some mineral formations can grow in shapes eerily reminiscent of fossilized bacterial filaments, making their identification incredibly difficult. Ordinary sedimentary rocks can form layered or thread-like patterns that are at first glance indistinguishable from ancient microbial colonies. This greatly complicates confirming that what we see is truly a trace of life and not a figment of inanimate nature. Likewise, when paleontologists discover fossils of more complex creatures, such as soft-bodied organisms or the first multicellular organisms, it challenges traditional models of evolution. Finding fossils with complex features in very ancient strata could mean that biological complexity arose on the planet much earlier than previously thought. But even here, a trap awaits. Interpreting such finds is often complicated by taphonomic processes, that is, how exactly an organism decomposed and was preserved in rock over millions of years. These processes can irreversibly distort or completely obscure its original biological features. And so the crucial question arises, are we truly witnessing the remains of an ancient creature, or are they simply the result of mineral replacement or other geological tricks? Moreover, it's always necessary to consider the geological context, that is, the rock layers in which the find was made. Sometimes, the layered structure of sedimentary rocks can confuse even an expert, as mineral deposits can form forms strikingly reminiscent of biological ones. These natural mineralizations are the result of ordinary geological processes, but they can create such intricate patterns that at first glance they appear to be the work of living nature, although in fact they are purely mineral in origin. To distinguish between true biological fossils and inanimate artifacts, scientists must employ a whole arsenal of sophisticated analytical methods. These include isotope analysis, electron microscopy, and detailed chemical profiling. These technologies help identify so-called biosignatures, unique isotope ratios or organic molecules that serve as irrefutable evidence of the presence of life. However, even here there is a risk of false positives, especially when dealing with ancient and highly altered fossils that have lain in the earth for billions of years. The line between natural mineral patterns and actual evidence of ancient life is often incredibly thin, almost indistinguishable. This requires painstaking interdisciplinary analysis from researchers to accurately decipher these messages from the deep past. For paleontologists and astrobiologists, this task becomes even more challenging when it comes to distinguishing between natural fossils and possible artifacts left behind by hypothetical ancient civilizations. The main problem lies in the striking similarity of some natural mineral structures to objects that appear artificial. This can be completely confusing when searching for signs of technological activity in the distant past. Many mineral formations, such as concretions, fossilized biological tissue, or so-called pseudofossils, can possess characteristics that at first glance suggest artificial objects, tools, or even structural elements. These natural structures often arise as a result of common geological processes: enormous pressure, mineral crystallization, or microbial activity, and they are quite capable of reproducing perfect geometric symmetry or having a composition very similar to artificial objects. One of the main obstacles to finding the truth is the fact that non-living processes constantly create ordered, structured patterns. For example, crystal growth can form perfectly symmetrical figures or layered structures that can be mistaken for mechanical marks or carved surfaces. Furthermore, fossilized microbial colonies or biofilm structures can create complex textures that can easily be mistaken for artificially processed surfaces. Therefore, distinguishing these natural formations from possible technological artifacts requires incredibly meticulous analysis, incorporating several methods: ultra-high-resolution imaging, spectroscopy, and isotopic studies. Another enormous difficulty is that any contextual clues that could help us are extremely rare. If any artifacts of an ancient civilization existed in the distant past, they would likely have been subjected to colossal geological changes, erosion, metamorphism, tectonic shifts. These merciless processes could completely obscure or destroy their original characteristics. Over hundreds of millions of years, even the most durable and long-lasting structures will turn into a mineral deposit indistinguishable from the surrounding rock. Without clear clues, such as associated debris, obvious signs of production, or a characteristic arrangement within rock layers, it becomes virtually impossible to determine whether a fossilized object is the result of natural processes or evidence of intelligent activity. Moreover, our understanding of the full diversity of natural geological phenomena is still far from perfect. Some structures we discover may appear to be anomalous natural formations, seemingly contradicting all current geological theories. This further complicates the task of identifying them. Scientists must examine such anomalous fossils with extreme caution, applying the most rigorous interdisciplinary approaches. They must analyze their form, composition, and context to determine whether they are merely quirks of nature or perhaps linked to ancient unknown technologies. And this, as yet unresolved problem raises a fascinating question. Could certain fossilized structures actually indicate the existence of ancient mechanisms or tools? The study of fossilized structures suspected of technological origin remains one of the most controversial yet fascinating areas of paleontological research. Unlike organic remains, such as bones or shells, these potential artifacts require incredibly meticulous analysis to separate genuine evidence from natural geological formations. Nevertheless, certain anomalies in the paleontological record have given rise to hypotheses about the existence of advanced technology in ancient times, millions of years before the emergence of known human civilizations. One of the most discussed examples is the anomalous, geometrically perfect formations found in certain sedimentary layers. These structures often exhibit striking symmetry, regularity, and complex shapes that are very difficult to explain solely by natural processes such as mineral growth or erosion. For example, some researchers have noted intricate layered inclusions resembling metal within certain fossils. Theoretically, these could represent the remains of ancient technologies buried within the rock mass. When studying ancient fossils and archaeological finds, we sometimes encounter structures that can be interpreted as reflecting primitive tools or even mechanical devices. When examined closely under a microscope, these inclusions sometimes reveal patterns reminiscent of gear teeth, hinges, or other elements of complex mechanisms. If these features were ever conclusively confirmed, they would indicate the existence of ancient craftsmanship far beyond all modern archaeological understanding. However, a critical scientific approach requires maintaining a healthy skepticism and conducting the most detailed examination. Many of these structures can easily be explained by mineral crystallization, pseudofossils, or other natural geological phenomena that merely mimic artificial structures. For example, some flint formations can take on complex geometries as a result of natural crystal growth processes, which can easily lead to false conclusions about the existence of ancient technologies. Furthermore, the very preservation of metallic materials over millions of years is extremely rare. Corrosion and mineral replacement processes in most cases completely destroy any original traces of metal, making their identification virtually impossible. It's also critical to consider the context in which these mysterious structures were found. If an object is found isolated from everything else, imagine that a single, strange discovery in ancient rock is just a nuisance, geological noise. It can tell us little about its origin, but what if we find a series of such anomalies? What if they form a single, consistent pattern across vast territories and hint at something more, the traces of some complex, organized activity? Then the arguments for the existence of ancient mechanisms left behind by someone before us begin to sound much more compelling. Even though some discoveries excite the imagination of scientists, a direct and undeniable connection between fossilized structures and the remains of ancient machines or tools remains elusive. This veil of secrecy has not been lifted. And this ongoing research, of course, forces us to ask more fundamental questions. Is the fossil record of this great book of Earth history capable of confirming, or conversely, forever refuting the hypothesis of the existence of civilizations on our planet that predated humanity? This is a topic that demands the most careful and unbiased attention. Trying to assess the chances that other intelligent beings existed here before us is an incredibly complex puzzle. It's full of both encouraging hints and glaring contradictions. The rock record, the fossil record, is our main portal into the planet's distant past. It allows us to trace the grand epic of life's evolution, stretching over billions of years. However, as soon as we begin to search these layers, not for dinosaur bones, but for evidence of advanced, perhaps even industrial civilizations, this record becomes a source of enormous difficulties. First, the fossilization process itself is incredibly selective and capricious. Nature prefers to preserve hard materials, bones, shells, teeth. But soft materials, including any organic artifacts or the remains of complex technologies, turn to stone in vanishingly rare cases. This selectivity becomes an almost insurmountable barrier, preventing us from discerning signs of ancient technological power or complex social organization if they existed before the advent of humans. Moreover, many of those finds that at first glance appear man-made, unusual structures or formations, upon closer inspection often turn out to be merely bizarre quirks of nature. Geological processes can create astonishing things that are easily mistaken for the work of humankind. Often, structures or altered materials that are either too similar to natural formations or too complex for our current analysis methods go unnoticed or are written off. Imagine anomalous mineral deposits or unusual patterns in sedimentary rock layers. They may be a ghostly hint of past activity, but without clear and durable artifacts like a hammer or a mechanical component, it all remains pure conjecture. On the other hand, paleontologists occasionally stumble upon finds that truly don't fit the overall picture. Anomalous chemical ratios in rocks or surprisingly well-preserved materials all add fuel to the fire of hypotheses about ancient technological civilizations. However, these sensational discoveries almost always lack context, the details that could transform a bold assumption into proven fact. And yet, the Earth's rock record does indeed offer some indirect clues hinting at the possible existence of pre-human civilizations. For example, the sudden and inexplicable appearance of enormous mineral deposits in a certain geological layer, or the discovery of strange clusters of microscopic spheres, microspherules, which may indicate colossal changes in the environment, possibly caused by human activity. But even these signals from the past are extremely ambiguous. Distinguishing clearly between natural geological cycles and traces of intelligent intervention is a titanic task. Ultimately, while paleontology offers us exciting prospects for studying Earth's ancient history, it often dashes our hopes of finding well-preserved and unmistakable traces of civilizations that came before us. This dearth of direct evidence only underscores how urgently we need new, more precise and sophisticated search methods. We need them to learn to read between the lines of this stone record, interpret ambiguous signals, and peer into places we couldn't previously. This raises a new question. What future technologies will help us search for the ghosts of the past? Modern technologies are already opening up entirely new horizons in this almost fantastical hunt for evidence. We are searching for what has remained hidden from our eyes for millions of years. Traditional archaeological methods, such as excavations and surface analysis, have always relied on visible objects. But recent scientific breakthroughs allow us to peer into previously inaccessible depths. One such revolutionary approach is the use of ground-penetrating radar, GPR, paired with 3D seismic surveys. Imagine a powerful X-ray for the entire planet. These non-destructive methods allow scientists to penetrate multi-meter layers of sedimentary rock and stone without disturbing their integrity. This opens up incredible opportunities for discovering hidden structures or artifacts underground, which could be the ruins of ancient cities or artificial structures. And when combined with machine learning algorithms, artificial intelligence can analyze enormous volumes of data, identifying anomalous patterns that could indicate the presence of ancient intelligence. Spectral imaging is becoming a particularly valuable tool. It allows us to see the world in wavelengths invisible to the human eye, infrared and ultraviolet. Like a detective using a special light at a crime scene, this approach helps detect the subtlest chemical and mineralogical traces that indicate the intervention of intelligent beings. For example, certain pigments, metals, or even synthetic compounds that may have been used in ancient construction leave behind a unique spectral signature that is strikingly different from natural minerals. This method can be applied remotely using drones or satellites, allowing us to explore vast, remote, and inaccessible corners of the planet. Furthermore, advances in isotope analysis, particularly in so-called isotope pattern thermometry, act as a geological thermometer. It allows scientists to determine the temperature of ancient layers with incredible accuracy and draw conclusions about the climate that prevailed on Earth millions of years ago. When applied to fossils or mineral deposits, these methods can reveal anomalous temperature fluctuations or chemical processes that don't fit into natural geological cycles. This, in turn, could be a direct indication of industrial activity involving the intervention of intelligent beings. The advent of micro-CT has opened another door to the past. This method, essentially a medical CT scanner for stones, allows us to peer inside the smallest or poorly preserved artifacts, forever sealed within the rock. Micro-CT creates high-resolution, three-dimensional images, allowing us to examine in detail the most complex elements of ancient technology or microscopic tool marks. This allows us to see not just an object, but the design and craftsmanship that prove its artificial origin. All these innovative approaches greatly increase our chances of discovering subtle, hidden, or time-worn traces that could be the legacy of ancient non-human civilizations. And as technology advances, we will be able to obtain increasingly precise and detailed pictures of the past, allowing us to gain a deeper understanding of the true history of our planet. Science and technology are blurring the line between what nature created and what intelligence could have created. Archaeological anomalies, which occasionally stir our imaginations and prompt reflection on ancient non-human civilizations, challenge our traditional understanding of history. They force researchers to continually re-examine established views. These anomalies are a wide variety of artifacts and structures that, at first glance, seem completely incompatible with the known technologies, time frames, or cultural context of ancient people. One of the most compelling categories of such mysteries is the incredibly precise and complex construction methods that seem millennia ahead of the technological capabilities of their supposed creators. For example, some megalithic structures around the world are distinguished by simply stunning geometric precision. Their alignment with the stars and planets indicates a profound understanding of astronomy and engineering that humanity acquired much later. These silent stone giants testify to a level of skill thought to be unattainable by people of that era. These extraordinary findings challenge our belief that ancient humans could have achieved such a level of development on their own without any outside help or knowledge transfer from a more advanced civilization. Furthermore, there are artifacts made of materials that seem completely out of place for their time, raising a host of questions about their true nature and origin. For example, discoveries of highly complex metal alloys or synthetic materials date back to an era when such technologies should not have existed. This may indicate the existence of alternative sources of knowledge, perhaps linked to non-human intelligence. Unusual isotopic compositions or mysterious microscopic traces on the surface of artifacts may also hint at production processes or sources far beyond the capabilities of the human race. And finally, there are completely inexplicable artifacts. Carved stones covered in symbols that have nothing in common with any known language or script. Objects bearing such marks of processing that they are impossible to reproduce even today. These finds plunge us even deeper into the abyss of mystery. They reveal something utterly alien, forcing us to wonder, were we the first? The artistry of their execution or their functional purpose don't fit into any known ancient culture. This could be a direct indication that, in the deepest antiquity, an entirely different form of intelligent life, or perhaps even an entire civilization, existed on our planet. Let's travel back in time and examine these mysteries. Monumental structures like the Great Pyramids still raise more questions than answers. These colossal structures are difficult to explain, even with modern engineering capabilities, let alone with ancient technology. And what about geological anomalies that simply cannot be explained by geology. Imagine perfectly smooth roads seemingly cut through mountain ranges and impassable landscapes, or gigantic underground complexes and chambers that seem to have no entrances at all. The construction methods of these structures and their true purpose remain a profound mystery to this day. This is precisely what gives rise to bold theories that their creators may not have been humans, but rather intelligent beings whose incredible knowledge and technology were irretrievably lost in the mists of time. When all these anomalies are put together, they become compelling pieces of some grand yet forgotten puzzle. These discoveries force us to completely reconsider the established view that humans are unique and the only intelligent species in Earth's history. They suggest that our distant ancestors may have been just part of a much larger and more complex worldview, one that may have included civilizations that existed long before the invention of writing, and perhaps even before the emergence of humanity itself. Right now, we'll take a closer look at how these mysterious artifacts and incredible structures challenge established archaeological theories, forcing us to take a completely new look at the ancient history of our planet. These unexplained artifacts and gigantic structures continue to baffle conventional archaeology. They are literally forcing scientists to re-examine the entire chronology and complexity of activity, not only of humans, but also, perhaps, of other prehistoric beings. According to the generally accepted version of history, human civilization is a relatively recent phenomenon. It emerged approximately 10,000 years ago and developed in a straight line, from primitive tribes of hunters and gatherers to more complex and advanced cultures. However, the sheer number of anomalous finds casts considerable doubt on this coherent theory. They hint that some ancient artifacts and structures may be significantly older or more technologically advanced than is commonly believed. These anomalies often possess characteristics that simply cannot be accommodated within existing scientific frameworks. This is what fuels endless debate and drives enthusiasts to continue their research. One of the main problems is artifacts whose age cannot be determined or whose craftsmanship is so advanced that it predates the known technological capabilities of the era by thousands of years. For example, intricate carvings on hard stone, mechanisms reminiscent of modern machine parts, and other mysterious objects call into question everything we know about the origins and development of human society. Tools and metal objects found in geological layers millions of years old evoke shock and bewilderment. They prompt us to consider the existence of lost knowledge and earlier unknown civilizations. And what about the structures? Megalithic monuments, such as giant stone circles or mysterious foundations of cyclopean proportions, are astonishing in their architectural complexity. This complexity is very difficult to explain with the primitive technologies believed to have been available at the time of their supposed construction. These anomalies force archaeologists to question the completeness of our understanding of technological evolution. They suggest that some artifacts may have origins that extend far beyond the generally accepted timescale. Moreover, some finds display signs of incredibly advanced manufacturing technologies, extreme precision machining, advanced metallurgy, or the use of materials with properties that simply defy the known capabilities of the time. These anomalies may be evidence of the existence of long-vanished civilizations that possessed a complex system of knowledge transmission. They may even be traces of extraterrestrial intervention. However, they also open the door to other equally fascinating theories, such as the Silurian Hypothesis. According to this hypothesis, an ancient, technologically advanced civilization may have existed on Earth long before the beginning of recorded human history. If the discovered artifacts are authentic and their dating is correct, this could mean that the history of our world is far more complex and multifaceted than modern textbooks suggest. These unexplained finds raise serious doubts among researchers. What if modern excavation and dating methods simply overlook or deliberately ignore evidence that doesn't fit into our conventional worldview? These artifacts are a powerful impetus for rethinking the very concept of human progress. They force us to seriously consider the possible existence of ancient civilizations that left behind subtle yet compelling traces. To unravel this mystery, we must look at history from a completely different perspective, allowing for the possibility of long-forgotten cultures that influenced the course of events in ways we are only now beginning to dimly comprehend. And among the most intriguing archaeological mysteries that can be rethought in light of this idea, the mystery of Easter Island stands out. The Silurian Hypothesis sheds new light on enigmatic structures whose origin and purpose remain unclear. For centuries, monuments such as the megalithic stone circles of Europe, the massive stone idols of Easter Island, or the perfectly calibrated Egyptian pyramids have inspired fascination and fueled countless speculation. Traditionally, these sites have been associated with ancient human civilizations possessing astonishing yet explainable engineering skills. However, if we accept the existence of previous, possibly highly advanced civilizations that existed before recorded historical events, these structures take on a completely new, far deeper significance. One of the most striking examples is the Göbekli Tepe complex in Turkey, considered the oldest megalithic structure in the world. Its monumental stone columns, intricately carved with animal images and abstract symbols, appear in the archaeological record seemingly out of nowhere, with no obvious predecessors. Could these be traces of an earlier civilization, possessing advanced construction technologies or sacred knowledge completely forgotten by subsequent cultures? The gigantic Nazca lines in Peru can be viewed in a similar light. These enormous geoglyphs, which can only be fully appreciated from above, challenge our traditional understanding of prehistoric art and engineering. Some researchers suggest that their scale and precision may indicate the use of techniques similar to aerial photography or remote sensing. This knowledge may have been inherited from earlier, technologically advanced societies. Moreover, the astonishing precision of the ancient Egyptian pyramids and megalithic temples on Malta demonstrates construction techniques that seem to exceed all conceivable capabilities of their supposed historical eras. These structures are aligned with celestial bodies with astonishing precision, and their complex internal acoustics and impressive scale of stonework raise numerous questions about the skill of their creators. according to the Silurian Hypothesis. These enigmatic structures may be the remnants of a long-vanished civilization that possessed forgotten engineering principles, and perhaps even otherworldly technologies. If we re-examine these archaeological mysteries from the perspective of the hypothesis of previous civilizations, we may discover entirely new levels of meaning. Their inexplicable features may be evidence of an older, technologically advanced society that left behind mysterious monuments, monuments that await understanding from a perspective radically different from the traditional one. Ancient megastructures and the unusual construction methods they employ offer intriguing clues that shed light on the possibility of advanced civilizations in the past. Unlike conventional archaeological finds, these massive structures often cannot be explained by known historical or technological possibilities. For example, some structures are composed of enormous stone blocks, perfectly fitted together without the use of mortar. Their alignment and geometry reveal a profound understanding of mathematics and astronomy. Structures such as megalithic stone circles, massive terraces, or complex aqueducts often demonstrate engineering mastery that surpasses what was thought possible with the primitive tools of ancient societies. What makes these structures particularly intriguing is their scale and precision. They seem to proclaim the existence of a highly advanced civilization that left behind unique architectural masterpieces. These ancient structures reveal complex planning processes, a deep understanding of material properties, and perhaps even technologies that predate conventional historical chronology by thousands of years. Unusual construction methods, such as the precise cutting and transport of gigantic stones over vast distances, may indicate lost technologies or practices that were completely forgotten over time. For example, some researchers have made bold suggestions about the ancients using analogs of modern geopolymer concrete or other composite materials, which sounds completely outlandish for that historical period. This suggests that the builders possessed knowledge that has been irretrievably lost over the centuries. Furthermore, anomalies in architectural styles, such as the use of multiple layers of diverse materials, complex geometric shapes, or the presence of structures that at first glance serve no practical purpose, may indicate something more than just cultural idiosyncrasies.